Hello, 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 everyone. Am I audible and visible? Yes. Hello, everyone. Am I audible and visible? Please, if yes, then give me a red heart and a fire emoji in the chat box. Hello, 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 everyone. So let me just check the chat box. Okay, 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 okay. Hello, hello, hello. Hi, everyone. Yes. Hi, everyone. How are you all? All good? Yes. All good? Let me just check it out. Yes. So let me just message on the group that we are starting, right? Okay, so for all who those know me and who don't know me, so my name is Sonali Malik and I'm a chemistry educator in NEET UG category. And today we have a mega marathon of DNF block in which we are going to cover complete a DNF block and we'll surely done and dust the complete chapter. Okay, so let's keep a target with ourselves that's till 1 or 2 p.m. we are going to end the marathon and sleep peacefully, right? Okay, so we'll be very quick, very fast, and I just need your support in the chat box, beta ji. If you will be giving this support in the chat box by giving hearts and thumbs ups and fire emojis, I will myself stay enthusiastic. Okay, fine. Now, in this session, my dear all students, we are going to cover the following topics. Okay, we should know what we're going to cover. Love from Sonali ma'am to all Tamil Nadu, to all Kashmir, and to all over the India students who are watching this marathon. Okay, right, fine. So here, now, if I talk about the very first thing which we are going to cover, it is basically the electronic configuration of D and F block elements, although we have done that in periodic classification, but we are going to revise. Why? Because electronic configuration is helpful in every topic. Whatsoever topic you will study, everyone, it is important, right? After that, we will study the general property, which is the longest topic. But yes, we have to be very quick in the very first half so that in the second half, when we get tired, we can complete these topics, which are, more of theoretical and ratification topics, right? So now, the very first general property, atomic size, then we'll cover melting point, then ionization energy, enthalpy of atomization, oxidation state, alloy formation, catalytic properties, interstitial compounds, standard reduction potentials, colored compound formations. All these properties we are going to cover, right? So duration is 8 to 9 hours, right? Because we have to complete each and every point of NCERT and we have to practice simultaneously the questions of JEE Mains and NEET, so it will require a little amount of time, okay? So you have to be supporting enough. Now, next, after this, right, we are going to do the preparation and properties of KMNO4 and K2CR27, right? Okay, after that, lastly, we have to do a very small block, which is F block, in which we are going to cover lanthanides as well as actinides. Is it clear, everyone? Okay, fine. Shall we start, guys? Yes. Shall we start, guys? Okay, so now let's just move ahead. Before moving ahead, for all those who ask the same question in the comment box every time that, ma'am, where we are going to get the notes? So you are going to get the notes on my Telegram channel, which is Sonali Malik Chemistry. You can scan this QR, or even on Telegram, you can type Sonali Malik Chemistry. You will find my channel. There I'll upload the notes, as well as in the Telegram channel of Unacademy NEET English also I'll upload the notes. Okay, fine. So let's start. So we are going to start with D block elements, right? Now, before starting into the definition, I just want to ask from you guys, okay, a little bit prior knowledge of periodic classification we are going to cover right here, right? Suppose this is our nucleus, right, guys? This is our nucleus, right? And this is, suppose, the outermost shell or the valence shell present in the atom, right, of a particular element. Clear? This is the nucleus, this is the outermost shell, or we can say the valence shell, right? Now, suppose this outermost shell or the valence shell is basically represented by the principal quantum number, which is n. Okay, so what is n right here? What is n right here? N is the principal quantum number. Am I clear? N is the principal quantum number. Okay, right, of outermost shell, of outermost shell, or we can say the valence shell, right? Okay, beta, n is not only the principal quantum number of the outermost shell, but in periodic classification and DNF block, we consider n also as period number, okay, right? Also as period number. And for every element, this n will be vary, right? Why? Because this n is basically, yes, it is the principal quantum number, but it is the value of maximum principal quantum number in electronic configuration of any element, okay, right? So this is basically the maximum value of principal quantum number in electronic configuration of any element. Okay, right? So now, if n is the outermost shell, okay, so one shell prior to the outermost shell is the penultimate shell, and for penultimate shell, the principal quantum number is n minus 1. Okay, now one more shell prior to penultimate shell is basically the anti-penultimate shell, and for anti-penultimate shell, bacha, principal quantum number is basically equals to n minus 2. Clear? Right? Now, what are D block elements, beta? D block elements are those elements in which last electron enters D subshell of the penultimate shell. Okay, so what are D block elements? These are the elements in which last electron enters where D subshell of penultimate shell, okay, of penultimate shell. Now, what do you mean by this? For example, I take the example of, say, scandium right here. The atomic number of scandium is 21. So we have already learned how to write electronic configuration in periodic classification. You guys must have written. I will tell you what is penultimate shell. Don't worry, I've already explained you in the previous page. Again, I'm going to tell you what is penultimate shell, okay? Just wait and watch. Here, if I write the electronic configuration of scandium, right? Its atomic number is 21. So it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Okay, right? Fine. So this is the electronic configuration of whom scandium. If you want to write the inert, or I should say the condensed electronic configuration. So we know that till here, this is basically the electronic configuration of argon. So you can also write argon 4s2, 3d1. Okay, now look at the electronic configuration of, my dear students, scandium. Quickly tell me in the chat box, everyone, that what is the value of maximum principal quantum number? What is the outermost shell which is being filled right here? Quickly tell me. Yes, quickly tell me in the electronic configuration, what is the maximum value of principal quantum number which you can see right here? Quickly tell me, everyone. Yes, quickly. What is the maximum value of principal quantum number? Yes, I can see it is corresponding to 4s subshell, and that is basically 4, right? Okay, so that means here the maximum value of principal quantum number is basically 4. That means this particular element belongs to fourth period, first of all. Okay, it basically belongs to which period? Fourth period, my dear students. Okay, right? And this fourth period is basically, or I should say 4 basically, right? 4 basically stands for what? Stands for what, my dear students? Here, this 4 basically stands for the outermost shell. Okay, so if n is equals to 4 is the outermost shell. One shell prior to the outermost shell is the penultimate shell. Okay, so that means here n minus 1 equal to 4 minus 1 equal to 3. So n is equals to 3 stands for what? Stands for penultimate shell. Yes, it basically stands for what? It basically stands for the penultimate shell. Now, in the penultimate shell, we have D subshell. That is basically 3D, right? Okay, that means here, last electron enters, where? It enters D subshell of the penultimate shell, which is n is equals to 3 shell. Okay, right, fine. That means what? Since here the last electron enters D subshell of the penultimate shell, therefore, my dear students, here scandium is said to be what? Scandium is said to be a D block element. Okay, fine. Therefore, scandium is a D block elements. Okay, scandium is a D block element. Clear, everyone? Any problem right here? Any problem right here? I request all of you to tell your friends that we are doing D and F block so that they can also join, right? So we can complete in one go. Fine. Okay, you can tell your friends that we have started it. Fine. Okay, so now you must have been clear what are D block elements, right? And why scandium is basically known as D block elements. Is it clear, guys? If it is clear, please give a heart or a thumbs up in the chat box. Now, if I will look at the entire periodic table, now where is the position of D block elements lies? See, but I have told you priorly also that group 1 and 2 basically are S block elements, okay, in the periodic table. Fine. Similarly, the group 13 to 18 are P block elements, right? What are they? They are P block elements, right? And in between S and P block elements, we have what, everyone? We basically have from group number 3 to group number 12 D block elements, okay? We have D block elements. Now, if I'll count the total number of groups which are present in the D block elements, they are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That means there are a total of 10 groups which are present in D block. Now, question arises, why this is so, ma'am? Okay, now question arises, why this is so, ma'am? Okay, so now we have to see why this is so. See, beta, if I have to consider D block elements, right? Here, the last electron enters D subshell, okay? Right? We know that in D block elements, last electron enters D subshell, okay? Enters D subshell, right? Okay, now we have studied in the previous class azimuthal quantum number, right? We have studied that L basically stands for what? L stands for azimuthal quantum number. Okay, it stands for azimuthal quantum number, right? Now we know that azimuthal quantum number can have value 0, 1, 2, 3. 0 basically corresponds for S subshell. 1 basically corresponds for P. 2 basically corresponds for D, right? Okay, that means for D subshell, the value of L, that is azimuthal quantum number, is basically equals to 2. Right? Now, if azimuthal quantum number is 2, then M, magnetic quantum number, which basically tells the number of orbitals which are present in a given subshell. Here, magnetic quantum numbers can have values from minus L to 0 to where, beta G? 2 plus L. Okay, right? That means here it can have values from minus 2 to 0 to plus 2, right? Now from minus 2 to 0, we have minus 1, and from 0 to plus 2, we have plus 1. That means magnetic quantum numbers have 5 value corresponding to azimuthal quantum numbers. L is equals to 2, right? That means here D subshell has how many orbitals, my dear students? D subshell has 5 orbitals, okay, right? Therefore, D subshell has 5 orbitals, okay? It has 5 orbitals. Fine, everyone. What are those orbitals? Rajay, I've already told you in periodic classification, they are 5 in number, right? And they are basically dxy, dyz, dxz, dx square minus y square, and dz square. Now, one orbital can maximum accommodate how many electrons, guys? It can maximum accommodate 2 electrons, right? Okay. Therefore, you have 5d orbitals, right? So they can maximum accommodate how many electrons, beta G? They can maximum accommodate 10 electrons, right? So what we will say? We will say that therefore 5 d orbitals, 5 d orbitals can maximum accommodate 10 electrons, right? Fine. That is the reason that D block has how many groups? 10 groups, right? Fine. So therefore, beta G, D block consists of how many group? 10 groups, okay? D block consists of how many group? 10 groups, okay? It consists of 10 groups. Clear? Now, what all these groups are, beta G? They start from group number 3 to group number 10, okay? Group number 3 to group number 10. Is this thing clear that why D block basically consists of 10 groups from group 3 to group 12? Yes, from group 3 to group 12. It is clear, everyone. From group 3 to group 12. Clear? Yes, clear. Right, I have corrected. It's 12. By mistake, I've written 10. Okay, everyone. Fine. So here are the 10 groups. Okay. Here are the 10 groups you can see, right? Group 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Clear? If it is, then please give the red heart in the chat box. Let's just move ahead. Let's just move ahead. Okay, right. Now, next thing is basically we have to learn how to write the electronic configuration of various D block elements. So, in order to do that, we need to learn a simple trick, although I have told that in the previous lectures. Today, I'm going to revise it for 2 minutes and then proceed ahead. Okay, so if you have to write the electronic configuration of LE elements, right? First, beta, if you have to write the electronic configuration, you need to find the period, right? How you will find the period? For example, if you want to write the electronic configuration of scandium, whose atomic number is 21. Okay, so what is period, beta G? What is period, Rajay? Period is the period number of nearest noble gas. Okay, it is period number of nearest noble gas, right? Nearest noble gas or nearest inert gas, right? We all know that, beta G, group 18 are the inert gases or the noble gases, right? They are basically helium, neon, argon, krypton, xenon, radon and oxyxenon. Now here, scandium is said to have an atomic number of 21. So which noble gas is nearest? Beta, in group number 3, argon is the last element, right? Sorry, in period number 3, argon is the last element, and in period number 4, beta G, krypton is the last element, right? That means here, scandium must lie in the period of krypton, right? It must lie in the period of whom? It must lie in the period of krypton. Now, krypton is said to have period 4, right? That means scandium is basically present in period number 4, okay? It is basically present in the period number 4, right? Okay, so in writing the electronic configuration, first, beta, you have to took the noble gas of the prior period. Like for example, scandium is lying in the 4th period. So the prior period is 3rd period, in which the noble gas which is lying is basically the argon. Okay, so here we are going to write argon 18. Right? After that, beta, the subshells are basically filled in the order Ns to N-2F to N-1D to Np, where N is basically the period number, right? Now here, scandium lies where? In period number 4. Okay, so subshells will filled in the order Ns is basically your 4s, then N-2F should be 4 minus 2, right? And that is basically your 2f. Now 2f subshell does not exist, beta ji, right? 2f subshell does not exist. We have already learned in periodic classification, right? Why? Because the value of principal quantum number should always be greater than azimuthal quantum number, right? And here for 2f, the principal quantum number is 2, and for f, the azimuthal quantum number L is 3. So this subshell is not possible. So next subshell which should be filled is basically, but beta g, n minus 1, that is 4 minus 1d 3d. Right? And then NP is basically 4P. Clear, everyone? So here, if we have to write the electronic configuration of scandium, we have already written argon, right? We are writing the condensed electronic configuration. So while writing argon, we have already filled how many electrons, beta G? We have already filled 18 electrons, right? So now the next electron will go where? Yes, the next electron will go where? The next electron will go into 4s, okay, right? Now S can have maximum of 2 electrons. After that, the next electron, 18 plus 2, 20 are already filled, one more need to be filled, will go in 3D. So the configuration comes out to be 3D1. Clear, everyone? Okay. Similarly, if I have to write the electronic configuration of yttrium, whose atomic number Z is 39. Okay. So if atomic number is 39, then the period is the period of the next nearest noble gas, right? So krypton is the last element in group 18 lying in the 4th period. Okay, right? So that means here yttrium must lie in the period of xenon, which is number 5, period number 5. Okay, so here the maximum value of principal quantum number, or n, or I should say the period number, is basically the 5, right? Now while writing the electronic configuration, you have to take the noble gas of the prior period. So prior period is period number 4. So you basically have to take what? You basically have to take krypton. Am I clear? You basically have to take krypton, whose atomic number is basically 36. Now here n is 5. That means it basically lies in which period? It basically lies in period number equals to 5, right? So first 5s is being filled, ns, then 5 minus 2f, 3f, but a 3f does not exist, right? Same logic. The value of principal quantum number has to be greater than azimuthal quantum number. Here equal is there. Okay. After that, beta g, n minus 1d, that means 5 minus 1d, 4d is being filled, right? And after beta g, np, that means 5p is being filled. Clear, right? So here till krypton, 36 electrons are filled. Yttrium has atomic number 39. That means you have to fill 3 more electrons, guys. Yes, you have to fill how many electrons more? 3 more electron, guys. Okay, fine. So where it will go? First 5s has to be filled. So it will be 5s2. Now S can maximum has 2 electron. So the next electron will go in 4D. Right? And you have to fill 1 more electron because 38 electrons are already filled. So here the electronic configuration is 5s2 4d1. I hope it is clear to you guys how to write the electronic configuration, right? Now we will use this knowledge in order to understand the electronic configuration of d block elements. Okay guys, perfectly clear? Yes, perfectly clear. Cool. Now, quickly look at the electronic configuration of scandium, right? Scandium basically lies in 4th period, right? And in the case of scandium, 3D is being filled. Clear, everyone? Okay, fine. And similarly, if I look at yttrium, yttrium is the first element of D block in the 5th period, and here I can clearly see 4D is being filled. Yes, quickly tell me what ma'am is trying to say. Ma'am is trying to say, my dear bacha log, see, what I am trying to say is, my dear bacha log, look at it here, that scandium is the first element. Okay, scandium is the first element, right? Okay, here 3D is filled, right? And it basically lies in 4th period. Fine. Okay, fine. Similarly, here scandium is 3D1. Titanium will be what? 3D2. And you will move ahead till the last element, zinc, right here, beta G. It will have 3D10. That means in 4th period, right, in D block, 3D is progressively being filled. Am I clear? Right. Similarly, in period number 5, we can clearly see beta G in yttrium. Yttrium is a first element. Here, 4D is here 4D is being filled, right? Okay, fine. So as you will move ahead till cadmium, we will see that 4D will be completely filled right here when you will write the electronic configuration. So what we are going to understand right here, that D block basically starts from period number 4, right, and goes till period number 7. Am I clear? Okay. In period number 4, 3D is progressively being filled. In period 5, 4D is progressively being filled. In period 6, 5D is progressively being filled. And beta ji, in period number 7, 6D is progressively being filled. Right? Okay. That is the reason here the 10 elements which basically lies in your period number 4 are 3D series. Okay, right, and the 10 elements lying in period number 5 are 4D series. In period number 6, 10 elements which are lying are known as 5D series, and 10 elements which lie in period number 7 are 6D series. Is this thing clear? If it is clear, please give a heart emoji in the chat box. Clear, guys? Yes. Is it clear? Okay, so what we got to understand that, ma'am, in period number 4, we have 3D series. Okay, we have 3D series. In period number 5, we have 4D series, right? We basically have 4D series. In period number 6, we basically have 5D series, okay? We basically have 5D series, right? Fine. And in period number 7, everyone, we basically have 6D series. Okay, we have 6D series. Okay, right. Now here, if I talk about the 3D series, it is the first transition series. Okay, now transition elements are D block elements, although there is some difference which I'll tell you ahead in this lecture, right? But here in 3D, first time D block or the transition elements are actually being filled. Okay, so 3D series is also basically known as what? It is basically known as first transition series. Am I clear? It is also known as what? First transition series. Am I clear, everyone? Right? 4D series is basically known as what? Second transition series. Okay, right? It is known as second transition series. Perfect, everyone. Fine. If I talk about 5D series, it is basically known as third transition series. Okay, it is basically known as third transition series, right? Okay, cool. And if I talk about 6D, 6D is basically known as fourth transition series. Am I clear? It is basically known as what? Fourth transition series. Clear, everyone? Yes. Is it clear? Perfectly clear. Okay, right. Now, here, if I talk about your 3D series, beta ji, if I talk about your 3D series, right, the first element of 3D series is scandium and the last element is zinc. In 4D series, first element is yttrium, last element is cadmium. Right? In 5D series, first element is lanthanum and the last element is mercury. Right? In 6D series, the first element is actinium and the last element is copper-cenium. Right? Everyone? Right, right, right. Okay. That means your 3D series starts from scandium and go till zinc. That means scandium is the first element and zinc is the last element. Okay. If you will write na beta, in this manner only things will get settled up in your mind, because there is lot of ratification right here. So you have to go in the order in which ma'am is teaching you. Trust me, once you will complete it, you will yourself will able to understand everything and you don't have to ratify it. Okay. Right. Now second is from ytterbium to cadmium. Right. Next is from lanthanum to mercury, and the last one is from actinium to copper-cenium. Okay, we know the magic number rule, guys, right? We know the magic number rule. So for group 3 of the periodic table, the magic number is 1832, right? That means if I know the atomic number of scandium, which is 21, right? Now, since scandium is basically lying where? Scandium is lying in group number 3, okay, right? So, if I will add 18 to the atomic number of scandium, I will get the atomic number of yttrium, which is 39, right? Next magic number is 18. So if we will add 18 to the atomic number of yttrium, you will get the atomic number of lanthanum, which is 57. And when you will add 32 to the atomic number of lanthanum, you will get the atomic number of actinium, which is 89. Is it clear, everyone? So 57 plus 32 is basically equals to 89. Perfectly clear, guys, right? However, if I have to come to group 4 to group 12, here the magic number is 18, 32, 32. Why does the magic number change right here? It's pretty simple, guys. It's pretty simple. Why the magic number is changing, beta ji? Because what will happen, right? The first magic number will be, 18 only. But after, when you will come to the 60 series, after lanthanum, beta, 14 lanthanides come, which are basically your F block elements. So instead of 18 as the next magic number, you will have 18 plus 14, which is 32. Am I clear? Right. So you will have what? You will have 32 as the next magic number, right? So now we all know that atomic number of zinc is 30, right? Okay. So 30. The first magic number is 18. You can add, you will get 48. After that, the next magic number is 32. 48 plus 32 comes out to be 80. The next magic number is 32. So 80 plus 32 is 1, 1, 12. Am I clear? It is 1, 1, 12. Perfect. Okay, so we have done the first element and the last element of the individual series. At the same time, we have learned their atomic numbers with the help of what? Magic number rule. If it is clear, please give heart emoji in the chat section. If it is clear, please give a heart emoji in the chat section and the fire emoji and say CC. CC means crystal clear. Okay, right. Now here, we will write the electronic configuration of the individual 3D series, 4D, 5D and 6D series, and we will learn the mnemonics in order to remember their names. Clear, everyone? Okay, so to be begin with, we have the very first series right here, which is basically your 3D series. Okay, so in order to remember the names of 3D series element, first we need to know that from which atomic number to which atomic number actually 3D series is. So I can quickly see that it is from atomic number 21 to atomic number 30, right? So it is basically from atomic number 21 to atomic number 30. Clear, everyone? So meanwhile, we know that there are 10 elements which we need to remember. So you just have to fill the electronic configuration now. So it is 22. Matlab you have to fill the counting now, not the electronic configuration. You just have to write the counting, okay? That after 21, 22 comes, after 22, 23 comes, after 23, 24 comes, after 24, 25, 26, 27, 28, 29, right? So how we can remember the name of 3D series? Here, see, one is shloka in Hindi. If you can understand Hindi, well and fine. Otherwise, you have an English mnemonic also. So Hindi mnemonic is Sakti Vikarman. Okay, Sakti basically stands for suck. Okay, suck, and T. So scandium and titanium. Okay, Sakti, scandium and titanium. Vikarman. Okay, V vanadium, Kar chromium, Man manganese. Clear? Man manganese. Perfect, everyone. Perfect, 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 perfect. Yes, we are just revising it. We'll done in 15-20 minutes. Why I'm revising? Because I'll be needing it in the entire periodic table, beta. Right? It is increasing my time and my energy only, but it is useful. That is why I'm doing it. Okay, Sophie, fine. Now, Ficoni, Fe-co-ni. That means iron, cobalt, and nickel. Cogen means Cu. Jan means Z and Zang. That means copper and zinc. Okay, copper and zinc. This is a shloka, Sakti Vikarman Ficoni Cogen. So if you can remember, you can remember in this particular manner. Otherwise, everyone, you can basically do in a English way. We all know Sachin Tendulkar. So he's a very famous batsman, but he have taken a pledge that I will coach only India. Why? Because Bharat, we all love him. Okay, right, fine. So he said, I will not coach Zimbabwe, I will coach only whom? India, right? So from there we got a mnemonic. Sachin, scandium, Tendulkar, titanium. Very crazy, it's very crazy to coach only India. Okay, so very, V vanadium, crazy, Cr, chromium, man, Mn, manganese. Okay, 4, then Fe, iron. Coach, cobalt. Neither, Ni, nickel. Coaches, here you have copper. Zimbabwe, so you can have zinc. Okay, right? So you can do any mnemonic. Sakti, Vi, Kar, Man, Fi, Ko, Ni, Ko, Jan. Okay, Sakti, Vikarman, Fi, Ko, Ni, Ko, Jan. Perfect, everyone. Perfect, peer, everyone. Is it clear? Yes. Is it clear, everyone? Okay, now here I have to learn how to write the electronic configuration as well as general electronic configurations. See beta, I have already taught you how to write the electronic configuration of scandium. Right, I can again tell you, not an issue. Right, see, I know that scandium has atomic number 21, titanium is 22, vanadium 23, chromium 24, manganese 25, Fe 26, then 27, then 28, then 29, and then 30. See everyone, look at me very carefully. We know that here 3D series basically lies in 4th period, okay? 3D series basically lies in 4th period, right? So that means here the value of maximum principal quantum number, or I should say n, or I should say the period number is basically 4, right? Okay, so we know that first Ns is filled, then N minus 2F is filled, then N minus 1D is filled, and then NP is being filled. Okay, so Ns here, since N is equals to fourth period, first 4S will fill. Already told you N minus 2F, 4F does not exist. Okay, so after that, what will be filled right here, beta? 4 minus 1D, that is basically 3D, right? Fine. And now here, since it is a 3D series, so last electron enter 3D only. So idealistically, after 3D, 4p has to be filled, but it won't get filled. Am I clear, everyone? Okay, fine. So now, here, while writing the electronic configuration of scandium, which is in 4th period, I have to take the noble gas of the prior period, which is 3rd period, and that is argon. Okay, so here, first I will write argon. Am I clear? First I will write what? Argon. Okay, so after argon, already 18 electrons are filled. Next will go in 4s. Right? Once 4s is filled, the next will go in 3D. So electronic configuration is 4s to 3d1. In titanium, nothing you have to do. Add one more electron because the atomic number is increasing just by 1. Okay, right? In vanadium, 3. Right, in chromium, it should be 4, idealistically. But beta, as we move to, higher elements of 4th periods and onwards, what happens is that the energy gap between 3rd and 4th shells basically gets decreases. So it's very easier for electron to get excite from 3D to 4s or from 4s to 3D. Clear? So what happens is right here, beta, that one electron basically gets excited from 4s to 3d. So it has 4s1 and 3d 5. Now why this excitation has happened, beta G? Because once this has happened, right? Once this has happened, chromium, okay, chromium right here is said to have, my dear bacha, 5 electrons in 3D, and when we have 5 electrons or 10 electrons in 3D, it is a half filled or a fully filled stable electronic configurations. And in atomic structure, we have studied that stable electronic configurations are preferred, and they are stable. Why? Due to exchange energy as well as due to symmetry that you must have studied in atomic structure, right? So this is what half filled, stable electronic configuration. Okay, half filled stable electronic configuration. Am I clear, everyone? Okay, this is half filled stable electronic configuration. Now, because of this, it is just not according to the trend, right? If should have been according to the trend, and then in 3D you should have 4. So that is why we say that it is an exceptional electronic configuration. And now we are going to mark star to all the exceptional electronic configuration. Okay. Then moving to manganese, here no exception, right? Fe, again no exception. Cobalt, no exception. Nickel, no exception. Now idealistically in copper, in S you should have 2, and in D, you should have 9. But here also the same thing happens. 1 electrons get excited from 4s to 3d, right? Why? In order to have a fully filled 3d subshell in the case of copper, right? So that is why the electronic configuration of copper is also exceptional. Why? Because it leads to fully filled, stable electronic configuration. Fully filled, stable electronic configuration, right? Zinc, no exception, 4s2, 3d10. Okay, so now if you will look at the electronic configuration, what should be the general electronic configuration right here, right? General electronic configuration, everyone, here should be the noble gas used is basically argon. Okay, right? And in S, either you can have 1 electron in the case of copper and chromium, or you can have 2 electrons, and in 3d you can have 1 to 10 electrons. Okay, so this is basically the general electronic configuration in the case of 3d series. They might ask you. Okay, fine. Now let's move to the 4d series. Now for 4d series, we basically have a mnemonic, very interesting, right? It is about a guy named Rohan is basically a very below average child. Every time he gives his exam, he basically fails. That is why he always gives his paper for rechecking. Am I clear? He always keep giving his paper for rechecking, and this time teachers have again checked it, but again, he failed, right? One teacher checked, he got failed. So the remaining teacher have decided that what's the need, yaar? He's already, a failure. He needs to improve. So we are not going to waste our time. Okay. So on the basis of that, we basically have got the mnemonics that yes, 0, not many teachers recheck Rohan papers again to confirm. Okay, so from yes we have Y, which is yttrium. From 0 we have Zr, which is zirconium. Okay, from not we have Nb, which is a niobium. Am I clear, everyone? Okay, fine. From many, we have MO, means molybdenum. Then from teachers, we have TC, which is technetium. From rechecked, we basically have ruthenium. And from Rohan, we basically have rhodium. Clear? Right. From papers, we basically have palladium, which is PD. From again, we have Ag, which is silver. And from confirmed, we basically have cadmium. Is it clear, everyone? Okay, fine. So here, we have yttrium as the first element, then zirconium, then niobium, then molybdenum, then technetium, then ruthenium, then rhodium, palladium, okay, silver, and cadmium, right? We already have seen that here 4D series basically starts from where? Okay, 4D series basically starts from atomic number 39 to 48. Okay, right? That means atomic number of yttrium is 39 and it will goes till 48. So now fill the counting right here, right? So what it is 40, 41, 42, 43, 44, 45, 46, 47, and 48. Now let's see the electronic configuration. Let's see the electronic configuration. Right, in Hindi people have a mnemonic, ye zindagi nahi mohabbat tumhari ro ro pukaregi aaj chandni. So you can take that mnemonic also. But yes, that is for only Hindi students, right? Obviously the English medium students won't be able to understand it. So that is why I haven't given it right here. Am I clear, everyone? Okay, fine. Chalo. So now let's come to the electronic configuration. Now if I talk about 4D series, it basically lies in period number 5. Okay, right? So here, the subshells are always filled in the order from Ns to N minus 2F, right, to N minus 1D to NP, right? So here, N is 5S, right? 5 minus 2F, that means 3F. 3F does not exist. I've already told you, right? Fine. So next, which will be filled will be basically 5 minus 1D, that is 4D, and then 5P. Is it clear, everyone? Fine. So here, if we have to write the electronic configuration of yttrium, right? Fine. So let's first write the atomic number of all the elements, right? First, let's write the atomic number of all the elements. Guys, so now here we know that all these align the period number 5. So we have to take a noble guess of the prior period, which is period number 4, guys. Okay, fine. So period number 4, noble gas is krypton, whose atomic number is 36. Cool, right? So now, first subshell which will be filled is the 5s. So atomic number is 39. We will fill 36 plus 2, 38 electrons already filled. Then next 4D. So it is 4D1. Am I clear, everyone? Okay, perfectly clear. Now, when you will move to zirconium, you have to do nothing special. Fill one more electron right here. We thought the same for niobium, that it will have 3 electrons in the 4D. Listen to me very carefully. We thought this will happen, but actually happens what? Again, the difference in energy between 5s and 4D is less. And electrons keep on moving here and there, right? From 4s, from 5s to 4D, from 4D to 5s. And you can, cannot give any logic for the electronic configuration. You just have to see the electronic spectrum. While seeing the electronic spectrum, you'll get to know the number of unpaired electrons, and from the unpaired electrons, beta ji, you can basically tell the electronic configuration. Am I clear? You can basically tell what? You can basically tell the electronic configuration just by seeing, yes, just by seeing the electronic spectrum. So when we will see the electronic spectrum of niobium, what happens is we see that in S it basically has 1 electron, and in D it basically has how many electrons, beta ji? 4 electrons, right? Similarly, in molybdenum, you have 1 electron right here. In technetium, again, you have 1 electron right here. In ruthenium, again, 1 electron. In rhodium, again, 1 electron, right? And in PD, we expected the same, right? Fine. But what happens is that here 5s does not has any electron. This 1 electron also gets excited to 4D, and it has 4D10, 5s0. Clear, right? Ag is next to copper. So it has electronic configuration similar to copper, which is 5s1, 4d10. And in the case of cadmium, fully filled. So this is the electronic configuration, right? Now, if I have to see whom are exceptionals, so we can see niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver. All of them are said to have what, everyone? All of them are said to have exceptional electronic configurations. So we need to remember them. Yes, we need to remember them. Is it clear, everyone? Okay, fine. Now, here if I have to write the general electronic configuration, what could be? It is basically krypton, right? Fine. In 5s, we can have 0, as in the case of palladium. We can have 1, as in the case of niobium, molybdenum, and so on. And we can have even 2, as in the case of yttrium, zirconium, and cadmium, right? So you can have 0 to 2 electrons. Am I clear? We can have 0 to 2 electrons, and in 4D again we can have 1 to 10 electrons. So this is basically the general electronic configuration. So I have told you the trick to remember. Now you can easily remember it. Yes, now you can easily remember it. Clear, everyone? Fine. Okay, cool. Chalo, let's just move ahead. Tushar, not 60, not 60, 4D beta, 4D, not 60, 4D. It's 4D series. Okay. Now, let's move ahead and come to 5D series, okay? Let's come to 5D series. Now, we know that 5D series basically starts from lanthanum, whose atomic number is 57 and goes till mercury. I've already told you whose atomic number is basically 80. So, till now, what we have did? Yes, till now, what we have did? We have written the counting. So, we will try to write the counting in a similar manner right here. Yes, is it clear? Right? So what you will do? You will do 58, 59, 60, 61, 62, 63, 64, 65. Oh my God, ma'am. How can after 65 we can have 80? That means there is some mishappening which is, happening right here. And what is a mishappening which is happening right here, beta? The mishappening is that after lanthanum, yes, after lanthanum, which you can see right here, okay, after lanthanum, which is the first element of 60 series, we have lanthanides. Am I clear? We have lanthanides starting from cerium 57 to lutetium 71, in which 4F is progressively being filled. Am I clear? Right? In which 4F is progressively filled. Okay, progressively filled. Fine. Am I clear? Is it clear, everyone? If it is clear, gives a thumbs up in the chat box, or a heart emoji, or a fire emoji. Right? Fine. So that means since from 58 to 71, we have lanthanides, right? And after lanthanides, which are till 71, we have 72 hafnium, which is again 60 series element. Okay, so hafnium have an atomic number of 72. After that, 73, 74, 75, 76, 77, 78, 79, and then 80. Clear, everyone? Now, what is a mnemonic? What is a mnemonic? What is a mnemonic to remember this? What is a mnemonic to remember the elements? Beta. See, there is a guy, Larry, who loves to travel the world, but every guy wants to settle in his life. And what is the end game? Which is the end goal? We want to get settled down with a good looking, nice, caring life partner. We all want to settle down like that? Yes or no, everyone? We all want to settle down like that? Agreed? Right. So Larry also decided to propose to his girlfriend and to get married. And his girlfriend basically lives where, beta ji? His girlfriend basically lives in Ireland. Larry loves to travel the world, and now it's time for Ireland right here. Agreed? Okay, fine. So Larry, right? Larry, from Larry we have LA, Lanthina, right? From has fun, we have HF, which is hafnium. Okay. From traveling, we have TA, which is tantalum. From world, we have W, which is tungsten. Okay, guys. Fine. From reach, we have RE, which is rhenium. From out, we have OS, which is osmium. From Ireland, we have IR, which is iridium. From please, we have PT, which is platinum. From ask, we have AU, which is gold. And from her, we have HG, which is basically mercury. Am I clear, everyone? Yes, am I clear, everyone? Okay, so here we have lanthanum, hafnium, tantalum, tungsten, right? Then we have rhenium, then we have osmium, iridium, platinum, gold, and mercury. So this way we can remember the elements in the case of whom? Elements in the case of 5D series. Again, ma'am, we need to learn the electronic configuration, right? What we need to learn, ma'am? We need to learn the electronic configuration. That is the most important thing. See, if I come to 5D series, now 5D series basically lies in which period, beta ji? It basically lies in period number 6. Okay, right? Now, here, subshells are being filled in the order NS, then N minus 2F, right? Then whom? Then N minus 1D, then NP, right? So when N is equals to 6, first 6S will fill. Then N minus 2F, that means 6 minus 2F, 4F will filled. Now can 4F be filled? Yes, 4F exists, beta. Why? Because here N is, yani principal quantum number is 4 and azimuthal quantum number for F is 3. As long as N is greater than L, that particular subshell can exist. Am I clear, everyone? Okay, so after 4F, the next shell which will be filled is N minus 1D. That is 5D, and once 5D is filled, although 5D is only filled in 5D series, but if 5D has also been filled and we are moving to P block, now we are not doing it, right? Then 6P will be filled. Am I clear? Fine. Okay. Now, here, The first element is lanthanum, whose atomic number is 57, right? Then after lanthanum, we basically have hafnium, okay? So hafnium atomic number is basically 72 because in between lanthanum and hafnium, we have 14 lanthanides. Is it clear, everyone? We have 14 lanthanides. Cool? Okay, after that we have 73, 74, 75, 76, 77, 78, 79 and 80. Okay, right. Now you tell me very quickly one thing. Yes, guys, tell me very quickly one thing right here. Beta, when we have to write the electronic configuration of lanthanum, which basically lies in period 6, we have to take a noble gas of prior period, which is period number 5th, and that basically is xenon, whose atomic number is 54. Okay, so the very first subshell which we expect to get filled is 6s. After that, the next subshell which has to be filled should be 4f, and it should have one electron in the 4f. But when you will open NCERT, you will find again the electronic configuration of lanthanum is exceptional. Here, the electron does not goes to 4f, it directly enters to 5d. Am I clear? It directly enters to 5d. Okay, fine. That is why lanthanum is basically, my dear students, is basically what? It's basically a d block element. Why? Because the last electron is entering 5d. However, as per the Bohr-Bury rule or your Aufbau principle, the electron should have entered 4f now. That is why lanthanum have properties similar to lanthanides. Is it clear, everyone? Okay, fine, cool. Now, here, now when we comes to hafnium, now before hafnium I have told you lanthanides have been there, have been came, and in lanthanides 4f have been completely filled. Okay, right. So here 4f is completely being filled, fine. Okay, ji, and one more electron basically goes to 5d. So you can add 54 plus 2, 56, 56 plus 14, 80, sorry, 56 plus 14, 70, and 70 plus 2, 72. So here the atomic number of hafnium is 72. Okay, guys, fine. Now, similarly in the case of tantalum, it is 3, clear. Tungsten, it is 4, without any exceptions, okay, without any exceptions. It is 5. Osmium, it is 6. Iridium, it is 7. And platinum, we expected it should be 2 and it should be 8. Right, everyone? But what happens again? One electrons get excited from 6s to 5d. Okay, one electrons basically gets excited from 6s to 5d. So here the electronic configuration of platinum is exceptional. Okay, bhai, it is basically what? It is exceptional. Fine. So what you call bhai in Tamil and Telugu, or the language in which you are native to, what you call bhai right there? Please tell me in the chat box. I'll call you by the same name. Right? What you call brother or bhai? In Hindi we call bhai. What you call in Telugu? Yes, Telugu. Yes, quickly. Telugu. Now, here, if I talk about AU, since it is copper AgAu, so it is lying below copper and Ag. So here the electronic configuration is similar to them. Fine. So it is 1 here and 10 there. Fine. And in the case of Hg, no exception. No exception. Fine. That means here only 2 exceptions are there. What all are these? These are PT and AU. Okay. PT and AU. Only 2 exceptions which are basically existing right here. Now, if I have to write the general electronic configuration, Anna, okay, so I'll call you Anna, Annaya, okay, I'll call you Anna. Clear, Anna? Is it clear to you, Anna? Clear, brother? Right? Okay, to all Thamis and Annas, it should have been clear, right? To all Thamis and Annas. Now, if I have to write general electronic configurations, beta, see, 4f is not being filled in the case of lanthanum. So you don't have to write 4F. You have to write the common one, okay? So first xenon will come. In 6s, you can have 1 to 2 electrons. And in 5d, you can have 1 to 10 electrons, okay? So this is basically what? It is basically clear to all you guys, right? No, Thambi. Okay, Thambi. Oh, I'm really sorry. It's Thambi. Thambi. To all Thambis and to all Anas. And to all Anyas. I'm so sorry. My bad. Fine. This is what? This is the general electronic configuration. Fine. This is what? This is the general electronic configurations of 5D series. Now, let's come to the last one, everyone. So, no, my back. I agreed it's my back. Completely taking it's my back. Fine. Okay. Fine. It's my back. Sorry, Anna. Sorry, Thambis. This brother is saying sorry to you guys. Fine. So now, let's come to 6D series, everyone. Now, let's come to 6D series. Okay. So now, if I talk about 6D series, beta ji, here, again, it is basically from actinium, whose atomic number is 89, till copper cerium, whose atomic number is 112. Now, similarly, as in the case of lanthanum, after lanthanum, lanthanide lies. Okay, right? After actinium, actinides lies. Am I clear? No. Two sisters we call Ani. Okay, two sisters we call Anis. Right? Okay, cool. Now, so after actinium, we have what, everyone? After actinium, we basically have actinides. Fine. After actinium, we basically have actinides. Now, actinides are basically from thorium 90 to lawrencinium 103, and in actinides, beta ji, 5F is being progressively being filled. Am I clear, everyone? Fine. Okay. It is basically 5F is progressively being filled. Okay. Progressively being filled. Clear, everyone? Fine. So that is why you will skip the atomic number 90 to 103. That means here RF will have atomic number what? It will have 104. Okay. So after actinium 89, you will have RF, which is basically equals to 104. Right. So this is 105, 106, 107, 108, 109, 1110 and 1111. Cool, everyone? Yes, cool, everyone. Akka. Okay, akka. Okay, akka and Anas. Is it clear? Huh? Chalo. So now let's come to the mnemonic. We all have studied R.D. Sharma. You know, R.D. Sharma is one of the pioneerest book, right? It's one of the pioneerest book which I used to study in 9th and 10th. And our teachers used to make our paper from R.D. Sharma and R.S. Agarwal only. So from there I have got the mnemonic of 60 series. Although it is not important. If you can't remember it, you can leave it because majority of elements of 6D series are radioactive. That is why we don't study their properties. Am I clear, everyone? Fine. Okay, you can take your mnemonic as well. Fine. So from actually we have AC, which is actinium. From R we have RF, which is Rutherfordium. Am I clear? Fine. From D we have DB, which is basically dubnium. Right. Then from Sharma we have SG, which is basically Siaborgium. From book, we basically take what? We basically take BH, which is bohorium. Okay. From meth, from has we take HS, which is basically hafnium. And from maths, we take MT, which is meternium. Okay. From difficult, we basically take DM, which is dramstadium. Okay, ji. From range, we basically take RG. Okay, which is rotenium, and from concept we take CN, which is coppercinium. Clear? Okay, so we have actinium, Rutherfordium, then we have dubnium, then we have Siaborgium. Okay, right, then we have bohorium, then we have your hafnium, right, meternium, Damstradium, Rotteningum, and copper senium. Clear, everyone? Perfectly clear, perfectly clear, perfectly clear. Okay, fine. Right, so one of you are saying more other mnemonics, so you can definitely take it. Now, here, let's come to the electronic configuration, guys. So now, if I talk about actinium, the atomic number is 89. And this has atomic number 104, right? 105, 106, 107, 108, 109, 108. Okay, 109, right? Fine. I think I have skipped the one, right? So it's 104, 105, 6, 7. Yeah, I have written it again now. Huh. So it should be 108, 109, 1110, 1111, and 1112. Now here, beta, I have to fill the subshell in the order NS, 2 again, N minus 2F, 2 again, N minus 1D, again 2NS. Now here, this is basically 60 series, right? This is basically 60 series, and 60 series basically lies in period n equals to 4, 7, okay? It basically lies in period number 7. Am I clear, everyone? It basically lies in period number 7. Okay, fine, cool. So here, n is basically equals to 7. So first, 7s will be filled. Then 7 minus 2f, that means 5f will be filled. Then 7 minus 1d, that is 60 is being filled. And then 7p, not s, 7p is basically being filled. Clear, everyone? Okay. Now, we have to take a noble gas of prior period. So now this is 7th period. We have to take a noble gas of 6th period, which is radon. Okay. So we are going to take radon 86 right here. Right. So first, we have to write the electronic configuration for 89. So first, 2 electrons will get into 7s. After that, next electron should enter 5f. Right? However, the same exception as lanthanum. Here, instead of 5f, the last electron enters 60 and 5f has 0 electrons, right? That is why we say that actinum is a d block element, right? Am I clear, everyone? That is why we say that actinum is what? Actinum is basically a d block element. Perfect, guys? Cool, right? Now, if I talk about Rutherfordium, now Rutherfordium comes after actinides, right? And in actinides, 5f is being progressively filled. So here you have how many? You have a total of, Bachaji, you have a total of how many? You have a total of 2 electrons right here. Cool. How many? You have a total of 2 electrons right here. Okay. Similarly, here there will be 3 electrons, right? Here there will be 4 electrons, right? And there will be no exception. There will be no exception till Damstradium, right? No exception. Here you have 5, here you have 6, here you have 7, here you have 8, right? No exception. Clear? No exception. It is a good period with less number of exception. There is no exception right here. Okay, so where does the exception lies? See, Rottenganium lying below Au, copper AgAu, then you have Rottengium, right? So it has the same thing, 7s1, 6010. Clear? And in copper cenium, no exception, beta ji. You have total of 10 electrons. That means there is only one exception, which is this, right? And actinum and lanthanum to are exceptions only, fine, right? But we always remember them, so I never make people write in them in exceptions. Clear? Right? So now if I have to write the general electronic configuration, yes, general electronic configuration. So what it will be? It will be radon, right? In 7s, you can have 1 to 2 electrons, right? And in 60, you can have 1 to 10 electrons, right? So this is basically the general electronic configuration corresponding to what? Corresponding to 6D series. Yes, 6D is pretty easy. You just have only one exception, which is Rg. No other exceptions is there. Clear? Fine. And trust me, 6D never comes in exam. Why? Because there are very less exceptions and they are radioactive. So I make you write. Why? Because NCERT have given it, but they have never asked the question. And they probably won't be asking the question. Now, let's come to general electronic configuration. So, beta, in writing the electronic configuration for D block element, which is valid to all 3D series, 4D series, 5D series and 6D series, first you have to write the inert gas. Right? That inert gas should be of prior period. Right? That means if you are writing for 3D, which is in period number 4, you have to take a noble gas of third period, which is argon. Right? First, you have to write the inert gas of whom? Of the prior period. Right? Okay. After that, you will fill your NS, which can have 0 to 2 electrons, and then N minus 1D, which can have 1 to 10 electrons. Clear? Okay. You probably can also write like this, right? You can also write it like this. Works in both the manners, right? Because here we are writing in increasing principal quantum number values. So you can write in this manner also. Clear, everyone? Okay. Chalo. Clear, akkas and annas and thambis? Okay, fine. And anise, bigger anise. Is it clear? Fine. If it is, please give a thumbs up in the chat box. So now, here, let me just sum up all the exceptions. In 3D, you have two exceptions, chromium and copper. Right? Exceptions can only be those, beta, which have either 1 electron in NS or 0. If you have 2 electrons in NS, that won't be an exception. Fine. Okay. So in 3D, only you have NS1 exceptions, which are 4s1, copper and chromium. Fine. For 4D, which has the maximum exceptions, you can learn a mnemonic NMT double RPA. NMT double RPA. Right? So N stands for niobium, then molybdenum, then technetium, then ruthenium, rhodium, palladium and Ag. Only palladium has 0 electrons, rest all of them has 1 electron in NS. Clear, everyone? Okay, fine. In 5D, we have only 2 exceptions. One is platinum and the other one is gold. Okay, so here, remembering for 3D and 5D is easy, and for 4D, I've given you a mnemonic. So these are the all exceptional electronic configurations. You should keep them in mind because from here, questions can definitely come. Okay, oh, my brother's wife is Annie. Now I am not saying anything. It is very weird. Okay, so now here, everyone. Let's come to the electronic configurations of ions. See, if they will ask us to write the electronic configuration of chromium, it's very easy. It is argon 18. Okay, argon 18, 4s2, 3d1. Clear, everyone? So now the last subshell which is being filled is third. But what is the outermost shell right here, beta? Outermost shell is N is equals to 4. When electrons are being removed and you are forming the ions, everyone, okay, then you always remove electrons from the subshell which is present in the outermost shell. That means if you have to form chromium 3 plus and you have to eliminate 3 electrons, first you have to eliminate 2 electrons from the outermost shell subshell, which is 4s. Clear? Right? Oh, by mistake I have written the wrong electronic. I have written of scandium. I'm so sorry. It is 4s1 3d5. I'm so sorry. My bad. By mistake, I've written scandium. Yes, what I was saying that in the case of chromium here, if I have to fill, first 4s is filled and then 3d is filled. However, if I have to write the electronic configuration of chromium 3 plus, I always have to remove the electron from the subshell which is present in the outermost shell. Right? Okay, fine. And that is basically whom? 4s. So first remove 1 electrons from 4s and the remaining 2 from 3d. Clear, everyone? Okay. So here the electronic configuration is argon 3d3. Clear? Is it clear to you guys? Yes. Is it clear to you guys? Any problem, anyone? Any problem, anyone? Right? Similarly, if I have to write the electronic configuration of cobalt, It is argon 3d7 4s2. However, if I have to write the electronic configuration of cobalt 2 plus, I have to remove the 2 electrons from the outermost shell subshell, which is 4s, right? So you will remove 2 electrons from 4s, clear, right? So the electronic configuration is 3d7, right? Similarly, manganese is said to have an electronic configuration of 3d5 4s2. However, if you have to form manganese 2 plus, you have to remove 2 electrons from 4s, right? So it will be 3d5. Palladium has an electronic configuration of krypton 4d10 5s0. Okay, and you have to write for palladium 2 plus. Now since 5s do not have any electron, so we have to remove it from 4d only, right? So the electronic configuration is krypton 4d8. Clear, right? So these are the electronic configurations which are given in the NCERT back. So remember always one thing, that if you want to add electrons, first you will add in 4s, then to 3d. But when you have to remove, first remove from 4s, then from 3d. Clear? Okay, fine. Now, let's come to few questions and let's see how many of you can give the correct answer for these questions. The very first question is, how many series of transition elements are present in D block? Quickly tell me, how many series of transition elements are present in D block? Quickly tell me. Yes, quickly tell me. How many? How many? Yes, quickly tell me. Very good, 4 series, right? 3D, 4D, 5D and 6D. So there are 4 series of transition elements which are present in the D block. Next beta, next. Which of the following elements belongs to second transition series, beta? For second transition series, what is the mnemonic? The mnemonic is, yes, 0, not many teachers, right? So yes, yttrium, 0, zirconium, not niobium, right? That means niobium is basically what, beta ji? Niobium is basically your element of second transition series. Okay, second transition series basically stands for 4D series. Am I clear? Fine. So if you have to write which elements belongs to 4D series, it is basically your niobium. Cool, guys? Yes, cool, fine. Okay, so now next is basically your third transition series. Third transition series is basically your 5D series. So you have to tell me which of the following element basically belongs to 5D series. Again, for 5D series, the mnemonic is Larry has, okay. So lanthanum has fun, hafnium, traveling, tantalum, world, tungsten, rich, rhenium, right? That means RE is what? Option number C. It basically belongs to which series, beta ji? It basically belongs to 5D series. Perfect, everyone? Is this thing perfect to you guys? Perfect, perfect, perfect. Okay, fine. So now let's come to the next topic, which is basically transition elements. Now you must have seen that D block elements and transition elements are used interchangeably, right? They are basically used interchangeably. Fine. Sometimes we say D block elements as transition elements and transition elements are basically called D block elements. So from where does the word transition came from? Beta, we know that the D block elements are in between S and P block elements. I have told you in the starting of the lecture. Right. Now S block elements are metals. Right. Right. And P block elements are generally non-metals. So you are transitioning from metals to non-metals by crossing D block elements, right? That is why D block elements are known as transition elements, right? Okay, therefore, beta ji, therefore, D block elements are known as transition elements. Am I clear? They are known as transition elements. Is it clear, guys? Okay, everyone, is it clear? Fine. Now, this is the general definition, but IUPAC always has to do something different as like NTA. I think they both are brother and sisters, right? So here, if I talk about the IUPAC, they have given a different definition, okay? They have given a different definition of transition elements. IUPAC says that all the elements which have incompletely or partially filled, okay, incompletely or partially filled D subshell, either in their ground state electronic configuration or most common oxidation state electronic configuration, they are basically known as transition elements, right? Now, what do you mean by partially filled? Partially filled means incompletely filled, right? Like for example, if I have manganese, right? Now, manganese has atomic number Z equals to 25. So, if I have to write the general electronic configuration, or I should say the actual electronic configuration, it is argon 4s2 3d5. Right, that means here your 3D is basically incompletely filled because 3D can maximum have 10 electrons. If it has less than 10, then it is incompletely filled or partially filled. This is the ground state electronic configuration of manganese. Am I clear? Ground state, that means the actual electronic configuration. Fine. So here I can see what? In completely filled, D subshell, right? Now it has partially filled D subshell in the ground state only, right? And when you will write the common oxidation state, which is Mn2 plus, then also it has partially filled D subshell, okay? So it should be the one case, or both can be also the case in ground state, or both in the common oxidation state, or either in one of these should be satisfied. Like either it should have partially filled in ground state or in the common oxidation state, or in both. Clear? So here in both the most common oxidation state and ground state beta, it is said to have incompletely filled D subshell. Clear? Fine. Okay. That is why we say that your manganese is a transition element. Clear? It is a transition element. Perfect, everyone. It is a transition element. Now, yes, if I talk about zinc, right? Zinc is said to have an electronic configuration of, beta ground state electronic configuration of 3d10 4s2, right? Cadmium has 4d10 5s2. Mercury has 5d10 6s2, right? And copper-cesium has 6010 7s2. So all of them have completely filled d orbital in their ground state, right? Fine. So they have completely filled, okay? They have completely filled d orbital in ground state. Clear? In ground state. Now, ma'am, if they have incompletely filled d orbital in a common oxidation state, right, then they might be transition elements in ground state, so they don't have, incompletely filled or partially filled d orbital. They have completely filled d orbital. So now let's take their common oxidation state, ma'am, of group number 12, which is basically +2, right? Which is basically +2, right? Fine. So here, zinc +2 has electronic configuration in common oxidation state. Okay, so for zinc +2, beta, you have to remove 2 electrons from 4s now. So it is 3d10. For cadmium, it is 4d10. From mercury, it is 5d10. And from copper-cesium, it is 6d10. So in the commonly occurring oxidation state also, they do not have partially filled d orbital. They have completely filled d orbital. Okay, so they have completely filled d orbital. Okay, completely filled d orbital in common oxidation state as well. So that means zinc, cadmium, mercury and copper-cesium are not transition elements, right? Okay, fine. They are basically what? They are basically pseudo transition elements. Am I clear? They are basically pseudo transition elements. Fine. They are basically pseudo transition elements. Clear, everyone? Okay, fine. So from here we got a general rule. Are zinc, cadmium, mercury and copper-selenium d block elements? Yes, because last electron enters d subshell. But are they transition element? No. Right? That means all transition elements are d block elements. But all d block elements are not transition elements. Clear? Right. So we got to understand all transition elements are d block elements, right? But all d block elements are not transition elements. Is this thing clear to you guys? If it is clear, let me ask you a question, okay? So I am giving you two statements, statement A and B. Tell me, are both correct, both incorrect, one correct and one incorrect? Quickly tell me. Quickly tell me. Yes. Is first statement correct? All transition elements are d block elements? Yes, beta. Yes, 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 yes. It is true. You guys are absolutely right. It is true. But are all d block element transition elements? Are all d block transition elements? Very good, beta ji. Very, very, very good. This is not true. Why? Because zinc, cadmium, mercury and copper selenium are your d block elements, but they are not transition elements. So this statement is false. Okay, the first statement is true and the second statement is basically false. Is it clear, everyone? The second statement is basically false. Is it clear? Right, absolutely correct. A is true, B is false. If it is clear, please give a red heart in the chat box. Yes, if it is clear, please give red heart in the chat box. Clear, everyone? Yes, clear? Absolutely correct. Absolutely correct. Now, let's just move ahead, everyone. Let's just move ahead. Now, let's take few NCERT and text question. Now, what's the beauty of this lecture? I have covered majority of NCERT questions in this lecture only. So, you don't have to go through NCERT once again and again. You just need to have one thorough reading. That's it. Okay, guys. So, this is a question, NCERT and text question, that copper has completely filled the subshell in the ground state. How can we take copper as a transition element? See, beta, if I talk about the ground state electronic configuration of copper, it is argon 4s2, or you can say 3d10 4s1. Okay, argon 3d10 4s1 is the electronic configuration, right? So in ground state, it has completely filled the orbital. Right. So let's write the common oxidation state. The common oxidation state of copper are copper plus 1 and copper plus 2. So in copper plus 1, what will happen? One electron from 4s will be discarded. Right. Still, 3d has 10 electrons right here. Am I clear, everyone? Still, 3d has how many? 10 electrons right here. Fine. However, in copper 2 plus, I can see 3d has 9 electrons. That means in its common oxidation state of plus 2, copper is said to have partially filled d orbital. Clear? It is said to have partially filled d subshell. That is why copper is a transition element. Am I clear? Copper is a transition element. Any doubt, anyone? Yes. Any doubt, anyone? Not any doubt? Yes. Not any doubt? Cool. Okay. Now, let's just move ahead to the next question. The next question is, on what grounds we can say scandium is a transition element but zinc is not? See, beta, in the case of scandium, whose atomic number is 21, when you will write the ground state electronic configuration, which is basically argon 4s2 3d1. This is the ground state electronic configuration, and the most common oxidation state of scandium is basically plus 3. right? So in plus 3, it is said to have an electronic configuration of argon only. So in plus 3, which is the most common oxidation state, I will tell you why plus 3 is the most common oxidation state ahead in this lecture. Don't worry about it. Now, try to understand the fact that in plus 3, you do not have any electron in 3D. However, in ground state electronic configuration, it has one electron in 3D. That is why it is a transition elements. However, if I talk about zinc, I've already explained you guys, right? Whether you take the ground state of zinc, right? Whether you take the ground state of zinc or you take the common oxidation state, guys, right? Fine, cool. Here in the common oxidation state also 3D is completely filled, okay, right? Fine. So in scandium in ground state 3D is partially filled. However, in zinc, both in ground state as well as in common oxidation state, 3D is fully filled. Clear? That is why zinc is not transition element, whereas scandium is. Clear, everyone? Okay, fine. So now, why I have done this question? Because once in Karnataka CET, see Karnataka CET 2013, right? Fine. Okay, there came this question directly from NCERT. The question is, scandium is a transition element, but zinc is not. So what should be the answer? A, B, C, D. Quickly tell me in the chat box. What should be the answer? Very good, people. Very good, very good, very good. Anas and Akaz. Very good, guys. Very good. Here, scandium has partially filled d orbitals, whereas zinc has what? Completely filled d orbital. That is why I'm doing the in-text question, guys, because you can see directly from in-text questions, so many times the questions are coming. Clear? Okay, fine. Now, let's come to the next question. Which of the following D block elements are D block elements but not transition elements? We know that zinc, cadmium, mercury are not the transition elements, right? So, answer is pretty clear. Option number B. Cool, guys? Fine. Okay. Now, so we are done with electronic configuration as well as what are transition elements. So now we are beginning the second part of today's marathon, which is the longest one. This is basically general properties of transition elements or D block elements. Okay. So the very first property is that all transition elements or D block elements are basically what? They are said to have metallic character. Now, what do you mean by metallic character? Metallic character means that D block elements display the properties which are typical properties of metal, right? Now, what are the typical properties of metal? They are ductile, they are malleable, they are lustrous, they are sonorous, okay? They have high tensile strength, they have high thermal and electrical conductivity. Am I clear, everyone? Fine. So, all those typical properties which a metal exhibit, all the D block elements are said to exhibit them. That is why we say that the D block elements are said to exhibit what? They are said to exhibit metallic character. Clear, everyone? Fine. Okay, so that means they are said to have high tensile strength. What is high tensile strength, beta? Tensile strength means resistance against force or tension. That means when you hit them, they don't broke up into pieces, right? Fine. So high tensile strength means high resistance towards force or tension. Force, tension and force are one and the same thing only, right? In chemistry. Don't know about physics, okay? So don't judge me right here. Am I clear, everyone? Fine. Okay. So you are my elder brother and sister, yeah? You guys are pretty advanced than me. No problem. So high resistance towards tension and force, okay? Towards tension and force. Clear, everyone? They are ductile. Now, what do you mean by ductile? Ductile means they can be drawn into thin wires, right? They can be drawn into thin wires. They are malleable. Malleable means they can be subdivided into thin sheets, okay? You can form thin sheets, like you can form thin sheets of gold, copper, right? So they are said to be what? They are basically said to be malleable. Am I clear, everyone? Fine. Now, Ahead in this lecture, I will tell you about metallic bonding. Like ionic compounds are said to exhibit ionic bond, right? Metals are said to exhibit metallic bonding, right? And D block elements or the transition cell elements are said to have strong metallic bond, right? Due to this strong metallic bond, they are said to exhibit what? High melting point and boiling point. Is it clear, everyone? Yes, is it clear? Right. So why high boiling point and melting point? Due to strong metallic bonding. Am I clear? Due to strong metallic bonding. Is it clear? Due to strong metallic bonding. Fine. Okay. Now, when you will study the metallic bond, you will see that transition elements have positively charged ions as well as electrons in their crystal lattice. Right. Now, due to presence, I will tell you ahead in this lecture, don't worry. Now, you just listen to me, you will understand that later on. Now, due to presence of this delocalized electron, delocalized means the electrons which can move here and there. Right. Charge carriers are present in transition elements crystals. Right. Fine. Now, when charge carriers are present and you will give current, that charge carriers will flow current from one end to the another end. Right. So why they have high thermal conductivity and electrical conductivity? Thermal means conductance of heat. Electrical means conductance for electricity. Why they have so beta? Due to presence of, due to presence of my dear students, delocalized electrons. Okay, due to presence of delocalized electrons. Further, they have metallic luster. Metallic luster means something which is shiny. Okay, right. So lustrous means they are said to have shiny appearance, and sonorous means when you hit them with hammer tongue, they produces a sound. Okay, everyone. So they produces a sound when you hit them with a rod, or you can take hammer, right? And give that hammer to my head also. Fine, if you're not able to understand this simple thing. To my head also and to your head also, right? Okay, kidding, everyone. Extremely kidding. Fine, no offense, just kidding. Okay, fine. Chaliye. So let's just move ahead. So we have done the very first thing, the very first property. Let me have a sip of water and then we will start with the second thing. Clear? Okay. Now, here, first thing is done. Why they are said to have typical metallic character? This thing is done. Fine. This thing is done. Done. Now, here, beta, all the D block elements, they are said to have the typical metallic structures. If you are a dropper, 1 year or a 2-year dropper, you guys have studied solid state. Right. In solid state, we see that metal is said to have crystal lattice or structure as BCC, which is body center cubic, FCC, which is face center cubic, CCP, which is cubic close packing, or HCP, which is hexagonal close packing. If you remember, it's okay. If you know, it's okay. If you don't know, doesn't matter. These are the typical metallic structures, right, which the metals basically possess. Okay, fine. If you know, it's okay. If you don't know, then also it's okay. Now, all of the D block elements or the transition elements possess these typical metallic structure. However, there are 4 elements, okay, which are zinc, cadmium, mercury, and manganese. Right? Fine. They do not exhibit beta G, typical metallic structure. Okay, do not exhibits these. Right? Fine. They do not exhibit typical metallic structure. Now, they can definitely ask you which of the following elements do not exhibit the typical metallic structure. You will close your eyes and say, ma'am, zinc, cadmium, mercury, and manganese. There are 4 which do not. It is an experimentally observed thing, beta G. Clear, everyone? Fine. Now, let's just move ahead to the next thing. Now, we have to understand beta G, atomic radius, as well as ionization energy. So we will be needing a little bit help of shielding effect and screening effect. Okay, so let's just revise quickly effective nuclear charge, shielding effect, and screening effect. Fine. Okay, see, if you have an atom right here of any element, right, this is basically the nucleus. This is basically the outermost shell, which is said to have outermost electron. And this is one shell prior to the outermost shell. Now, this nucleus can do two things, beta ji. Right, this nucleus can do one thing right here, beta ji. What is the one thing? That since nucleus is positively charged, so it can apply what? It can apply forces of attraction towards the outermost shell electrons. Why? Because they are negatively charged. Am I clear, everyone? Why they are negatively charged? Is it clear, everyone? Fine. Okay. Nucleus, since it is positively charged, so it can apply forces of attraction towards the outermost shell electrons. Right. Now, what are these forces of attraction will be equal to? See, nucleus is said to have protons. Right. Number of protons are equals to Z. Right. Fine. And each proton is said to have a unipositive charge. So, if we have 10 protons, what will be the positive charge? 10 plus, because every proton has 1 unit positive charge. If you have 15 protons in the nucleus, what is a nuclear charge which the nucleus will be applying to the outermost shell? 10 plus. If you have 16 protons, 16 plus. 17 protons, 17 plus. Agreed, everyone? Agreed or not? If agreed, please give a thumbs up in the chat box. If you agreed, please give a thumbs up in the chat box. Yes, clear or not? Clear, everyone? Clear or not? Clear? Fine. Okay. Yes. Okay. So now, here, if there would not have been intervening shell or this shell in between the nucleus and the outermost shell, then the charge equals to the total number of proton is the measure of forces of attraction, or I should say the nuclear charge, which nucleus will be applying to the outermost shell electrons. Right? However, if you have a shell between the outermost shell and the nucleus, which is said to consist of electrons. Now, these electrons will apply what? These electrons, bacha, will apply forces of repulsion. Am I clear? These electrons will apply what? These electrons will apply forces of repulsion. Clear, everyone? Fine. So, these electrons will apply forces of repulsion. Clear? And due to this repulsion, right, the total attraction which the outermost shell electrons should have experienced basically gets reduces. Is it clear? It basically gets reduces. Clear or not, everyone? Perfectly clear, right? It basically gets reduces. Fine. Okay. Fine. Now, here, if this intervening shell would not have present, then what is the attraction or what is the nuclear charge which the nucleus would have applied to the outermost shell electrons? Beta, it is equals to Z. Clear? It is equals to Z. And what is Z right here, beta G? Z is equals to number of protons. Am I clear, everyone? It is basically equals to number of protons. But due to repulsion caused by the inner shell electron, the net forces of attraction or the net nuclear charge which the outermost shell electrons are experiencing is somewhat reduced. And since it is reduced, it is less than Z. Right, and they are less than Z by a factor equal to sigma. Clear? Right. Now, what is this sigma? Sigma is basically shielding constant or screening constant. Right. It is basically shielding constant, or you can say screening constant. Clear? Shielding constant or screening constant. Fine. Now, this is basically measure of shielding. More is the shielding caused by inner shell electron to the outermost shell electrons, more will be the sigma. It is Slater constant. I have taught how to calculate sigma in the prior lecture, which is periodic classification. If you want to learn, you can definitely watch that lecture out. Clear, guys? Fine. Now here, there occurs a reduction in the nuclear charge from Z by a factor sigma, and now the nuclear charge becomes Z effective. Now, what is this Z effective? Z effective is basically the effective nuclear charge or the reduced nuclear charge which now the outermost shell electrons is basically experiencing. Is it clear, everyone? Is it clear, everyone? Fine. Okay. Fine. So now, here, what is happening that there occurs a reduction in the forces of attraction due to repulsion of the inner shell electron, right? Or there is a reduction in the nuclear charge due to repulsion caused by inner shell electrons. And this is basically known as what? This is basically known as your shielding effect or screening effect, right? This is basically known as shielding effect or screening effect. Fine. Okay, so what is shielding effect? Reduction in the forces of attraction experienced by the outermost shell electrons due to repulsion caused by the inner shell electrons. Or shielding effect is decreased in the nuclear charge experienced by the outermost shell electrons due to repulsion caused by the inner shell electrons, right? Sigma is basically the measure of the repulsion or the screening which the inner shell electron is causing. Z is basically equals to number of protons, and Z effective is the effective nuclear charge. Clear, everyone? Fine, I have taught you in periodic classification. Now, more is the shielding, more is the repulsion, more is the sigma, right? Fine. And if sigma increases, beta G, then this factor increases and Z effective will get what? It will get decreases, right? So we can say right here that Z effective is basically inversely proportional to shielding effect or sigma. Clear? More is the shielding, more is the screening, lesser is the Z effective. Fine, everyone? Okay. Now, if you are taking, suppose, subshells of inner shell. Okay, this is your nucleus. This is your inner shell and this is your outer shell. Now this inner shell can have many subshells, right? Okay, suppose the outer shell is n is equals to 4. So inner shell, n is equals to 5. So inner shell is n is equals to 4. Now for a given value of principal quantum number, say n is equals to 4, right? Right, you can have which subshell? You can have 4s, you can have 4p, you can have 4d and you can have 4f, beta G. If I talk about s, right? If S is present, is this inner shell, 4s. Now 4s will shield the outermost shell electron more. Why? Because it is spherical. Think of it. If in my front I have the nucleus, I am 4s. I am lying before the outermost subshell. Now 4s is spherical. So from all the rounds I will shield the outermost shell electron from the nucleus. However, if I am 4p, then there will be spaces above and below from where the nucleus, can apply attraction to the outermost shell electron. So 4p won't have that good shielding. Clear? Okay. So if I have n is equals to 4 and I have to compare order of shielding. Okay. Order of shielding. Clear? Right. So 4s will do better shielding than 4p. 4p will do better shielding with 4d and 4d will do better shielding than 4f. Is it clear, everyone? Am I clear? Okay, fine. So for same value of n, shielding of s is more than p, p is more than d and d is more than f. Okay, this is the order of shielding. This is the order of shielding. Now you only tell me, from here, can we conclude that your D and F has poor shielding? Yes, D and F subshell has what? D and F subshell has poor shielding. Am I clear? They are said to have what? They are said to have poor shielding. Is it clear, guys? Is it clear? If it is clear, please give a thumbs up in the chat box. If it is clear, please give a thumbs up in the chat box. Quickly. Yes, quickly. Fine, now I will use all of these things ahead, right, in ionization energies as well as in atomic size. Fine, so that is why I've explained it ahead. So now, let's come to the second property. First was metallic character. Yes, first was metallic character. Second property is atomic radius. Right, second property is what? Second property is basically atomic radius, or you can say atomic size. Clear? Now, if I talk about the D block elements, they lie in between of S block and P block elements. Right, that means first we have S block elements, then we have our P block elements, and then we have our D block elements. Am I clear, everyone? This is the order in which the elements are present. Agreed, everyone? Agreed, agreed, agreed? Yes, ma'am, agreed. Okay, so as we move from S to P to D, that means left to right in a period, effective nuclear charge increases. And we have studied in periodic classification, if effective nuclear charge increases, okay, the attraction between the nucleus and the outermost shell increases, right? And the distance between nucleus and the outermost shell decreases, which is the atomic radius. That means your atomic size or atomic radius is inversely proportional to Z effective. And as we move left to right from S block to P block to D block, Z effective is getting increased. Right now, since the Z effective is getting increased, my dear lovely students, here atomic size decreases. That means S block elements have larger size than D block elements, and D block elements have larger size than P block elements. Why? Because from left to right, that means from S to D to P block, okay, from S to D to P block, what is happening, everyone? Z effective is getting increases. Right, fine. So since Z effective increases, atomic size decreases. This is a general thing. Fine, okay. Now, here we have to study the variation of atomic size and atomic radius in periods, specially for 3D series. Especially for 3D series, we have to. Okay, so I am studying it along 3D series or along period, the variation. Okay, the variation of atomic size. Now, if I talk about 3D series, guys, it basically consists of scandium, titanium, vanadium, chromium, manganese, Sakti V Karman, Piconi, Kojan. Okay, Piconi, Kojan. Now, in order to understand the variation of size, guys, we need to write the electronic configurations. Okay, so what is the electronic configuration, Raji? In the case of scandium, the electronic configuration is 3D1 4s2. Okay, in the case of titanium, it is 3D2 4s2. Vanadium 3D3 4s2. Chromium 3D5 4s1. Manganese 3D5 4s2. Fe 3D6 4s2. Copper 3D7 4s2. Nickel 3D8 4s2. Copper 3D9 4s1. And zinc 3D10 4s2. Now beta, when you move left to right in a period, or when you move left to right in 3D series, what happens? Z effective increases, right? Z effective increases. Yes, ma'am, left to right Z effective increases. At the same time, beta, outermost shell, subshell is 4s. Inner shell, which cause shielding, is 3D. Right? N is equals to 3 is the inner subshell, and it is said to have 3D. And number of electrons in 3D are getting increased. Now, when number of electrons in 3D get increased, sigma increases. Sigma increases means your shielding, screening also increases. That means left to right, Z effective also increases, and sigma, shielding, also gets increases. So that means there is a competition between the two, right? That means there is a competition between the two, right? Fine. Now first, what happens is right here, my dear students, that first till manganese, the winner is Z effective, right? Because the number of electrons in 3D are less. So sigma is comparatively less. Although it is increasing, but comparatively less. That means here, till scandium to manganese, right? The winner is whom? Z effective. Z effective increases more than sigma. Okay. In Fe, cobalt and nickel, there is a draw. That means here, Z effective is equivalent to sigma, nearly equivalent to sigma. And in the case of copper and zinc, you can see 3D has 9 and 10 electrons. That means there is lot many electrons in the inner shell, right? So sigma increases right here more than Z effective. Clear? Fine. So here in the case of zinc and copper, what will happen, my dear students? Here sigma will be more than Z effective. Is it clear, guys? Yes. Is it clear, guys? Agreed or not? Perfectly clear? Yes. Perfectly clear. Okay, fine. Now, if I have to give the order of size in 3D elements, okay. So, if I have to give the order of atomic radius or atomic size, order of atomic radius or size, okay. Order of atomic radius, guys. So, here, since from scandium to manganese, Z effective is increasing. So, more is a Z effective, lesser is the atomic radius. Okay, so that means from scandium to manganese, what is happening? Yes, what is happening, everyone? Atomic radius is getting decreased. That means scandium has more atomic radius than titanium. Titanium has more than vanadium. Vanadium is more than chromium, and chromium has more than manganese. Is it clear, everyone? Fine. Now, when it comes the case of Fe, cobalt and nickel, since Z effective is counterbalancing the sigma, right? It is counterbalancing the sigma, everyone. Fine. So what happens is the size of Fe is nearly equal to cobalt and cobalt is nearly equal to nickel. Now in the case of copper and zinc, sigma increases. If sigma increases, beta, sigma and Z effective are inversely proportional. Z effective decreases. And if Z effective decreases, atomic radius or atomic size increases. Right? Okay. So copper has more size than nickel and zinc has more size than copper. So this is the overall order. If you want to see, you can match it from the graph which is given in the NCERT. This is scandium. From scandium to titanium to vanadium to chromium to manganese. Radius decreases, right? Then in the case of Fe, cobalt and nickel, it is almost equal. Then this is copper, it has more than nickel. This is nickel and this is copper. And the last one is zinc, right? So if you will look at the graph, you will get to understand that although at the end, the atomic radius of zinc is getting increased right here. Is it clear, everyone? Fine. Okay. Here, what is happening, everyone? Here, the atomic radius of zinc is basically getting increased. Fine. However, still, zinc have lesser radius than scandium. Okay, so if they ask you to compare, beta, scandium has a higher radius than zinc. You need to keep this thing in your mind. Okay, it has higher radius than zinc. You need to keep this thing in your mind. Am I clear, everyone? Am I clear, everyone? Fine. Now, here, when you will look this particular trend, in this trend, can we see that copper is said to have a higher radius or size than manganese? As well as in this, not copper, chromium. I'm so sorry, not copper, chromium. So when you will see this order, you will get to see that chromium is said to have more size in comparison to what manganese. At the same time, when you look at this graph, in the graph, you can easily see that chromium has a higher atomic size or radius than manganese. Right. However, when you will open this particular table in NCERT, right? Now, as per the graph and as per the order, chromium has higher than manganese. However, when you will open this graph or this data which is given in the NCERT, you will see that your chromium is said to have radius 129 and manganese is said to have radius 137 picometer. That means manganese has more than chromium. Now, why such anomaly in the data? Why such anomaly in the data? People keep on asking. So the answer is, beta, here the graph which they have given is basically of atomic radius. Now atomic radius could be covalent radius. Clear? This graph and this order is basically corresponding to atomic radius which could be covalent radius. However, the data which is given right here is for ionic or metallic radius. So when they ask you the order of ionic and metallic radius, beta, manganese has higher than chromium. However, if they just ask you atomic radius or covalent radius, then chromium has higher than manganese. This you need to learn. Beta, this is data. This is data. If you will finding the size and the size comes out to be anomalous, so this is data, na? Right? Everything is exceptional right here. Fine, everything is exceptional right here. So it's a data. There is no logic for it. If you will ask me for any explanation, I'll give it. But that is false. The NCRT has also been made from data. Am I clear, everyone? Okay, Elara, focus. Fine. So here, I think this thing should be clear to you guys. So if they will ask you only atomic radius, chromium has more than manganese, and metallic or ionic, then manganese has more than chromium. It's exceptional. Fine, everyone? Okay, fine. So you basically have to remember this only, beta. But you just need to remember one thing, that in the case of metallic, manganese has more than chromium. Nothing else you need to remember. Clear, everyone? Fine. So here we have completed the variation along 3D series or along the period. Is this thing is clear, Beta ji? Is this thing? If yes, please give red hearts in the chat box. If it is clear, please give red hearts in the chat box. It will boost my morale. Okay. Already by seeing students less than 89, I'm little bit disappointed, but I will give my 100% only to these 89 students also, so that next time we have 189 live watching. Clear? Fine. And soon let's take it to 1089. Fine, everyone. Now let's just come to the variation. Okay, let's just come to the variation, right, along the variation along the beta G group. Okay, now let's see variation along the group. Beta, we know that as we move top to bottom, okay, we know that as we move top to bottom in a group, I have told you in the periodic classification that number of shells increases. And if number of shells increases, atomic radius or atomic size increases, right? That means atomic radius or atomic size, right? Atomic radius or atomic size is directly proportional. Am I clear? It is directly proportional to number of shells. Am I clear? It's directly proportional to number of shells. Is it clear, everyone? It is directly proportional to number of shells. Perfect, right? So if top to bottom, we are moving from 3D series to 4D series to 5D series, right? Top to bottom in a group, then size should have increased. Right, and that happens also as we move from scandium to yttrium to lanthanum, atomic size or atomic radius increases. Clear, guys? Okay, that means if you are taking group 3, right, and as we move from 3D to 4D to 5D series, atomic size, atomic radius increases. That means yttrium has more than scandium and lanthanum has more than yttrium. Is it clear, everyone? Is it clear or not? Clear, 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 clear. Okay, fine. However, when it comes to your group number 4, which is titanium, zirconium and hafnium, and so on, right? So on till group number 12. Okay, when you move from group number 4 to group number 12, what happens is, here 4D has a higher size than 3D, but 4D and 5D element size is similar. Similarly, here also, similarly, here also, similarly, till zinc, same thing is happening. Right? Okay, fine. That means what is happening from group number, what is happening from group number 4 to 12? 4D has more size than 3D, and 4D and 5D are said to have similar size. That means titanium has lesser size than zirconium. However, zirconium and hafnium, this is zirconium, this is hafnium, they both are said to have similar size. Now, what is the reason for that? What is the reason for that? I will give you the break at 8:30. once I will complete the ionization energy, then I will give you the break. So most probability 8:30 or 9, I will give you half an hour break. Okay, I'll also have my dinner. You also have your dinner. Fine, till that, please no breaks, okay? Now, here, why does this happening, yaar? The reason is after group 3 or after lanthanum, am I clear? After your group number 3 or after lanthanum, we have 14 lanthanides. Okay, we have 14 lanthanides. Starting from cerium 58 to lutetium 71, in which 4F is progressively filled. Am I clear? In which 4F is progressively filled. Am I clear, everyone? Fine. And when 4F is being filled, guys, right? Okay. So in lanthanides, what is happening? In lanthanides, what is happening? In lanthanides, guys, what is happening? Here, 4F is being filled, right? 4F is being filled. Clear? Right. And when 4F is being filled, beta ji, 4F is said to have poor shielding. Right? 4F is said to have poor shielding. And when 4F is said to have poor shielding, that means sigma is less. Right? Then effective nuclear charge or Z effective increases. Clear, everyone? And when Z effective increases, atomic size decreases. So atomic size of 5D decreases to a level that it becomes equivalent to 4D. Is it clear? So atomic size of 5D decreases to a level that it becomes equivalent to 4D. Why? Because hafnium beta G, before hafnium, 4F has been filled, which has poor shielding. So Z effective increases, size decreases. So size of hafnium decreases to a level that it becomes equivalent to zirconium. And same happens with all the elements starting from group 4 to group 12. So if they ask you, what is the order of size, okay, say of copper, Ag and Au. Beta, copper has lesser size than Ag and Ag has similar size to Au. Right? So this is applicable to all the groups. Is it clear, everyone? If it is clear, please give a red heart. Okay. Now, you can see this graph which is made in the NCERT, guys. This lower graph is of 3D series. Upper is of 4D. And this is of 5D. So you can see that the atomic size of 4D and 5D are nearly equal. Why? Because these points are nearly merging with one another. Okay. Right. Fine. Cool, everyone? Cool. So you can see from the graph as well. You can see from the graph as well. Fine. Chalo, let's move ahead. Let's do some questions. So the very first question is atomic radius of Ag is closest to, just told you, copper Ag Au, right? In 3D series, in group number 11, we have copper. Right? Fine, you can clearly see we have in group number 11 copper. Below copper we have Ag and below Ag we have Au. Right, everyone? Ag have more size than copper, but Ag and Au have nearly equal size. Yes or no, everyone? Yes, that means Ag has atomic radius similar to that of whom? It is similar to that of Au. Perfect, guys. Perfect. Text. This has been asked in AIPMT 2010. Which of the following pairs has same size? Beta, we know that zirconium and hafnium, they both are said to have same size, right? So why? Due to lanthanoid contraction. Fine, this is basically lanthanoid contraction only, right? Whenever due to poor shielding, Z effective increases, na beta. This is lanthanoid contraction only. Clear? So reduction in atomic size due to increase in Z effective due to poor shielding is lanthanide contraction, mera beta. Okay, this is lanthanide contraction. So due to lanthanide contraction, contraction means reduction in size. Clear? So due to lanthanide contraction, the size of zirconium and hafnium nearly becomes what? Nearly becomes similar. Am I clear, everyone? Fine. Chalo. Let's move to the next property, which is property number 3. This is basically your melting point. Okay. This is basically your melting point. Fine. So what is the melting point, beta? Transition metals are solid, right? So if you have to convert a transition metal from solid to its liquid state, right? So at a temperature at which this transition is occurring, right? The temperature at which this transition is occurring, that is, metal is converting from solid state to liquid state, that temperature is basically known as melting point. Am I clear? This temperature is basically known as what? This is basically known as melting point, right? Now, transition metals, as I have told you earlier also, are said to have metallic bond. Now, stronger is a metallic bond which is present between the metal ions, right, and their electrons. The more amount of heat or energy has to be given, or the more amount of temperature has been given to the metal which is present in the solid state, so that its ion can move apart, and from solid it can convert into the liquid state, right? That means temperature is higher, which is has to be given. So that means what? The melting point will also be higher. Yes, the melting point will also be higher. Agreed, everyone? Fine. That means stronger the metallic bonding, more is the heat or the energy which is required to give it this strong metallic bond and to convert a metal from a solid state to liquid state, and higher will be the melting point. So from here, what is the conclusion? That more is the strength of metallic bonding, more will be the melting point. Okay. So from here we can say conclusion is that that melting point, okay, melting point is directly proportional to the strength of metallic bonding. Am I clear? It is directly proportional to what? Strength of metallic bonding. Am I clear? It is directly proportional to the strength of metallic bonding. Ma'am, what is this metallic bonding? Yeah, you are saying it from so much time, metallic bonding, metallic bonding. What is this metallic bonding? See, beta, in the case of transition metals, since they are metals, है ना, metals are said to have low ionization energy. So if the ionization energy is low, it is very easier for them to lose the electrons, right? So metal can, when present in their gaseous state, beta, or in the solid state, can move or can lose n electrons and form Mn plus cation, right? Now this Mn plus is said to be what? It is said to be the positively charged ion. This is your positively charged ion. And what is this? This is basically your delocalized electrons. Am I clear? These are what, guys? These are basically your delocalized electrons. Okay. So these are your delocalized electrons. Am I clear, everyone? So if you have a crystal lattice of any metal, you have lot many positively charged ions, right? Now these positively charged ions are basically known as kernels. Okay, they are basically known as kernels, right? So you will have a lot of kernels present in the metal lattice, as well as you have delocalized electrons, right? So this yellow positively charged ions, which you can see right here, are your kernels, and this pink one are your delocalized electron. Clear? Okay. So now the forces of attraction between the electron, which is negatively charged, and the kernel, which is positively charged, is the metallic bonding. Am I clear? Right. Okay. So the forces of attraction, right? The forces of attraction between the kernels and the delocalized. Delocalized means electrons moving from here and there, okay? So the forces of attraction between the kernels and the delocalized electron is basically known as metallic bonding. Clear, everyone? Any problem, anyone? Yes. Any problem, anyone? Fine. Okay. Now you tell me one thing. If these delocalized electrons will be more, right? These delocalized electrons are basically the unpaired electrons, beta, right? These are basically the last electron or the unpaired electron, mostly the unpaired electron, which is present, right, in the ground state electronic configuration of any metal, right? So more are these delocalized electrons or these unpaired electrons, don't you think more will be the metallic bondings happening in the crystal of the metal, or we can say more is the strength of metallic bonding? Agreed, everyone? Agreed. So what we can say right here? What we can say right here? We can say that strength of metallic bonding. Yes, strength of metallic bonding. Clear? Strength of metallic bonding is directly proportional to number of unpaired electrons. Okay, it is directly proportional to what? It is directly proportional to number of unpaired electrons. Am I clear? Okay, so what should be the final conclusion? Yes, what should be the final conclusion? Final conclusion is basically, my dear students, that more are the number of unpaired electrons, more is the strength of metallic bonding, and more is the strength of metallic bonding, more is the melting point of transition elements, right? Okay, so more are the unpaired electrons, more is the strength of metallic bonding, and more is the strength of metallic bonding, more is the melting point of whom, beta ji? Of the transition elements. Is it clear, everyone? Fine. Okay, cool. So now let's just come to the final melting point variation in D block, right? Now here, first thing written in the NCERT regarding the melting point of D block elements or the transition elements is that your D block elements are said to possess high melting point, right? All the D block elements, they are said to possess high melting point. So what could be the reason for that, beta? When you will write the electronic configuration of D block elements, what you will see? You will see there are large number of unpaired electron in N-1D subshell and NS subshell. Agreed. Fine. And all these unpaired electrons will be involved in what? Metallic bonding, right? So that means strength of metallic bonding increases right here. So if strength of metallic bond increases, then melting point also increases. That means due to involvement of large number of unpaired electrons which are present in NS subshell and N-1D subshell, the strength of metallic bonding is more, and due to which melting point of transition element and D block elements is also said to be more. Clear, everyone? Perfectly clear? Yes, perfectly clear. Okay, fine, cool. Chalo, that's great. Now, let's see the variation of melting point in 3D series. Okay, now let's see the variation of melting point in 3D series. Clear? Okay, so if I talk about 3D series, beta, you are along the period. Hai na? 3D series means as we move along the period, what is the variation? So see, in 3D series, we have scandium, titanium, okay, vanadium, then chromium. Right. The electronic configuration of scandium, everyone, is basically 3D1 4s2, right? And that of chromium is basically 3D5 4s1. Clear? That means as we move from scandium to chromium, what is happening? Are the number of unpaired electrons increasing? In fact, chromium is said to have the maximum number of unpaired electrons, everyone. Clear, everyone? Here, scandium is said to have, chromium is said to have the maximum number of unpaired electrons in the 3D, guys. Clear? It is said to have what? It is said to have the maximum number of unpaired electrons. Where? In 3D. Okay, right? Okay, it has a total of 5 plus 1, 6 unpaired electrons. Okay, so from scandium to chromium, number of unpaired electrons increases. Now, if the number of unpaired electrons increases, guys, what will happen? What will happen? The strength of metallic bonding increases. And if the strength of metallic bonding basically increases, my dear students, what will happen? The melting point also increases. Clear? Now, once you come from chromium to manganese, suddenly pairing occurs. Okay, suddenly, right? Suddenly pairing occurs. And this sudden pairing basically results into the reduction of melting point of the manganese, right? It becomes way too less than chromium. Some people explain it in this manner. Some people say that it has 5 electron in 3D, which is completely half filled, and 4s, which is completely filled. So it is a stable electronic configuration. Okay, people say that's why there occurs reduction in the melting point as moving from chromium to manganese beta, because they say that it is said to have a stable electronic configuration. Okay, it is said to have a stable electronic configuration. Fine. And if it is said to have a stable electronic configuration, beta G, the one which is said to have a stable electronic configuration generally forms very weak metallic bonding. Clear? Right. So therefore, it is said to have weak metallic bonding. Why? Because it has stable configuration. It does not want to get involved in metallic bonding. Fine. So it has weak metallic bonding. Right? That is why the melting point decreases from chromium to manganese. Now, as we move to Fe, the Fe is said to have higher melting point than manganese, that for sure. In manganese, we observe a dip basically, right? Now, Fe is said to have a configuration of 3d6, 4s2. So that means that Fe pairing has started, beta. Look at it. If you have 6 electrons, so what will happen? Pairing will start. Now, as we move from Fe to cobalt, cobalt has 3d7, so one more pair is coming right here. And when you will move to zinc, all the electrons will get paired, right? That means as we move from Fe to zinc, beta G, Fe to zinc, what is happening? What is happening? Here, number of unpaired electron decreases. Right? Now, since the number of unpaired electrons decreases, the strength of metallic bond also get decreases, guys. Clear? Okay, fine. And that is why melting point also decreases right here. Is it clear for guys? Right. Now, while seeing the data, we can easily say that chromium is said to have highest number of unpaired electrons in 3D series. That is why chromium has highest melting point. Okay, it has highest melting point in 3D series. Am I clear? In 3D series. Clear, guys? Perfectly clear or not? Clear? Okay, fine. Let's just move ahead. Okay, let's just move ahead. Now, this is a graph drawn in NCERT. The blue line corresponds to 3D series. The light blue line or the light green line corresponds to 4D series, and the pink line basically corresponds to 5D series. So as we move from 3D to 4D to 5D series, what we will observe right here, guys, what we will observe right here, you can see the graph also, that what should be the general trend, huh? What should be the general trend of melting point? By seeing this graph, what you will get to understand here? We'll get to understand that 5D series elements have more melting point than 4D, and 4D has more than 3D. Right? This is a general thing which we can see, right? Because melting point of 5D is definitely higher than 4D, and 4D is definitely higher than 3D, although exceptions are there. But this is a general trend. Clear, everyone? Okay. Now, below manganese in 4D series, we have technetium. So, as in manganese, we have obtained a dip, right? From titanium to vanadium to chromium, increase. Then from manganese, dip. Then again increases. Fine to Fe and then decreases, right? This is the thing which is happening. So, in the case of manganese, we have a dip. Similarly, in 4D, below manganese, right, we basically have technetium. In technetium also we have a dip, and below technetium we have Re. But in Re, which is lying in the 5D series, we are not seeing any dip right here. Clear? So the examiner may ask you that in the graph of melting point versus atomic number, in which two elements are we seeing the dip? So the answer to that is, my dear students, in manganese and technetium. Right? Dip is observed. Dip is observed in graph of 3D series and 4D series and 4D series. Am I clear, everyone? And now, by seeing the entire graph, tell me the elements which is said to have the highest melting point. See, beta. So peak corresponding to the one which are said to have highest. I've already told you chromium is said to have highest in 3D. Below chromium, I have molybdenum. So molybdenum have highest in 4D. And below molybdenum, I have tungsten. Right? Fine. And tungsten have highest melting point in 5D. Okay. So by seeing the graph, I can clearly see, right, that tungsten is said to have the highest melting point in D block elements. Am I clear? Which element is said to have the maximum melting point, beta ji? Tungsten. Clear? And that is the reason tungsten is basically used to make bulb is a filament, because in bulb the temperature is very high. So the filament, they make it of tungsten. It has a very high melting point, so it doesn't melt. Right? Okay. Therefore, it is used to make bulbs filament. Okay. To make bulbs filament. Am I clear, everyone? That is why it is basically used to make bulb filament. Cool? Fine? Clear, everyone? Next, they may ask, which element in 3D has highest melting point? You will say chromium. Okay. So chromium has highest melting point in 3D. Clear? It has highest melting point in 3D. Now, above chromium, you have molybdenum. Molybdenum has highest melting point in 4D. Clear? And above molybdenum, above chromium, you have molybdenum, and above molybdenum, you have tungsten. It has highest melting point. It has highest melting point in 5D. Am I clear? In fact, tungsten has the highest melting point in among all the transition elements, right? Among all the D block elements, it is said to have the highest melting point. Now, if I have to see the general trends of melting point along a group, so general trend by seeing this graph seems to be what? What is the general trend of melting point? Yes. Quickly tell me, what is the general trend which we observe? General trend which we observe for the melting point beta. General trend is basically that 4D has more than 3D and 5D has more than your 4D. Now this is general trend. Okay, this is basically your general trend. And if I talk about all the groups, 10 groups of D block elements, this general trend is obeyed only from group 4 to group 10. Am I clear? Only and only from group 4 to group 10, the order is that 4D has more melting point than 3D, right? And 5D has more than 4D, right? Okay, am I clear, everyone? This is only and only observed in the case of 4 to 10th. Clear? 4 to 10th. Fine. Like for example, if you will pick up, say, of fourth group, titanium, zirconium and hafnium. So the order will be what? Yes, you have titanium, zirconium and hafnium. So what will happen? The melting point increases top to bottom effortlessly. Clear? However, the exception exists in third group, 12th group and 11th group. What happens in the third group, guys? It is reverse to this. Reverse to this means 3D has more than 4D and 4D has more than 5D. Am I clear? Like for example, if you have group 3, so group 3 basically consists of scandium, okay, yttrium and lanthanum. So top to bottom melting point decreases. Clear everyone? Fine. Okay. Clear. Right. That means scandium has more than yttrium and yttrium has more than lanthanum. Similarly for group 12 also the same thing is there. That means zinc has more. Okay. Zinc has more than cadmium. Zinc has more than cadmium and cadmium has more than mercury, right? Zinc has more melting point than cadmium and cadmium has more than mercury. Again, all is experimentally observed. No logic, no explanation. You have to learn. That is why I'm giving you tricks to remember. Am I clear? That is why I'm giving you tricks to remember. Clear everyone? Clear? 60 beta ji, all of them are radioactive, Pobina. So when they are radioactive, you cannot study their property easily. That is why NCERT has not given their data. And that is why we don't have to study them. Am I clear? Fine. Is it clear, Mobina ji? Fine. Now, if I talk about your group number 11. So here 3D has more than 5D and 5D has more than 4D. Clear everyone? Fine. Here 3D has more than 5D and 5D has more than 4D. Right? Like for example, if you will take group number 11. So group number 11, basically this consists of what? Copper AgAu. Right? So copper will have highest. After that you have 5D. That means Au. And then you have 3D, which is Ag. Okay, right? So copper has more than Au and Au has more than Ag. So this is the complete description of melting point. Is it clear, guys? Is it clear? If it is clear, please give a thumbs up or a heart in the chat box if you are totally clear with this particular fact. Clear, everyone? Yes, clear? Perfectly clear? If yes, then you have to answer me few questions. First is, which of the elements shows lowest melting point in 3D? Chromium, Fe, nickel and copper. Just told you, beta. From manganese to Fe, it increases. But from Fe to copper, it again decreases. Right? That means here, copper will said to have what? Lowest melting point among these in 3D. Clear? Fine. Okay. Next question. Element which is said to have highest melting point in 3D. Quickly tell me in the chat box. Quickly tell me in the chat box which is said to have the highest melting point. Beta, manganese has a dip. Manganese has a dip. Yes, very good, beta ji. Very good. Highest is of chromium in the 3D. I've just told you. Okay. Chromium is said to have what? Chromium is said to have the highest melting point in 3D. Perfectly clear? Okay. Next, everyone. Next topic. Now I'll just move to the next topic, which is the fourth general property. And this is basically your enthalpy of atomization. Am I clear? This is basically your enthalpy of atomization. Now, what is your enthalpy of atomization, guys? Okay. What is your enthalpy of atomization? So, enthalpy of atomization is basically the energy which is required, okay, to convert 1 mole of a substance, any substance, okay, 1 mole of a substance, right, into its gaseous atomic form. Am I clear? Into its gaseous atomic form. Right? Fine. So in this process, the energy which is required, am I clear? The energy which is required, clear? That energy is basically your enthalpy of atomization, which is represented by delta AH, right? H stands for enthalpy, A stands for atomization. Is it clear, everyone? Hi, Nandini. Hello, hello, hello. Is it clear, everyone? Perfectly clear? Okay. Now, look at to me very carefully. Look at to me very carefully. Now, for example, I have to write enthalpy of atomization for, say, H2O. So, at room temperature, H2O exists in liquid state. So, you have to convert, okay, this substance into its gaseous atomic form. So, atoms are basically two hydrogen atoms. Clear? You have two hydrogen atoms in it, plus you have one oxygen atom, right? So, in this process, the energy which is required is enthalpy of atomization. Similarly, if you have methane, it is in gaseous form, right? So, you have to convert it into gaseous atomic form. That means carbon solid plus 4 hydrogen gaseous. Sorry, I have said solid here, it's gaseous. Carbon gaseous plus 4 hydrogen gaseous. Clear? Right? So, the enthalpy which is required is basically enthalpy of atomization. In the case of transition elements, my dear students, we have transition metals in solid state and they are already in their atomic form. So, you don't have to convert them into atom. You just have to convert them into their gaseous form, right? So, the energy required for this process will be termed as enthalpy of atomization for transition elements. Clear? Now, if you will look at clearly, when you are converting 1 mole of a solid substance into its gaseous form in thermodynamics, you guys have studied the enthalpy required for this is basically enthalpy of sublimation. Right? That means what? That means here, my dear students, here, what we will observe, beta G, that here enthalpy of atomization for transition metals, okay, for transition metals is basically equal to enthalpy of sublimation. Am I clear? Is basically equal to enthalpy of sublimation. Am I clear, everyone? This is true for transition element. If this thing is absolutely clear, please give a red heart in the chat box. Yes, if it is clear, please give a red heart in the chat box. Fine. Now, beta, see, more is a strength of metallic bonding. Now, more heat you have to give to break the metallic bond present between the metal atom in a transition element, right? They will move apart and convert into gaseous state, right? Fine. And more is the enthalpy of atomization. That means more is the strength of metallic bonding, my dear students. More will be the enthalpy of atomization, right? So what is the conclusion? The conclusion is enthalpy of atomization is directly proportional to strength of metallic bond, and the strength of metallic bond, beta G, depends upon what? Number of unpaired electrons, right? So from here we got the final conclusion, which is similar to that of melting point. Clear, everyone? Fine. Okay. Is it clear? Fine. Now, here in NCERT, when you will read this topic, the very first point which has been written is that transition elements have high enthalpy of atomization in a similar way as they have high melting point. So why this is so that your transition metals are said to have what? They are said to have a high enthalpy of atomization. What is the probable or the possible reason for that? Yes, what is the probable or the possible reason for that, beta G? Reason is, beta, transition metals have large amount of unpaired electron in Ns and N-1d subshell. Right? What is the reason? Reason is because, yes, because transition elements, yes, transition elements have large amount of or have more number of unpaired electrons in N-1d and Ns subshell right? Therefore, strength of metallic bonding increases. Therefore, strength of metallic bonding increases, right? And if the strength of metallic bonding increases, enthalpy of atomization also increases or is said to be high. Is it clear, everyone? Is it clear? If yes, please give red hearts in the chat box. Now, beta, if you are talking about 3D series, guys. So, since the melting point, you have seen the melting point is not, the trend is not regular. So, enthalpy of atomization trend to is more worst. Clear? So, what all we need to remember and what all is written in NCERT? Very few points which are very understandable. Right. First point is, if I have to compare the enthalpy of atomization of chromium and manganese. In chromium, I have 6 unpaired electrons, and in manganese, I have 5 unpaired electrons. So ultimately, since chromium has more unpaired electrons, so it is said to have more good strength of metallic bonding, and ultimately the melting point is high. Right, everyone? Right. Okay. So the very first point which is written in NCERT and which we need to remember is that enthalpy of atomization of chromium is higher than manganese, right? And one more point which is written is, if I ask you which element in 3D is said to have the lowest enthalpy of atomization? Yes. See, try to understand the melting point trend. Now, the similar is this trend, right? First, your melting point increases, so enthalpy of atomization increases. Why? Because number of unpaired electrons increases. Then, since the number of unpaired electrons decreases, enthalpy of atomization decreases. There is no regular trend. However, we need to remember few points. First is this. Second is, why zinc do you think is said to have lowest enthalpy of atomization in 3D, right? Zinc has lowest, what? It has lowest enthalpy of atomization in 3D. So what could be the probable reason for that, beta? Why it is said to have so? Because it has no unpaired electron, guys. Right? It has no unpaired electron, guys. Right? So no unpaired electron. Not good metallic bonding. Weak enthalpy of atomization. Why? Because no unpaired electron. Right? Its configuration is 3D10 4s2. Clear? Its configuration is 3D10 4s2. So no unpaired electron. Am I clear, everyone? Perfectly clear? Fine. Chalo. So let's just move ahead. Beta G, although I have told you there is no regular trend of enthalpy of atomization, I've already explained you that. But, okay. If you will look at NCERT in a table, they have given the values of enthalpy of atomizations. So in worst of the worst scenario, they might ask you to compare the enthalpy of atomization of 3D series, and the chances for this is very low, right? However, BAB loves you. Okay, right? So that is why ma'am have brought a mnemonic for you guys. And what is that mnemonic? The mnemonic is basically Janab Manku. Janab Manku is a girl. Okay, so Janab Manku basically works in a laboratory. Okay, so Janab Manku scans Fe, cobalt, chromium, nickel through TV. Clear? Okay, so from Zeneb we have zinc. From Manku we have manganese and copper. From scans we have scandium. Okay, from CR we have chromium, Fe, cobalt, nickel. Through TV, T stands for titanium and V stands from vanadium. So you can yourself see that as per the data given in NCERT, the trend is not at all regular, right? So we can see zinc has the lowest, whereas vanadium has the highest enthalpy of atomization. Again, not at all regular. Is it clear, everyone? Fine. Okay, so Zenab Manku scans chromium, cobalt, Fe, nickel through TV. That is a mnemonic which you can use to remember the order of enthalpy of atomization. Clear, guys? Fine. Chalo. So now, let's see how much understanding you guys have for the topic. Fine, let me ask you a few questions. So the very first question right here is, in first transition series, which of the following has the lowest enthalpy of atomization? Yes, quickly tell me in the chat box. Quickly tell me in the chat box. Be quick. Yes, be quick. Very good, absolutely correct. I've just told you, beta, zinc have the lowest, Zaneb at the extreme end. Clear? Fine. Chalo. After that, next question. Beta, it is from NCRT only. Okay, right. So I have framed it into an MCQ. This is an NCRT in text question. I framed it into the MCQ. So in series, scandium, whose atomic number is 21, to zinc, whose atomic number is 30, the enthalpy of atomization of zinc is lowest. Okay, the enthalpy of atomization of zinc is lowest. Why? Okay, why it is so? Why it is so? Quickly tell me why it is so. See, pretty simple, beta ji. Pretty simple. Because here, in case of zinc, we know that there is no involvement of 3d electron in the metallic bonding. Why? Because 3d is completely filled in the case of zinc. So the answer is option number A. Is it clear, everyone? Yes. Jasleen, why D, beta? Why D? Arey bhai, zinc has no electron involved in metallic bonding, beta. Why? Because it has 3d10 4s2. All electrons are paired. Only unpaired electrons are involved in the metallic bonding, right? So if no electrons are involved in metallic bonding, so the enthalpy of atomization is way too less, right? So what should be the answer? Option number 1. Clear? Okay, fine. Now, let's come to the fifth atomic property, and this fifth atomic property is basically your density. Okay, it is basically your density. Now, here, if I talk about density, my dear students, so you have to study the variation of density only for period, and all that also only for 3D. Is it clear, everyone? Fine. So here we have to study the variation along 3D series. So see, beta, if I talk about 3D series, right, that means you're moving left to right in a period, right? So as we move left to right in a period, say from scandium to titanium to vanadium to chromium to zinc, mass is increasing. Yes. Now, left to right, since Z effective increases, that means what? That means what? Atomic size decreases, or we can say volume decreases. Yes or no, guys? Yes or no? Yes, ma'am. Okay. Now, density can be represented by rho or D is mass divided by volume, right? It is mass per unit volume. So, mass increases, volume decreases, that means denominator decreases, numerator increases. That means what? That means density should get increases left to right. Fine. And if I have to look at the unit, if mass is taken in gram and volume is taken in centimeter cube, then the unit will be gram per centimeter cube. Right. So here is the data of NCRT. Now we can clearly see that as we move, okay, as we move from scandium to titanium to vanadium to chromium to manganese to Fe to cobalt to nickel, we can see that density is increasing regularly. Right. Now, in NCRT, it has been written that the density of nickel is same to that of copper. But beta, this is not true. In fact, in JEE Mains, once the question has been asked also, if you will look foreign authors, you will get to see that copper has a little higher density than nickel. Clear? Okay. Copper has a density of approximately 8.96 gram per centimeter cube, right? And nickel has your 8.9 gram per centimeter cube. So copper has little higher than nickel. But as per the NCERT, they both have same. But in JEE Mains, once a question has been asked in which both were given in the option nickel and copper, and they have asked which is said to have highest, they have corrected copper as the correct one. Fine. So you should be aware of it. If both are given in the option nickel and copper, then tick copper. Okay. Now moving from copper to zinc, we see an exception right here. Right. Okay. Fine. We have seen an exception over here that in the case of zinc, what is happening? That density decreases. Why, beta? Because, you know, in zinc, 3D has lot and lot of unpaired electron. Okay, so due to which what happens beta G? Due to which what happens beta G? Here, here what happens is beta G, right? Due to more and more d electrons, what is happening? Here, their poor shielding, okay, or I should say their shielding basically gets increases, right? That means sigma basically gets increases, right? So here if sigma is basically get increases, Z effective get decreases, and if Z effective get decreases, atomic size or atomic volume get increases right here. So here what happens is there occurs a sudden increase in the volume, due to which density suddenly decreases. Right, everyone? Is it clear? So what should be the order? What should be the order? The order is that titanium more than scandium, vanadium more than titanium, chromium more than vanadium, then manganese, then Fe, then cobalt, then nickel. Nickel has nearly same that of copper, but if question comes, tick copper, right? And they both have more than zinc. Okay, now they will ask you, right, in 3D, which element is said to have the lowest density. So you can see the data. Which element have the lowest density? Yes, which element has the, yeah, bilkul, absolutely correct. It increases left to right except zinc. Zinc is an exception over here. Fine. Now, if I ask you which elements have the minimum density in 3D, yes, minimum density, beta scandium. Okay, scandium has minimum density. Yes, it has minimum density in 3D. Is it clear? It has minimum density in 3D. And which has highest? Copper has highest. Okay, copper has maximum density in 3D. Okay, copper has maximum density in 3D. Am I clear, everyone? Yes. Is it clear or not? Quickly tell me. Is it clear or not? Clear? Right? Now, although it hasn't been mentioned, but they can definitely ask this question. They can ask you which elements or which two elements have highest density in the entire D block. One, they can ask you maximum and minimum in 3D, and one they can ask you with the entire D block. So, beta, here osmium and iridium. Okay, osmium and iridium, they have maximum density in transition elements. Okay, they have maximum density in transition element. This is a data you need to remember. In transition elements. Clear? And among osmium and iridium, if you have to compare, then iridium has little higher than osmium. Okay, it has little higher. Osmium has 22.57 gram per centimeter cube. Okay, right, and iridium has 22.61 gram per centimeter cube. Right, iridium has little higher, okay, has little higher than your osmium. Clear, everyone? Fine. Okay, so now let's see how much you were engaged in this particular point. Which metal has highest density? Iridium is not mentioned, only osmium is mentioned. Then you have to pick whom? You have to pick whom? A, B, C, D. Among A, B, C, D. Absolutely correct. Beta G, osmium. Okay, you have to pick osmium. Absolutely correct. Osmium is the correct answer. Next, which element in 3D has the highest density? Yes, which element in 3D has the highest density? Now, this question has been asked in JEE Mains. Now, you can clearly see that here, both nickel and copper have been given. Right? So, in such case, NTA have to give you full mark, whether you mark nickel, whether you mark copper, but you have to be extra correct because we don't know what NTA can do. So, we will tick what? We will tick copper. Okay, we will tick copper. Is it clear, everyone? Okay, so we will tick copper. Fine. Now, fine. So we are done with the fourth property. Now there comes the fifth property. Clear? Now there comes the fifth property, and this property is basically what, beta ji? This property is your ionization energy. Am I clear? This property is basically your ionization energy. I am having a sip of water. You note down the heading, then we will start it in 2 minutes. No, 1 minute, okay? We will start in 1 minute. I am having a sip of water. Yes. Yes. Fifth property, fifth general property, ionization energy. Now, fifth or sixth? I guess it's fifth, yeah. I guess it's fifth, not sixth. Okay, sixth. I'm so sorry. Fifth was density, right? Yeah, it's sixth. Fifth was density. Absolutely correct. Fifth was density, so it is sixth. Cool. Sixth. Agreed. Sixth. Right. Now, ionization energy. Now, what is ionization energy, beta? See, ionization is the energy, the minimum amount of energy which is required to remove an electron from a metal which is present in its gaseous isolated state. Okay, so what you have to do, you have to remove electron from the metal which is present in the gaseous isolated state, and this electron should be the most loosely bound electron. That means electrons of the outermost shell or the valence shell, right? And you have to convert this metal into M plus gaseous cation, right? So the amount of energy which is required in this particular transformation, in this particular process, okay, that energy which is required, is your ionization energy, IE. Clear, everyone? You can write it as IE, or you can write as delta ionization H. Clear, everyone? Fine. Is it clear or not? Perfectly clear? Yes. Perfectly clear? Clear, everyone? Okay. Fine. Fine, 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 fine. I think it should be super fine. Now, if I have to compare the ionization energy of D block elements, S and P block elements, first you have S block elements, then you have D block elements, then you have are the P block elements. So as we move left to right, Z effective increases, and I have told you in periodic classification that Z effective is directly proportional to ionization energy. More is Z effective, more is the attraction between nucleus and the outermost shell electron, and the larger amount of ionization energy is required to remove the outermost shell electron. Clear? Right. That means ionization energy is directly proportional to Z effective. Beta, I will give you break after completing the ionization energy. I have made a picture by which I will try to wind up this lecture by 2 p.m. Otherwise, like last time, it will get extended. So please help me. Please help me. Okay. Fine. Okay. Please help me, and please be a little cordial. Otherwise, it will again stretch up to 11 hours. We have to complete it in 9 hours. So if you will support me, you will help me, then only we can do it. Otherwise, it's not possible. Because after 12, you know that the break will come after every 1 hour. Okay, cool. Right. So left to right, as we move from S block to D block to P block, Z effective is getting increased, right? So fine. So if Z effective is getting increased, so ionization energy is also increases. That means ionization energy of P block is higher than D, and D is higher than S. So that means D block is said to have ionization energy between S and P block. Okay, fine, everyone. Now, if I have to write first the variation of ionization energy along the group, okay, right? So, beta, as we move top to bottom in a group, in all the groups except group number 3, 5D series is said to have highest ionization energy. Why? Because in 5D beta, there occurs lanthanoid contractions. And due to lanthanoid contraction, Z effective increases. Lanthanoid contraction is what? It is poor shielding of 4F. And due to poor shielding, Z effective increases. And if Z effective increases, then ionization energy definitely increases. And we know that lanthanide contraction doesn't take place in group number 3. That means in the case of lanthanum. Why? Because after lanthanum only lanthanides are coming. Am I clear, beta ji? Fine. Okay, so after lanthanum only lanthanides is coming, right? So except group number 3, all the other group 5D element is said to have highest ionization energy. Clear? Okay, right. So what we have studied right here? Yes, what we have studied right here? We have studied right here, my dear students, that just a second. Yeah, right. We have studied that 5D element will have highest energy except group number 3. Okay, fine. So let's just subdivide it all the group from 3 to 12 in 3 cases. Okay, let's subdivide them. Okay. Now, if I have to talk about group number 3. So beta, in group number 3, we know that there is no lanthanide contraction. So let's go by general trend. Top to bottom size increases, right? And when size increases, ionization energy decreases. Why? Because atomic size is inversely proportional to ionization energy, right? So what will be the order? The order will be 3D has more than 4D and 4D has more than 5D. Okay, that means if you have in group 3 scandium, scandium has more ionization energy than yttrium and yttrium has more ionization energy than lanthanum. Clear everyone? Fine. Okay. Now listen to me very carefully. In group number 7, 8, 9, 11 and 12, the order is reversed to that of group 3. You have to remember it because you need to learn the trick. It's all exceptional, right? So here, order is basically the opposite to group 3, right? Similarly, in group number 4, 5, 6 and 10, it is different from that of group 3. It is different. Clear? What happens in group 4, 5, 6 and 10? Beta, here 4D has more than 3D and 5D has more than 4D. Right? So for example, in group 4, you have group 4. Right? In group 4, you have in 3D titanium, in 4D zirconium and in 5D hafnium. Right? So hafnium has higher energy than zirconium and zirconium has higher energy than titanium. Similarly, in group 5, you have vanadium, niobium and tantalum. So as we move from 3D to 4D to 5D, ionization energy increases. Is it clear, everyone? Okay. See, beta, it's very easy to remember the exception. In group number 3, the trend is general, that as we move top to bottom, ionization energy decreases. Right? Then you have to just remember the group numbers. So 4, 5, 6. After 3, 4, 5, 6 and 10. Okay. Here the order is reversed to this. Right? And you have learned except third group, everywhere 5D has more ionization energy. So here 5D is highest. Right? And in these also 5D should be highest as per this line. So you have to reverse only 2. You have to reverse 4D with 3D. That's it. Am I clear? Right? You just have to reverse 4D and 3D. Clear? That means here 4D at top, 3D in between. Is it clear, everyone? Okay, so for example, in group number 7, you have manganese in 3D. Right? Below manganese, you have TC in 4D. Right? And below TC, you have Re in 5D. So this is the order. Am I clear, everyone? Is it clear, everyone? Quickly tell me. Is it clear? Pretty simple. Group 3, general trend. Top to bottom decreases. That means 3D has more than 4D, 4D has more than 5D. Reverse to group 3, we have in group 4, 5, 6 and 10. Okay, right, and 5D should have been highest. So if 5D has to be highest, we have to vice versa 4D and 3D with each other. Simple. Learned. Learned. If this trick is clear to you guys, give me a red heart and a thumbs up in the chat box. If this thing is clear to you guys, please give me a red heart in the chat box. Clear, guys? Yes, clear. Okay, so we have seen the variation of ionization energy along the group. Now we have to see along the period, right? So when we move left to right in a period, what is the expected trend? Beta, left to right, Z effective increases. Yes, left to right, Z effective increases. And if Z effective increases, what will happen? Yes, what will happen, everyone? If Z effective increases, your ionization energy will get increases. Am I clear? If Z effective increases, then definitely what will happen? Your ionization energy will get increases. Agreed, everyone? Yes, agreed, everyone. Okay, so that means if I have to consider the very first element which lie on the extreme left, like for example, in 3D series, we have scandium. Okay, it will have the minimum ionization energy, right? And as we move left to right, the ionization energy increases. So as we move from scandium to the last element, zinc, it should have what? It should have maximum ionization energy, right? That means in each series, first element is said to have what? It is said to have minimum ionization energy. Am I clear? It is said to have minimum ionization energy. However, the last element of each series is said to have what? It is said to have maximum ionization energy. Is it clear, everyone? Yes. Is it clear, everyone? Perfectly clear. Yes, perfectly clear. Okay, fine. You can ask your questions in the chat box. Okay, never do like this, ma'am, I have a question. Write your question in the chat box. It will get solved. Okay, guys, fine. Now, here, in 4D series, the very first element is yttrium. It has the minimum. And the last element is cadmium. It has the maximum. 5D series, the first element is lanthanum, right? And the last element is mercury. Now, although very less probability of this, but yes, few questions have been asked in this manner. They might ask you the variation of ionization energy along 3D. Okay, they might ask you the variation of ionization energy along 3D. They might ask you that. Okay, so for that, I have a mnemonic, right? So it is basically Zainab's birthday. Zainab is basically a girl, okay? Now, Zainab has total of how many sisters, beta ji? 3. First is Sudita, second is Vedita, and third is Manisha. Clear, everyone? Fine. Okay, so there are 3 sisters, whom, beta ji? Sunita, Vinita, and Manisha. So what happens is, Manisha came first. You know, they have just cutted the cake at 12 a.m. in the Zainab's birthday, right? And we all do the same thing. Now, at night, we do not eat cake. Next day, when we come back from the school, the first thing you want to do is have a piece of cake. So, Bedisha did a clever act. What she did, she came very early from the school and nibbles. Nibbles means ate the cake before Sudita, Vinita, and Zainab came home. Clear? So from there we got the mnemonic. Sunita, Venita came home, cried till Manisha nibbles cutted cake for Zainab's birthday. Zainab means to nibbles means to swallow, to eat very fast. Okay. So from Sunita we have scandium, from Venita we have vanadium, from cried chromium, from till titanium, from Manisha manganese, from nibbles nickel, from cutted copper, from cake cobalt, from 4 we have Fe, from Zenibs we have zinc. Okay, so what should be the order of ionization energy? Yes, order of ionization energy in 3D. Yes, guys, the order of ionization energy in 3D, right? So the order is the way. After scandium we have vanadium, then chromium, then titanium, then manganese, then nickel, right? Then you have copper, then you have cobalt, then you have Fe, and then you have zinc. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 10 elements covered. Yes, 10 elements covered, guys. Fine. So this is the overall order of ionization energy for 3D series. Okay, Hindi mnemonics. So Hindi mnemonics, if you want to learn, so I have in PW teaches in taught in Hindi batches also. So you can type the by name, okay, with the lecture in Hindi of DNF block, you will find it. Okay, guys. Now here, this is the only mnemonic I can give you. Fine. What happened? Oh God. Magic. It's magic. It's magic. Chalo. So now let's move ahead, Betaji. Let's just move ahead. Now, we have to understand few questions of the NCERT and few trends of ionization in the NCERT. So for that, we need to understand few things. Okay. First thing is that if you want to remove the electron from say 3D5 or 3D10 electronic configurations, we all know that 3D5 and 3D10 electronic configurations are extra stable electronic configuration. Why? Why, everyone? Due to exchange energy and due to symmetry. Yes, due to exchange energy and due to symmetry. Agreed, everyone? Agreed, everyone? Fine. Okay. So if you have to remove an electron from a stable electronic configuration, you have to give extra energy. Okay, that means ionization energy is high. Clear? So whenever you are removing electrons from, whenever you are removing electron from D5 or D10, high ionization energy is required. Right? And if after removing the electron, you are getting this D5 and D10 electronic configuration. Okay. So after removing electron, okay, after removing electron, if D5 and D10 is coming, so anyone want to lose this electron, right? So in that particular case, very low ionization energy is required. Like for example, if you have to go from 3D6 4s2 to 3D5 4s2, very less energy will be required. Why? Because D5 is stable. Clear? Very low ionization energy is required. Okay. So whenever after losing one electron or two electrons, D5 or D10 configuration is coming, right? Very less ionization energy is required. Is this point clear or not? Because then only you will able to understand the next topic which I am going to teach. Yes. Is it clear, everyone? Clear? Perfectly clear? Okay. So now let's go through the questions which are given in the NCERT, which we need to discuss in detail. The very first question, zinc has highest first ionization energy in 3D series. Why zinc has highest ionization energy in 3D? Yes, why it is said to have the highest ionization energy in 3D? Clear? Are Charan, Sparsh, Pankaj, Panchal. Okay, G. Fine. Now, why zinc has highest first ionization energy in 3D? Answer to that is pretty simple. Beta, zinc has fully filled electronic configuration which is very stable. Right? Argon 3D10 4s2. Am I clear, everyone? Fine. Okay. So it has fully filled stable electronic configuration, right? That is why zinc has highest, okay, zinc has highest ionization energy in 3D, okay, in 3D. Fine, everyone. Okay, so now let's come to the next question. Very interesting it is. Question is, the first ionization energy of zinc is higher than copper. Cool. However, the second ionization energy, everyone, of copper is higher than zinc. Why it is so? See, pretty simple. If you are taking copper, right? Fine. If you are taking copper, fine. So copper has 3d10 4s1. So if we have to remove the first electron, the energy which is required is first ionization energy. That means IE1, guys. Yes, IE1, guys. Okay, fine. After the removal of first electron, you will have copper plus, which will have an electronic configuration of 3d10. Now, if you have to remove second electron from copper plus, the energy which is being required is your second ionization energy, which is IE2. Am I clear, everyone? Okay, fine. Now, similarly, in the case of manganese, okay, in the case of manganese, it has a configuration of 3d10 4s2, right? When it will lose one electron, it will form Mn plus, and the energy required is the first ionization energy. So one electron is lost. It is always lost from the outermost subshell, that means 4s. So it is 3d10 4s1. Clear? Right. Okay. Now, talking about second ionization energy, if you will give, it will form Mn2 plus. So it will have 3d10 electronic configuration. Now, my question to you guys is, if you have to compare the first ionization energy, okay, fine. In copper, the electron has to be removed from this. In manganese, it has to be to remove from this. Which is more stable, this or this? Definitely this one. Why? Because 3d is also completely filled, 4s is also completely filled. Okay, right. That is why we say that first ionization energy, right? First ionization energy of zinc is higher than copper. Oh God, I have by mistake written manganese, right? I have to write zinc. I'm so sorry. I'm so sorry, everyone. By mistake, I've written manganese. Huh? I think now ma'am should give you a break. I'm so sorry. It is zinc, not manganese. I'm so sorry, guys. So sorry. Yes, sorry. It's zinc. Haha, zinc, zinc. Zinc, guys. Extremely sorry. Right? Sorry. Again, sorry. Haha. It's zinc. I'm so sorry. Okay, so first ionization energy of zinc is higher than copper. Why? Because zinc both are filled and copper is one is fully filled and one is half filled. Right. Now, if I talk about the second ionization energy, right, in zinc, if you will lose one electron, you will get a stable electronic configuration. I have just told you, yes, I have just told you that whenever you are losing an electron and getting a more stable electronic configuration, lesser energy is required. So that is why the second ionization energy of zinc will be lower. And in the copper, the electron has to be removed from a stable 3d10 configuration. So large amount of ionization energy is required. Clear? Okay. So therefore, IE2 will be higher of copper more than zinc. Is it clear, everyone? Yes. Is it clear? Perfectly clear or not? Clear? Okay, fine. Chalo. Let's move ahead. Next question. First ionization energy of manganese is higher than chromium, but second of chromium is higher than manganese. Same thing, beta ji. If I have chromium, it has 3d5 4s1. Yes, its configuration is 3d5 4s1. So after removing the very first electron, the energy required is first ionization energy. We get chromium plus. It has 3d5 electronic configuration, and after removal of second electron, in which we required second ionization energy, we get chromium 2 plus, which is 3d4. Clear? Okay, fine. And similarly, in the case of, say, manganese, which has 3d5 4s2 electronic configuration, when you are removing the first electron, right? When you are removing the first electron and forming manganese plus, right? So the energy required is the first ionization energy. So here you get 3d5 4s1, right? And after removal of one electron, you will get more electron, manganese 2 plus, for which you need second ionization energy, and then you will get 3d5 right here. So if you look at the electronic configuration of chromium and manganese, in chromium, 4s has 1 electron, but in manganese it has 2 electrons. That means electronic configuration of manganese is more stable than chromium. Clear? Right? Therefore, first ionization energy of manganese is definitely high than chromium. However, if you have to look at the second ionization energy, in chromium, electron has to be removed from more stable electronic configuration of 3d5 comparative to this, right? That is why, beta G, second ionization energy of chromium is more than manganese. Okay, it is more than manganese. Perfect, everyone. Perfect, perfect, perfect. Now, why the third ionization energy of manganese is more than Fe? See, beta, third ionization energy will be the energy which is required to remove electron from Mn2 plus. So, Mn2 plus has 3d5. Clear, everyone? Okay, so if you have to form Mn, then Mn plus, then you will form Mn2 plus. Now, so for this, first ionization energy is required. For this, second ionization energy is required. And from this, if you have to remove the electron, then third ionization energy is required, guys. Clear? Fine. Okay. Perfect. So same thing. If you have to do from Fe2 plus, which has 3d6, okay, fine. So you only tell me, yeah, manganese, if you have to remove the third electron for which third ionization energy is required, guys, right? Okay, so manganese has half filled, which is more stable than Fe, right? That is why the third ionization energy, okay, of Fe, of manganese is higher than Fe. Okay, the same logic of electronic configuration, nothing else. Okay, fine. Now let's do some question and see how attentive you were. Okay, if you have got it, then please give me some red hearts in the chat box. If you have got it, please give me some red hearts in the chat box. Yes, everyone, some red hearts in the chat box if you have got it. Some red hearts in the chat box. Yes, guys. If you have got it, then yes, some red hearts in the chat box. Got it? Perfectly got it? Cool. Now, here, let's do some question. So it has been asked in JEE Mains, which is said to have maximum third ionization energy. Beta, it's very easy. I've just told you. So if in removing the third electron, you have a stable electronic configuration now, then the third ionization energy will be high. Okay, right. So see, if I talk about cobalt, right? So if you have cobalt 2 plus, then if you have to form cobalt 3 plus, the energy required is ionization energy 3. Okay, so cobalt 2 plus has 3d7 electronic configuration. Similarly, if I talk about Fe2 plus, so here it is 3d6. If you have nickel 2 plus and you have to form nickel 3 plus, the energy required is third ionization energy. And if you have manganese 2 plus and you have to remove the third electron to form Mn3 plus, the energy required is ionization energy. Now, in the case in which the electronic configuration is stable, the ionization energy which is required is high, right? And, right, that means, and here, if after removal of one electron, you are getting a stable electronic configuration, listen to me very carefully. Maximum, yes, manganese, agreed. However, guys, listen to me very carefully. However, if after removal of one electron, you're getting a stable electronic configuration, in that case, the ionization energy will be minimum. So, in the case of Fe, after removal of one electron, we get 3d5, right? Okay, clear. So, that is why we will say that Fe is said to have minimum ionization energy. Agreed, everyone? Agreed? Got it? Yes, got it? Fine. Chalo, it's a very good question. Now, they are asking us the order of second ionization energy. We have already seen that the second ionization energy of chromium is higher than manganese. We have just seen. So I think if we know this thing, then we do not need to see further. C will be the answer. We have just seen. Cool? Okay, fine. ठीक है? Chalo. So this is the 7th topic, which we will discuss after the break, I guess. So now it's the time of a break, half an hour break, 30 minutes break. 30 minutes is enough for you to eat your lunch. Yes, 30 minutes are enough or less than that. Yes, everyone. Less than that. Are 30 minutes enough for your lunch? Lunch, I'm saying dinner. I'll have my lunch because I didn't have my lunch. Haan bhai, 30 minutes are enough to have your dinner. Let's keep 25 to 30 minutes, okay? Maximum 30, minimum 25. And if 1 to 2 minutes exceeds, then please don't ask where is Bab, okay? And please, I can see 60 students right here. I want all of them after the break. Let's be consistent and complete this chapter. Fine, okay? So 30 minutes break till 9 p.m. Okay, fine. So let's meet. Hello everyone, am I audible and visible? Hello, hello, hello. Yes. Hello everyone. Am I audible and visible? Can you see me? Can you hear me? Okay. So let me just message everyone to rejoin. Okay. To rejoin. Fine. Let me just message. Okay. So I've messaged, right? I have messaged people to rejoin, right? So that we can start. So let's start. I think you guys must have refreshed, right? Okay, so I also had food. I was also very hungry. Actually, I had just my breakfast. My mother went to my Masi's house. I didn't knew it. So when I went downstairs, there was nothing to eat. So I have to order. So it took a little time. That is why I just came a little bit later. Don't worry, I will now give the next break only when I have to start with K2CR207 and KMNO4. Okay, right? So after that, only 2 hours topic will be left. 1 hour is for KMNO4, K2CR27 and the another 1 hour for F block elements. Okay, let's go everyone. Fine. Chalo, let's start. So the seventh property or the 7 general characteristic which we have to study right now is basically your oxidation state. Okay. Now, if I talk about D block elements, they show variable oxidation state. Now, why they show variable oxidation state? Because beta, here the energy difference between Ns and N minus 1D subshell is very less. Okay, right. Like for example, if you have manganese, fine. In manganese, you have 2 electrons right here in 4s, right? And you have how many? Yes, you have how many electrons, beta G? You have how many electrons in 3D? 5 electrons. So the energy difference is so less. So what can happen, beta G? Here, the excitation of electrons can occur. Okay. In fact, the difference between 4s, 3D and next higher shell is also very less. That means here, if you have 4p na, beta G, so the energy difference is very less. So electrons can get excited. Like from 4s, 1 electron can get excited to 4p. So you have 7 unpaired electrons. In chemical bonding, we have studied. Now, the as number as of we have half filled p orbital, right? That is half filled p, d or s orbital. That is basically equivalent to covalency. And covalency is basically equals to number of covalent bond formed, right? Okay. Now, as many as half filled atomic orbital you have in the electronic configuration, that number of orbitals can be involved in the overlap with the other orbitals and results into the formation of what? Covalent bond. Right? Okay. So here it has been written that due to this little difference beta G, both the orbitals can be used in order to form the bond. That is why in the case of manganese, you can have up to 7 oxidation state. Is it clear, everyone? Okay, I'm repeating it once again. As per the VBT, if you have more number of half-filled atomic orbitals, more are the chances of formation of covalent bond by overlapping of that half-filled atomic orbital of transition element with the side element, right? And as the number of covalent bonds increases, the oxidation state on the central metal atom or ion also increases. Clear, everyone? Fine. Now, here, your transition elements can have variable oxidation states, many oxidation states, right? But now the question arises that how you can find for any element maximum oxidation state and minimum oxidation state, okay, right? So now, if you want to find the maximum and minimum oxidation state, you need to calculate 2 things. The very first thing is N. N is basically equals to the number of unpaired electrons. Mark my word. It is basically equals to what? It is basically equals to number of unpaired electrons present in D subshell. Okay. And then you need to find M. What is M? M is basically the number of unpaired electron in NS subshell, or I should say number of electrons in NS. Whether paired, whether not paired, both allowed. Okay, so for D, you have to take only unpaired electron, and for S, you have to take the total electrons. Okay, so maximum oxidation state of any element in D block element is basically equals to N plus M, right? And the minimum oxidation state is basically equals to number of NS electrons. That means it is equal to M. Am I clear, everyone? Okay, like for example, I have manganese. Okay, now electronic configuration of manganese is argon 3d5 4s2. Am I clear, everyone? So here, what is the value of M? Beta, M is basically equals to 2, right? Because M is basically number of electrons in NS subshell, right? It is basically equals to 2. And if I talk about N, N are basically number of unpaired electrons. So in manganese, you have 3d5. So it has 5 unpaired electrons, right? So M is basically equals to 5, right? Now, if I have to find for manganese maximum oxidation state, it is N plus M, right? That means 5 plus 2. So that is basically equals to what? Plus 7. Yes, it is basically equals to what? Plus 7. Agreed, right? And if I have to find minimum oxidation state, now minimum oxidation state is equals to M. So it is basically equals to how much? Plus 2. Clear, right? That means manganese can have all the oxidation states from plus 2 to plus 7. Okay, so these are the minimum and maximum oxidation states corresponding to what? Corresponding to manganese. Perfect. Okay, right. Now, here in this table, we will write all the possible oxidation states for 3D elements. Okay, right. To begin with, we have the first 3D elements, which is scandium. Right. Now, if I talk about scandium, my dear lovely students, okay, now if I specifically talk about whom, I talk about scandium. See, if I have to find the minimum oxidation state, so minimum is the number of NS electron. So there are 2 electron. So minimum should be plus 2 and maximum should be 2, that is number of NS electrons, plus number of N minus 1D unpaired electron, that is 2 plus 1 equals to plus 3. Now, when scandium is said to acquire plus 3 beta G, here scandium is said to have the electronic configuration of argon, right? We know that scandium has electronic configuration of 3d1 4s2. Okay, so when it will form scandium 3 plus beta G, it will have the configuration of whom? Argon, right? So this is a stable configuration, or I should say stable electronic configuration of noble gas, which is highly stable. That is the reason scandium forms compounds in plus 3 oxidation state only. It hardly form any compound in plus 2 oxidation state. Okay, so scandium hardly form, matlab it does not even form any compound in plus 2 oxidation state. It forms compounds only in plus 3 oxidation state. Okay, now if I talk about titanium, guys, right, what should be the minimum oxidation state? Number of NS electrons, which is basically 2, right? And maximum D plus S, so 2 plus 2, right? Number of unpaired electrons in D, 2 plus NS electrons 2. So it is plus 4, and in between them, it can also have plus 3 oxidation state. Okay, it can also have plus 3 oxidation state. Similarly, if I talk about vanadium, it can have from plus 2 to 2 plus 3 plus 5, right? That means plus 3 plus 4. If I talk about chromium, right? Now, although it has 1 electron in NS, right? But in the case of chromium, we mostly see plus 2 oxidation state only beta. It hardly shows plus 1 oxidation state. Am I clear? Mostly it shows plus 2 only. Okay, fine, cool. Now, after that, beta G, maximum is 1 plus 5, that is plus 6. So here it can have all the oxidation states between them, plus 3, plus 4, and plus 5. Right, now let's come to Mn. Right, minimum is again plus 2, maximum is 2 plus 5, plus 7. So in meanwhile, it can show all the intermediate oxidation states. Clear, guys? Perfectly clear? Okay, fine. Now here, if I talk about Fe, see, try to understand this fact. In Fe now, you have D6. So that means in D6, the pairing has begun. So you have only 4 unpaired electrons. That means N is only 4 and M is 2. So 4 plus 2, that means the maximum oxidation state which it can show is plus 6. Right? And the minimum is plus 2. It also shows plus 3, plus 4, right? Fine. Plus 5. But it hardly occurs in plus 5 oxidation states and plus 4. Matlab, they are very rare. Very rare. Okay. So majorly plus 2, plus 6, 3 and plus 6 mostly. Clear? Okay. If I talk about cobalt, similarly cobalt can also show minimum plus 2, and here we have one more electron pair, so 3 are left unpaired. So 3 plus 2 is plus 5. Again, plus 5 is very hardly shown, although plus 3 and plus 4 are shown. Am I clear, everyone? Okay, fine. Nickel, it can have plus 2 and 2 unpaired electrons in 3d8, plus 2, you can have 4 plus 4. Clear, everyone? So it's to plus 2 and plus 4 and plus 3. Copper, see, copper can show plus 1 oxidation state. In fact, copper plus 1 is stable in the gaseous state. So it can show plus 1 oxidation state, right? And in some of the cases, it might show plus 2. Plus 2 is basically more shown in the aqueous form, which I will explain you ahead. Clear? We will discuss about the fact. Okay, right. Now, if I talk about zinc, it only shows majorly plus 2 oxidation state. Now, you only tell me which oxidation state is shown by the maximum number of elements. Yes, which oxidation state is basically shown by the maximum number of elements? I guess plus 2. So, what is the most common oxidation state, Rajay? It is plus 2, right? Except scandium. Scandium hardly shows plus 2. ठीक है जी? Is it clear, everyone? Fine. Am I clear? Yes. Am I clear, guys? Perfectly clear. Shall we move ahead? Okay. Right. Fine. Cool. Any problem, anyone? Yes. Any problem, anyone? Clear? Shall we move ahead? Okay. Now, so the important point of NCERT, which we'll cover by watching the previous table. So these are, if you will see, right, the middle elements, right? Middle elements, which is manganese, it can shows maximum number of oxidation state. Why? Because ma'am, here the maximum number of unpaired electrons are existing in 5D, and ma'am, 4s also has 2 electrons. Agreed, everyone? Agreed, everyone, right? So we got to understand that elements which occurs in the middle of 3D series can show maximum oxidation state. Agreed? Which element is the one? The beta element is basically manganese. Am I clear? The element is manganese, which can show all the oxidation state from plus 2 to plus 7. Clear? Right? Now, the elements which are occurring on the extreme ends, right? For example, on left extreme end, we have scandium. And on the right extreme end, we have copper and zinc. These elements are said to have very few oxidation state. Why? Again, the number of unpaired electrons are very less. Okay, fine. So we got to understand the second point, that the lesser number of oxidation states are shown by the elements on the extreme end. Scandium can show oxidation state of only plus 3. Okay, copper can show oxidation state of only plus 1 and plus 2, and zinc can only show the oxidation state of plus 2. Clear, everyone? Fine. Now, scandium in plus 3, titanium in plus 4, vanadium in plus 5, chromium in plus 6, and manganese in plus 7, guys. Right. Here, they are said to have a stable electronic configuration of argon. Right. Right. They have a stable inert gas configuration in all these oxidation states. That is why these oxidation states are highest stability one. Matlab, these oxidation state has the highest stability. Am I clear? Why? Because they have stable inert gas configuration. Configuration. Am I clear, everyone? Fine. Chalo, let's move ahead. Let's move ahead. Let's move ahead. Ma'am, why chromium does not show +1 oxidation state? It might show +1, but that is not stable. That is why we have not written. Beta, see, the range, it's okay to find. Range you can find. But there are few oxidation states in the range which an element does not show in any compound. Clear, everyone? So, in order to find the compound, we need at least, if you will find any compound, then only you can just, say that this particular oxidation state exists or not. So, we don't found any much compounds in the case of chromium where it shows +1 oxidation state. Clear, everyone? We rarely found any compounds like that. Okay, so now let's just move ahead, everyone. For zinc, the most stable oxidation state is +2. Why? Because here it has 3D 10 electronic configuration, which is fully filled. So this line is also written in NCERT, right? Similarly, for Mn2+, it has 3D 5 configuration, and Fe3+ has also 3D 5 configuration. So they are also amongst stable electronic configurations. Okay, they are what? They are amongst stable oxidation states, right? Amongst the stable oxidation states corresponding for Mn and Fe. Although most stable for Mn is +7, but yes, +2 is also stable, right? Why? Because here it has half filled d orbital. Is it clear, everyone? Am I clear? Yes, am I clear? Perfectly clear? Okay, chalo. Let's just move ahead, guys. Now, this is a very important point. Very, very, very important point. Okay. Now, what does this point says? This point says that in p block elements, as we move down the group, the lower oxidation state is more stable due to inert pair effect. Okay, so we know that in group 13, or I should say group 15, as we move from nitrogen to phosphorus to arsenic to antimony to bismuth, okay, although the group electronic configuration is ns2np3, right? So what should be the group oxidation state, beta? Number of electrons in ns plus np, so 2 plus 3 5 should be the group oxidation state, and that is basically the maximum oxidation state also, right? Fine. So here, due to inert pair effect, the stability of +5 oxidation state decreases, whereas +3 increases, right? That means for bismuth, only for bismuth, +3 oxidation state is more stable than +5. You guys must have studied inert pair effect. If not, then my lecture for P block is available on this channel. You can study it from there, okay? Now I can't dive into detail. It is a 2-hour long topic. We just need to understand only the fact that due to inert pair effect, the stability of lower oxidation state increases down the group. So for heavier elements like bismuth, +3, that means a lower oxidation state is more stable than higher oxidation state. Clear, everyone? Okay. However, if I talk about D block elements here, for D block elements, beta G, higher oxidation state is more stable for heavier elements. Like for example, if I consider the group of chromium, molybdenum and tungsten, okay, which is basically your group number 6, right? So for group number 6, Rajay, for tungsten and for molybdenum, right, +6 is more stable. That means higher oxidation state, because highest oxidation state possible for groups number 6 is +6 only. Clear? Right. So for molybdenum and tungsten, +6 is more stable comparative to what? Comparative to the chromium. Right? It is an experimentally observed fact. How this fact has been proved, beta? This fact has been proved that when you take oxides of all the three, like for example, if you take tungsten oxide, WO3, here tungsten has +6 oxidation state. You take molybdenum oxide, that is MoO3. Here molybdenum is again said to have +6 oxidation state. And in the case of chromium, you can either take CrO3, right, or you can take K2 Cr2O7, right? So here all of them are present in maximum oxidation state. So they cannot undergo oxidation because oxidation means increase in oxidation number. Already their oxidation number is maximum, right? Fine. So they can undergo reduction. That means decrease in oxidation number. And if they can undergo reduction, then they might act as what? They might act as oxidizing agent, guys, right? So it has been seen that these both do not act as oxidizing agent. ठीक है, they both do not act as oxidizing agent, and if they do not act as oxidizing agent, that means +6 is stable for them, right? However, we all know that K2Cr2O7 or CrO3 is a very good oxidizing agent, right? Why? Because for chromium +6 is not stable, it can undergo reduction. Clear? Right? Fine. So here we can say that chromium in +6 can act as good oxidizing agent. Is it clear, everyone? Yes, is it clear or not? Perfectly clear. If clear, please give red hearts or thumbs up or fire emoji very quickly. Yes, please give it. Please give it. Yes, 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 please give it. Now, beta, although we have written the common oxidation state for all the elements in 3D series, but if transition metals are forming coordination compounds with carbonyl ligand, this I will teach you in coordination compounds. Here, carbonyl is said to be a neutral ligand. That means here it is said to have zero oxidation state, right? So if you take the oxidation state of Fe as X, now here you have how many carbonyls? 5. So it will be equal to 0. So therefore, X will becomes equals to 0. Similarly, here also the oxidation state of nickel is 0. So that means transition metals can also have a zero oxidation state. It has been given in NCERT where they can have zero oxidation state, beta, in their metal carbonyls. Where? In their metal carbonyls. Okay, in their metal carbonyls. Okay, guys, clear? Perfectly clear? Fine. Chalo. Let's move ahead. Let's move ahead. Now, there are two transition elements, okay, right? They are not from 3D. They are not from 3D, but my dear students, they are said to exhibit maximum oxidation state of +8, right? Fine. And they are ruthenium and osmium. Clear? So they both exhibit highest oxidation state in the entire D block, which is said to be +8. This is in fact which you need to remember. Am I clear, everyone? Take care. Okay, fine. So ruthenium and osmium, they have maximum oxidation state of +8. Cool, everyone? Fine. Chalo. Let's move ahead to few questions. So here, the very first question, let me see how much active you were in this particular topic. Okay, so I'm giving you one question right here. You tell me the answer. The question is, the element that usually does not shows a variable oxidation state is. Which elements do not show variable oxidation state? The one on the extreme ends, right? That is scandium and copper, but copper can show two oxidation state, which is +1 and +2. But scandium can show only one oxidation state, which is +3. That means scandium, my dear friend, is said to be the one which is said to have only one oxidation state. So it does not show the variable oxidation state. Clear? Fine. Now let's move ahead, guys. Which of the following transition element do not exhibit variable oxidation state? Now here people will say, ma'am, zinc also shows one oxidation state, which is +2, and scandium also, right? So answer should be option C, both. But my dear students, they are saying transition element. Clear? And zinc is clearly not transition element. Am I clear? Zinc is not, it is a D block element, but it is not a transition element. I've already told you, right? So what will be the answer? Answer is option number A, scandium. For all those who are thinking that it will be C, you guys are not wrong. You just have forgotten something. Am I clear? Right? This question is given in NCERT. Right? This question is given in NCERT. If I remember, it is given in NCERT too, right? So NCERT in text question, name the transition element which do not exhibit variable oxidation state. So answer is scandium +3 only, right? Not zinc. Why? Because zinc is not transition element. Am I clear? Zinc is not transition element. Is it clear? Yes. Is it clear, everyone? Perfectly clear or not? Quickly tell me. Is it clear? Yes. Cool? Fine? Chalo. Let's just move ahead to the next question. The common positive oxidation state that could occur for an element with atomic number 24 is, see, 24 is basically your chromium beta, and chromium can have all the oxidation states from +2 to +6. Clear? So answer will be option number C. Okay, the answer will be what? The answer will be option number C. Cool? Okay, fine. Chalo. Let's just move ahead to the next question, guys. Let's just move ahead to the next question. Oxidation state of scandium, possible, +3. No question required right here. Which one of the following exhibit large number of oxidation states, beta, in 3D? We know that manganese exhibits maximum number of oxidation state, right? Fine. Starting from how much? +2 to +7. So what will be the answer? Answer is option number D. Am I clear? Answer is option number D. Fine. Okay, so next question on your screen, beautiful question. Which of the following not act as oxidizing agent? I have just told you that chromium in +6 can act as an oxidizing agent, right? Okay, fine. However, tungsten in +6 and molybdenum in +6, they are the stable oxidation state for both of them, right? But chromium in +6 can act as an oxidizing agent, right? So here it can act as an oxidizing agent, but these two cannot act as oxidizing agent, my dear friend. So what will be the answer to this particular question? Yes, what will be the answer to this particular question? B and C, option number C. Cool, fine. So it's very easy, yaar. It's very easy to do the questions, right? You just need to understand the concept. Fine. So here we have done with the 7th general property. Now we are coming to the 8th general property, and this is basically your standard electrode potential. Okay, so the next property is basically standard electrode potential. Okay, now we have already studied electrochemistry, right? We know that standard electrode, ma'am, not understood. Which not understood, beta? Haven't I told you that +6 is more stable? +6 is more stable for heavier elements in D block comparative to chromium. That means for tungsten and molybdenum, +6 is more stable. Haven't you heard it? I've just told you. So tungsten in +6 and molybdenum in +6 are stable. They won't undergo reduction or act as an oxidizing agent. However, chromium in +6 can undergo reduction and can act as oxidizing agent. Is it clear? Is it clear? What you haven't understood, Mobina? Haven't you heard me? I've just told you. Right? Okay, so answer is B and C for that particular question. Fine. The answer is B, C for that particular question. Now, next, this is number 8. This is basically your standard electrode potential. Okay, so let's just complete this in 30 minutes. This is the biggest one. After that, easier things will be there. Okay, fine. So now, here, standard electrode potential. See, we know that in electrochemistry, standard electron potential can be of two types, right? It can be of how many types? It can be of two types, right? One is basically your standard oxidation potential, right? And the other one is basically your standard reduction potential. Right. Now, what is SOP or standard oxidation potential, beta? It is basically the measure of tendency of a substance to undergo oxidation. That means more is the value of SOP or more is the value of standard oxidation potential. More is the tendency of a substance to undergo what? To undergo oxidation. That means if SOP increases, tendency to undergo oxidation increases. Am I clear, everyone? right? Fine, right? Similarly, standard reduction potential is the measure of a substance's tendency to undergo reduction. That means more is the value of SRP or standard reduction potential, more is a tendency of a substance to undergo reduction. Now, how do we represent oxidation potential and reduction potential? Now, for example, we are writing an oxidation reaction for a metal, which is basically losing how many electrons, beta G? N electrons. Okay, it is losing how many electrons? N electrons. So its oxidation potential can be written as E naught. Naught stands for standard. Okay, standard means measured at a temperature of 25 degrees Celsius, concentration of electrolyte as 1 molar and pressure 1 atm. Okay, so naught stands for standard. And if you want to write the oxidation potential, then it is basically written in subscript M hash Mn plus. Am I clear, everyone? Okay, in a similar way, yes, in a similar way, if you want to represent standard reduction potential, now reduction means gain of electrons, right? So Mn plus can gain N electrons and form metal M. So if you want to write the reduction potential corresponding to this is basically Mn plus to M. Am I clear? Fine. Okay, so you might have recapped what is reduction potential and oxidation potential, right? Now, if SOP is more, tendency of a substance to undergo oxidation is more. At the same time, tendency of a substance to reduce other substance is also more. Okay, right? That means that substance is basically what? It is strong reducing agent. Clear? It is strong reducing agent. Reducing agent is a substance which can cause reduction. So the one which undergoes oxidation can only cause the reduction of the other, right? Okay, so it is said to be strong reducing agent. Am I clear, everyone? Fine. Okay. Now, if more is the SRP, more is the tendency of a substance to undergo reduction, or we can say oxidize the other substance. Yes, oxidize the other substance. So that substance will what? That substance will be a strong oxidizing agent. Okay, so it will be what? It will be strong oxidizing agent. Is it clear? It will be strong oxidizing agent. Am I clear? So everyone, it is a strong oxidizing agent, right? So now we will be needing Hess law in order to understand how do we calculate electrode potential. Okay, so I'm just doing a quick recap of Hess law. So Hess law basically states that if you want to calculate the change in state function as in enthalpy is a state function. Now state function is the one which depends only upon initial and final state of the reactant. Okay, that means if you are taking a state function, right, state function does not depend upon the path. That means if you have initial reactant and final product same, right, so enthalpy change will be delta H only whether you take this path, whether you take this path, doesn't matter. Okay, so Hess law says that delta H, that is the enthalpy change for this path, is equal to that of this path, which is delta H1 plus delta H2, and it is also equals to that of this path, which is delta H3 plus delta H4. Am I clear? So we will be needing Hess law to understand that. Okay guys, is it clear? If clear, please give a thumbs up. If it is clear, please give a thumbs up. Clear? Okay, fine. Now, let's come to how do we calculate electrode potential. Now guys, standard electrode potential is calculated with the help of 3 parameters. Clear? First, it depends upon enthalpy of atomization or enthalpy of sublimation of transition element, which I have just told you are nearly same. Clear? ठीक है, right? At the same time, it depends upon the ionization energy, and at the same time, it depends upon what, guys? It depends upon hydration energy. Agreed? Fine. Now, see, you just have to answer a few questions, and once this topic is over, then only you can understand it better. So please be patient and listen to me very carefully without leaving the class. Okay. So now, if I talk about a metal solid, right? If this metal solid is getting converted into metal gaseous, we know that the enthalpy change for this particular process could either be your enthalpy of atomization, or it could either be your enthalpy of sublimation. Am I clear? It could either be enthalpy of atomization, or it could either be enthalpy of sublimation. Is it clear, everyone? And this energy is basically you have to give from outside. That means it is an endothermic process, or you can say that this is basically energy required. We always know that enthalpy of atomization or sublimation is energy required. Clear, everyone? Fine. Okay. Now, if you have to convert a metal in gaseous state to M plus in gaseous state, so here also you required which enthalpy or energy, beta? You basically required ionization energy. Okay, you basically required what? You basically required ionization energy. Am I clear, everyone? Fine. Similarly, if you have to convert M plus gaseous into M plus aqueous. Okay, so for this process, the energy which you required is basically your hydration energy, right? Okay, now ionization energy was the energy which you have to supply from outside. It's always endothermic. I've explained you in periodic classification. Okay, right? It's always what? It is always endothermic. That means it is energy required. Clear? It is energy required. Cool? Fine. And hydration energy is better released. It's always negative in sign. Am I clear? Hydration energy is what? It is basically energy released. Fine. Now, if you go directly from M solid to M plus aqueous, here the total enthalpy change is delta H total. Okay, this is the total enthalpy change. Am I clear? Now, by Hess law, okay, by Hess law, Rajay, delta H total is basically equals to delta A atomization plus delta ionization plus delta hydration, right? Okay, and you know, on the value of delta H total only your standard electrode potential, or you can say your standard reduction potential, basically depends. Am I clear, everyone? Am I clear, everyone? Okay, so your standard electrode potential, right? Standard electrode potential depends upon delta H total. Am I clear? It depends upon what? It depends upon delta H total. Clear, everyone? Okay, fine, cool. So now, listen to me very carefully, guys. Here, enthalpy of atomization is positive, ionization is positive, but hydration is negative. So the sum of these three could be positive or could be negative, right? Fine. And their sum gives delta H total, right? Fine. And on this delta H total, standard electrode potential or standard reduction potential depends. Right, because we measure usually standard reduction potentials only. So on this only SRP depends. How? It is an experiment, guys. It is definitely an experiment. You can't do anything. Experimentally, it has been found. Okay, fine, cool, guys. Now, one more thing. If hydration energy is more negative, na beta, then overall the negative term is more than the positive term. Right, like for example, the total positive is plus 20, but the total negative is minus 30. So minus 10 is delta H total, and more negative is delta H total, na beta. More negative is SRP. Keep this thing in mind. More negative is delta H total, more negative is SRP. Keep this thing in your mind. It's very important. Is this point clear or not? Yes. Is this point clear or not? Quickly tell me. Is this point clear or not? Quickly tell me in the chat box. Clear, everyone? Is this point clear? Yes, clear? Right? If clear, please tell me in the chat box. Clear, ma'am, clear. Okay, fine. Now, here this enthalpy change is when you change M solid to M2 plus aqueous. Now, what if you want to calculate electrode potential from change of 0 to +2? Then in that particular case, beta, the whole diagram will comprise one more step, right? Like for example, here you have metal solid. So in order to convert metal solid into metal gaseous, you basically required what? You basically requires enthalpy of atomization or enthalpy of sublimation, right? If you have to convert metal gaseous into M plus gaseous, so for that, you basically required first ionization energy, right? Okay. And if you want to convert M plus gaseous into M2 plus gaseous, you required second ionization energy. And in order to hydrate this, to get M2 plus aqueous, the energy which you will be requiring is hydration energy. Okay, so you might have to write this change if you are seeing for the change corresponding to M solid to M2 plus aqueous, right? If you have to go to M3 plus, then here you have to add one more ionization energy and so on. Okay, guys, fine. I hope this is understandable. Now let's move ahead. See, beta, you will see the SRPs of various elements, है ना, in 3D series. So if SRP, that is E naught Mn plus to Mn, comes out to be negative, right? We have studied more is a value of SRP, more is a tendency of a substance to undergo reduction. So here the SRP is negative. That means this Mn plus have very less chance to get reduced to M, right? That means, do you think that this particular change is possible? This reduction is possible? Answer is no, ma'am. Right? Answer is no, ma'am. Right? If this is not possible, that means what? Metal prefers to stay in plus n oxidation states, right? That means here plus n in that particular case will be stable oxidation state. Am I clear? Plus n in that particular case will be what, beta ji? It will be stable oxidation state. Am I clear, everyone? It will be stable oxidation state. Clear, everyone? Yes, clear? Okay, so if you are writing the SRP of many elements and if the SRP is negative, then metal in that N plus oxidation state is said to be stable. If this point is clear, give me thumbs up in the chat box. Yeah, stop chatting, bhai. Stop chatting, yaar. Stop chatting, guys. What you are doing, yaar? Please put your attention right here, na, guys. So what should be the answer? Is it clear? Clear or not clear? Is it clear? If it is clear, please give a thumbs up in the chat box. It's a very important point. If SRP is negative, then metal in N plus oxidation state is said to be what, guys? It's said to be stable, okay? It is said to be stable, right? So in that particular case, plus N is a stable oxidation state. Now, if you will look at, my dear students, the M2 plus to M, that means E naught reduction potential corresponding to M2 plus to M, we will see this table for 3D series. And if you will quickly look at it, you will get to see that the trends are very irregular, right? There is not a regular trend of standard reduction potential for M2 plus to M. Now, NCERT has asked this question, right? That why, guys, that why the trend is not regular. So the answer is, beta, your standard reduction potential depends upon delta H total, I've just told you, and delta H total depends upon enthalpy of atomization and ionization energy, and the trend of ionization energy and enthalpy of atomization is not at all regular for 3D series, right? So how delta H total and standard reduction potential can be, can be regular? Am I clear, everyone? Fine. So the answer is, beta, this irregular trend is due to irregularity in ionization energy and enthalpy of atomization. Now, my dear students, here, if you still want to observe a general trend. So you will see that from titanium to vanadium to chromium, right, to chromium, my dear students, right, to chromium, it is becoming less negative. However, in the case of manganese, it is becoming very highly negative. So if you will observe from titanium to vanadium to chromium, it is becoming less negative, but that means approaching near to zero. However, in the case of manganese, it is coming to be highly negative. So I think this is something which is not, as per the general thing which was going right here. We were trying to make something general out here, but this was very irregular, right? Similarly, when you are moving from Fe to cobalt to nickel, in the case of nickel, we observe that here it should be more negative when we are coming to, from first element to 8, 1, right? But here the decrease is only of, from copper to nickel of minus 0.3, right? And nickel is said to have the negative 1. Now, copper is said to have positive, which is again very weird. And in zinc, there is sudden increase and becoming very high negative from plus 0.34 to minus 0.76. So here, manganese, nickel, cobalt and zinc have very weird values if you will compare to rest of the elements. Clear? They have very weird values, everyone. Agreed? Okay, now why is it so? The question can definitely be asked. Okay, bhai, fine. So now, why everyone has a negative value of reduction potential, but copper has positive, right? Why it is so? Why it is so? Because beta, your delta H total, okay, your delta H total, guys, your delta H total is the sum of enthalpy of atomization, ionization and hydration. Now, if you are considering copper 2 plus, right? So here, first, copper solid were converted to copper gaseous, then to copper plus 1 gaseous by giving IE1, then to copper 2 plus gaseous by giving IE2, and then from copper 2 plus gaseous to copper 2 plus aqueous by release of hydration energy. So here if you will find delta H total, my dear friends, delta H total will be equal to what? Enthalpy of atomization plus first ionization energy plus second ionization energy plus hydration energy. Am I clear? Plus hydration energy. Is it clear, everyone? I think it should be clear. Now, in the case of copper, beta, the sum of enthalpy of atomization, first ionization energy and second ionization energy, it's highly positive. Highly positive comparative to hydration energy. So overall delta H total comes out to be positive. Now I have told you, if delta H total is negative, SRP is negative. Generally, there are exceptions. And when delta H total is positive, SRP is positive. So that is why in the case of copper, beta G, the SRP is said to be positive. Is it clear, everyone? Fine. Is it clear or not? Yes, is it clear or not? Quickly tell me in the chat box, guys. Clear? Perfectly clear? Okay, right? Therefore, E naught copper 2 plus to copper is positive. Fine. Everyone, is it clear? If clear, please give a thumbs up in the chat box. If clear, please give a thumbs up in the chat box. Okay, cool. Fine. Now, here, you can see this is basically enthalpy of atomization, and you can see the second and third, first and second ionization energy, not second and third, first and second ionization energy are really, really high in the case of copper. Okay, so that is the reason. Fine, that is the reason. Okay, that is the reason. Fine, that is the reason. Okay, guys, chalo. So let's just move ahead. Let's just move ahead. Yeah, E naught copper 2 plus to copper is positive, right? If it is positive, then copper 2 plus has a huge tendency to get converted into copper, right? This is possible. Fine. However, if this is positive, this is the reduction potential, beta, then the oxidation potential comes out to be negative. Yes, is it comes out to be negative? That means copper do not undergoes generally oxidation to copper 2 plus. Okay, this doesn't happen. That means copper have very less tendency to go into copper 2 plus. Clear? Right. So do you think this reaction is possible when metal reacts with acid, forms metal salt, forms metal salt by the release of H2 gas? Do you really think this reaction will be possible? Yes. Do you really think this reaction will be possible where copper is going from 0 to plus 2? Do you think? Yes. Do you think this reaction will be possible? Yes, everyone. Do you think this reaction will be possible? Answer is no. Why? Because copper has very less tendency to go from 0 to plus 3. That means copper cannot liberate hydrogen gas from acid. Am I clear? Copper cannot liberate hydrogen gas from where? From acid. Is it clear, everyone? Is it clear? Okay, if it is clear, please give a thumbs up in the chat box and a red emoji. If it is clear, please give a thumbs up in the chat box and a red emoji. Fine. Okay, now let's just move ahead. Let's just move ahead. We have also observed the trend was little bit irregular in the case of manganese, nickel and zinc. So why is it so? First, let's take manganese. In the case of manganese, the reduction potential is highly negative. And I have told you when the reduction potential is highly negative, right? Okay, so this particular oxidation state is said to be stable. Then only it is negative. I've just told you 2 to 3 slides back. Haven't I told you? Haven't I told you? Yes, ma'am, you have told us. Yes, ma'am, you have told us. Clear? Right. So if this is highly negative, why it is so? Because for manganese, plus 2 oxidation state is highly stable. Is highly stable. Why it is so? Why it is so? Because in the case of manganese 2 plus, manganese is said to have an electronic configuration of 3d5, which is half-filled stable electronic configuration. Am I clear? Which is half-filled. Yes, which is half-filled stable electronic configuration. Am I clear? This is half-filled stable electronic configuration. Is it clear, guys? Is it clear or not? Perfectly clear? Okay, fine. Now, in the case of nickel, the value is negative. Why? Here, the reason is hydration energy, beta. See, the reason could be stable electronic configuration also for being negative and hydration energy also. Clear? So, in the case of nickel, beta G, here, this is negative. That means plus 2 is stable oxidation state. Plus 2 is stable oxidation state. Yes, plus 2 is stable oxidation state for nickel. Right, fine. Okay. And why this is negative? Because of highly negative hydration energy. Okay. Because of highly negative hydration energy. Am I clear, guys? Now, in the case of zinc, again, this is negative. That means plus 2 is stable oxidation state for zinc. Yes, plus 2 is stable oxidation state for zinc. Yes, right. So, therefore, plus 2 is a stable oxidation state for zinc. And why it is a stable oxidation state, guys? What is the reason for this being the stable oxidation state? Answer is pretty simple, beta G. Here in zinc plus 2, you have a fully filled electronic configuration of 3d10. Okay, so this is a fully filled, stable electronic configuration. Okay, fully filled, stable electronic configuration. Am I clear, guys? Is this thing clear? Okay. If this thing is completely clear to you, please give a thumbs up in the chat box. Yes, please give a thumbs up in the chat box. Right. Meanwhile, we will do the NCERT reading. Okay. So we are doing the NCERT reading. Let's do the NCERT reading for this portion which we have studied. Okay, so NCERT states that copper has a unique behavior for positive E0 value which explains that why copper could not liberate hydrogen gas with acid. Why? Because copper have a very less tendency to go to +2. I've just explained you. ठीक है? Right? Fine. Now here, copper can not go to +2 oxidation state by merely reacting with acid. However, if you still want to do so, beta, you have to react copper with a strong oxidizing agent such as nitric acid and concentrated sulfuric acid. Then only the copper will get oxidized, and if copper will get oxidized from 0 to +2, the acid has to be reduced. Is it clear, everyone? Yes, is it clear? So they may give you assertion that here or they can give you statement 1. Statement 1 could be that copper 2 plus has a very less tendency to get converted to copper. Okay, right? Why? Because the E0 copper to copper 2 plus is negative. Statement 1. And statement 2, they will say that that is the only reason because of which copper do not react with acid. Right. So statement 1 is also 2 and statement 2 is also 2. And in statement 3 they are saying if you still want to convert from copper to copper 2 plus, what you have to do, you basically have to take a very strong oxidizing agent such as nitric acid or hot concentrated sulfuric acid. Then only these will oxidize copper to +2 and themselves get reduced. Clear? Okay, fine. Now here, why this can happen? This can happen because this high energy to transformation from copper to copper 2 plus is not balanced by hydration energy. Again, the same thing that here the hydration energy is less. However, the enthalpy of atomization and the sum of the first and the second ionization energy is higher. So hydration energy is not able to balance that positive value. Okay. So now the general trend towards the less negative E0 value is related to increase in sum of first and second ionization enthalpies. Already explained you. It is interesting to note that E0 values for Mn, nickel and zinc are more negative than expected, which I have already explained you. Why? Because for manganese +2, for nickel +2 and for zinc +2 oxidation states are stable. Is it clear, everyone? Is it clear, everyone? So we have read the NCERT also corresponding to the points which I have told you previously. Okay, so now let's come to the Mn3 plus to 2 plus reduction potentials. Okay, so now we are seeing the trends of E0, Mn3 plus or metal 3 plus to metal 2 plus trends. Okay, so these are also reduction potential but for different oxidations or reductions, right? For different reductions, right? This is corresponding to reduction of metal from +3 to +2. Previously we have done from +2 to 0. Okay guys, so for this also the reduction trend is being given to you. Now here when you will see the data, suppose this is the data, we don't have to cram the data. You don't have to cram the data. You have to learn few specific things. Like for example, for scandium 3 plus to scandium 2 plus, the reduction potential corresponding to this particular reduction is said to have a negative value. Right? If this is said to have a negative value, that means scandium 3 plus cannot get converted to scandium 2 plus. Agreed, everyone? Agreed, everyone? This cannot happen. This cannot happen. Why? Why this cannot happen, beta G? Because E0 scandium 3 plus to scandium 2 plus is negative. Okay, is negative. So when the reduction potential is negative, the tendency of reduction is not possible. Is it clear, everyone? Is it clear, everyone? Fine. Okay. However, if you have to do the reverse process, that means if you have to consider the oxidation potential. So if you will consider E0 scandium 2 plus to scandium 3 plus, the value is plus 0.37 volt, right? Now, since the oxidation potential is positive, that means scandium 2 plus has a huge tendency to get oxidized to scandium 3 plus by a loss of 1 electron. So, the chances of this oxidation is very high, right? Okay, so chances of this oxidation is very high since scandium 2 plus is undergoing oxidation beta. So the one which is undergoing oxidation act as what? Act as reducing agent, right? Therefore scandium 2 plus act as a strong reducing agent. Okay, it acts as a strong reducing agent because oxidation corresponding to 2 plus to 3 plus is high. Okay, am I clear, everyone? Is it clear? If this point is clear, please give a thumbs up in the chat box. Okay, so they will ask you why scandium 2 plus act as a reducing agent. So is it clear, guys? Yes, is it clear? Fine. Now, similarly, beta, they will say that reduction potential corresponding from manganese from +3 to +2 is highly positive. Okay, is highly positive. That means Mn3 plus has a huge tendency to get reduced to Mn2 plus. Yes or no? Yes or no? Yes. If it has a huge tendency to undergo reduction, then it acts as a strong oxidizing agent. Am I clear? It acts as a strong oxidizing agent. Okay. It acts as a strong oxidizing agent. Clear? It acts as a strong oxidizing agent. Is it clear, everyone? Yes. Is it clear, everyone? Perfectly clear? Perfectly clear? Okay, fine. Now, similarly, you have chromium 3 plus to chromium 2 plus. Here it is saying the reduction potential is negative, right? So, if reduction potential is negative, then +3 is said to be the stable oxidation state for chromium. But you will say, ma'am, in chromium, if you have chromium +3, the electronic configuration for chromium +3 is 3d3. So 3d3 is definitely not a stable oxidation, stable electronic configuration, right? So 3d3 is definitely not a stable electronic configuration. Then why for chromium +3 is said to be a stable oxidation state? So the answer is beta, +3 stable oxidation state for chromium in aqueous solution. In aqueous solution, chromium is basically forming a coordination complex with water. Okay, so it is basically existing in such a form, right? So whenever metal ion or metal atom is surrounding by ligands, the 5d orbitals are no longer degenerate. They split up into two sets of orbital. Clear? Right? They split up into two sets of orbital. Am I clear, everyone? Fine. Okay. That means here, if I consider the 5d orbital, fine. Here, if I consider what? The 5d orbitals, which are 3dxy, 3dyz, 3dxz, 3dx square minus y square, and 3dz square. Okay, so first all these 5 orbitals were degenerate. Degenerate means all of them were said to have equal energy, right? They were said to have equal energy, but as soon as they come in a contact of a ligand, right, you will study in coordination complex. Now just try to cram it, but later on you will understand it. So here the 5d orbitals will undergo splitting, right, in two sets. One set is of axial orbitals. Now we know that the axial orbitals are dx square minus y square and dz square. And the second set is basically non-axial orbitals. Okay, the second set is basically non-axial orbitals, which are dxy, dyz, and dxz. Is it clear, everyone? Fine. Okay. This set is basically known as T2G, and this set is basically known as EG. Now you have 3 electrons. T2G is of lower energy, EG is of higher energy. Clear, everyone? Okay. So first we fill the electrons as per Aufbau principle. That means first the lower energy one is filled, then the higher energy one will fill. So here first 3 electrons will come here. Okay. That means T2G 3, it is a half-filled configuration, and T2G3 is a stable electronic configuration. Okay, so this is a half-filled configuration, and T2G3 is considered to be stable electronic configuration in coordination complexes. Clear, everyone? Why? Because it is half-filled, symmetrical. Okay, guys, is it clear? Is it clear? Yes, is it clear? Everyone, is it clear or not? Quickly tell me. Fine. So due to T2G plus 3 is a stable oxidation state for chromium in aqueous solution. Is it clear, everyone? Fine. Okay. Let's just move ahead. Is it clear? If clear, please give a chat and thumbs up in the chat box. Please give a thumbs up in the chat box or a red heart. Clear? Okay, fine. So now let's just move to the next point. Beta, the electrode potential for Mn3 plus to 2 plus is highly positive, as well as for cobalt 3 plus to 2 plus is again highly positive. If the reduction potential is high, the tendency of them to undergo reduction is high, and to oxidize the other substance is also high. That means here manganese 3 plus and cobalt 3 plus, they act as what? They act as strong oxidizing agent. Am I clear? They act as strong oxidizing agent. Perfectly clear, guys? Okay, fine. Chalo. Let's move ahead to the next point. If you will see the reduction potential corresponding to titanium, vanadium and chromium from +3 to +2, the values are highly negative. So if you will write the oxidation potential, the values will be positive. Okay, so it will be plus 0.37. It will be plus 0.26. Okay, fine. And this will be plus chromium 2 plus to chromium 3 plus. So oxidation potentials are high. That means they have a huge tendency to undergo oxidation and to reduce the other substance as well, right? So that means here titanium 2 plus, vanadium 2 plus and chromium 2 plus, they act as, yes, they act as what? They act as strong reducing agents. Am I clear? They act as strong reducing agent. If this thing is clear, please give a thumbs up in the chat box. Yes, if this thing is clear, please give a thumbs up in the chat box, guys. Clear? Perfectly clear? Okay, fine. Let me have a sip of water. Meanwhile, you just read the NCERT lines very quickly. Then we will solve few questions. Okay. So here are the few lines of NCERT. Okay, here are the few lines of NCERT, guys. You can quickly read them. These are based on the points which I've explained you in the previous page. Fine. So the very first line is that on examination of this table, right, we get to see that scandium is said to have a very low value of reduction potential. True, it is said to have a very low negative value. And since the reduction potential is negative, that is why scandium 3 plus is a stable electronic configuration, stable oxidation state. And why it is a stable oxidation state, that I have already explained you, because it has an electronic configuration of a noble gas, which is argon. Perfect, everyone? Okay, then if I'll see the values, okay, the values is highest for zinc. Okay, why? Because for zinc, when you will remove the electrons, 2 electrons, you will get 3d10 configuration. Absolutely correct, right? If you will just look at the reduction potential corresponding from Zn, 2 plus 2 Zn, it is highly negative. Why? Because plus 2 is a stable oxidation state for zinc because of fully filled 3d10 electronic configuration, which I have already explained you. But I am reading the lines of NCERT so that you can understand. Okay. Then here manganese again have high value. Okay. Why it is said to have a very high value? Guys, why it is said to have a very high value? The answer is pretty simple. Because manganese plus 2 is a stable oxidation state. Right? And for Fe, the value is less. Okay? For Fe, the value is less. Why for Fe, the value is less? Guys, why for Fe? See, this is for manganese. It is highly positive. Right? Okay. Why it is highly positive? Because Mn plus 3 has a huge tendency to get converted to Mn plus 2. Why? Because Mn plus 2 is 3d5. So that is why the value is highly positive. But for Fe, it is less positive. Why? Because here, in the case of Fe, plus 3 oxidation state is more stable. It is 3d5. Right? So it is a very less tendency to get converted to plus 2, which is 3d6. Clear? So the same thing they have written it right here, that the comparatively high value of manganese show that Mn plus 2 is stable, right? And that is low for Fe because Fe in plus 3 oxidation state is already stable due to D5 configuration. Okay, right. Now, chromium in aqueous state has half filled T2G. That is why it is stable. And same is applicable for vanadium, vanadium 2 plus. Right. Now, vanadium 2 plus is also has half filled T2G in aqueous solution. Right. So, vanadium 2 plus is also stable. Why? Because of similar electronic configuration as chromium of T2G3. Clear, everyone? So we have studied all these points already. We have just read our NCERT to get it more clear and to cover each and every point. Because see, you can't write every point, but you can squint NCERT lines very easily. So that is why I keep on doing that. Clear? So till here, if everything is clear, right, in the case of electrode potential, this topic is over. Please give me thumbs up. Now I am proceeding towards the questions. If it is clear, please give me a thumbs up. I am proceeding towards question. Now here, which is most stable oxidation state in aqueous solution? So beta, in aqueous solution, vanadium 2 plus is stable, right? Why? Due to T2G3. And chromium 3 plus is also stable. Why? Due to T2G3 configuration. So answer is option number D. Am I clear? Answer is option number D. Clear? Let's move to the next question. Now, this is a question from NCERT only. I have just made this question from NCERT. The question is the E0 Mn2 plus to M values for copper is highly positive. I have just explained you. What is the reason? The reason is copper is said to have high values of enthalpy of atomization, ionization energy, and low value of what? Low value of hydration energy. So the answer is option number B. Am I clear? Answer is option number B. Fine. Let's move ahead, guys. Let's move ahead. Next. E0 Mn3 plus to Mn is positive. Absolutely correct. Then chromium 3 plus to chromium. Yes, guys. Is it true? Is it true? Right? Definitely true. See, if you will see Mn3 plus to 2 plus for manganese, it is this. Highly positive. And from chromium, it is highly negative. Absolutely correct. Why? Because manganese plus 2 is stable and for chromium plus 3 is stable. So manganese wants to grow from plus 2 to plus 3 And chromium does not want to go from +3 to +2. Why? Because for chromium, +3 is actually stable. Why? Due to half-filled T2G. Right. So that is why the statement 1 is definitely true. Clear? Now the statement B, that the third ionization energy of manganese is larger than chromium. Yes, the third ionization energy of manganese is higher than chromium. Is it true? Beta, it's true. Why? Because if you have to remove third electron from manganese, right, you have to remove it from 3d5. Okay, right, fine. So this is definitely high. Whereas for chromium, you have to remove the electron from 3d3, which does not, from 3d4, which does not require that much amount of energy. So this line is also true, right? This line is also true. Okay, third ionization energy definitely of manganese is higher than chromium for sure. Why? Because in manganese, electron has to be removed from d5. Perfect, everyone. Right? So both the statements are said to be what? Both the statements are said to be correct. Next. So you have to give the correct order of increasing oxidizing power. So beta see, here this is the question of NCERT. In MnO4 2 minus, manganese has +7 oxidation state. Here chromium has +6, and here you can easily see that vanadium is said to have +3 oxidation state. You can calculate oxidation number by yourself, right? So left to right as you're moving, the oxidation state is becoming higher, and the higher oxidation state has more tendency to lower itself or to undergo reduction, right? That is why the one which is having higher oxidation state is having higher chances to undergo reduction, and hence it is said to have higher chance to act as oxidizing agent, or it has more oxidizing power. Clear? That means this is absolutely correct. Fine. Then beta G, oxidizing power of cobalt 3 plus is more than Mn3 plus. See, reduction potential of cobalt 3 plus to 2 plus is more than Mn3 plus to 2 plus. So since the reduction potential is more, cobalt 3 plus has more tendency to undergo reduction. So it has a better chance to act as an oxidizing agent. That means this is also true. And chromium in +6 is definitely oxidizing, then molybdenum and tungsten +6. That means C is also correct. Right? So what will be the answer? Answer is all of these, right? So I think you must be enjoying the process, right? Where you're covering all the NCERT in text, questions, NCERT's important lines, everything is getting covered. Okay, slowly. Fine. So now let's move ahead, guys. Let's move ahead. Now, chromium 2 plus is oxidizing, but Mn3 plus is reducing in nature. Apart from the fact, both of them have D4 configuration. See beta, if you have chromium 2 plus, it is having 3D4 configuration, right? It has a huge tendency to get converted to +3. Why? Because it will have 3D3 and it can have T2G3 configuration. Clear, everyone? Fine. So that means it has a huge tendency to undergo oxidation, right? So it will act as what? Reducing agent. Fine. And if I talk about manganese, if it is present in +3, the configuration is 3D4, similar to chromium 2 plus. So beta, it has a huge tendency to gain one electron and get converted to Mn2 plus. Why? Because here Mn2 plus has 3D5 configuration. That means it has a huge tendency to undergo decrease in oxidation number or reduction. If it has a huge tendency to undergo reduction, it basically act as oxidizing agent. Clear, everyone? Fine. So here chromium in +2 and manganese in +3. The question is saying it is a previous year question of NEET 2023 or 22, right? Might be, I guess, 23. Fine. So it is a question of NEET 2023 or 22. I'm not sure. Clear? Fine. So this question was asked, right? That both are said to have D4 configuration, right? Fine. However, chromium 2 plus is reducing agent and manganese 3 plus is reducing agent. Why? Beta G, because here the electronic configuration of chromium changes from D4 to D3. Okay, so it is changing from D4 to D3 and D3 is said to have T2G3 configuration, which is highly stable, right? So answer is what? Answer is basically option number A. Clear everyone? Yes, is it clear? Perfectly clear? Okay, chalo. Let's move ahead, guys. Let's just move ahead. Next question on your screen is, the set of correct statements is, first, manganese exhibit +7 oxidation state in its oxide. It is true. You will study this point in upcoming slides. It is true. Ruthenium and osmium has +8 oxidation state. True. Scandium shows +4 oxidation state. Aha, scandium can maximum show only +3 oxidation state. Chromium is oxidizing agent in +6 oxidation state. Absolutely true. Right. So first, second, and fourth is true. So the answer is basically option number B. Is it clear? Answer is basically option number B. Fine. Chalo. Let's move ahead, guys. Let's move ahead. Fine. Now here, one more NCERT in text question, which we have to discuss basically right here. Why E0 for Mn3 plus to Mn couple is much more positive than chromium 3 plus to 2 plus and Fe3 plus to 2 plus. Yeah, see, this is positive because Mn has a huge tendency to get converted from +3 to +2. Why? Because in +2, Mn has 3d5 configuration. So this is one of the reasons that it is said to be highly positive. Okay, so that is the reason that E0 Mn +3 to Mn is highly positive. This is one of the reasons. Okay, and the second reason which is mentioned in NCERT is that, bacha, here the third ionization energy in the case of manganese is much higher. Why? Because you have to eliminate electron from D5 configuration, na? Agreed? Okay, so third ionization energy is very higher, right? And if third ionization energy is higher, that means the positive part in delta H total is higher, and when delta H total comes out to be positive, the E0 itself comes out to be positive. Fine. So in NCERT, the reason for that is written is higher ionization energy for manganese. Is it clear, guys? Yes. Is it clear? Fine. Okay. Chalo. Let's move ahead, beta ji. So now here we have completed how many properties in total? We have completed in total, I guess, 8 properties, right? So now it comes to 9th property. Oh, wait, yaar, where are you going? So now, 9th property is basically trend and stability of higher oxidation state. Am I clear? Right? Fine. 9th property is trend in stability of higher oxidation state. This is 9th point. Okay, this is point number 9. You just note the heading. I am having a sip of water here. Now, let's come to trends in stability of higher oxidation states. Now, beta, generally in 3D series, the higher oxidation states are stable either in forms of oxides or fluorides. Like for example, manganese is said to have an highest oxidation state of +7. Now, this +7 is stable. Okay, this +7 is stable in its oxide. Now the answer is why the higher oxidation states of 3D series are stable either in form of their oxides or halides. So what is the reason for that? What is the reason for that, beta? The reason is fluorine and oxygen. Okay, fluorine and oxygen, both of them, my dear students, both of them are said to have small size. Okay, they are said to have what? They are said to have small size and high electronegativity. And whenever size is small, we know that lattice energy is inversely proportional to size. So when size is small, that means lattice energy is high. And if lattice energy is high, that means what? Beta G. It is said to be stable. And if it is said to be stable, the bond dissociation energy ultimately is said to be higher, right? That means lattice energy is high and bond dissociation, bond dissociation, bond dissociation energy is also high, okay, is also high. So due to high bond dissociation energy and lattice energy, these oxides and fluorides are highly stable. That is the reason that usually higher oxidation states in 3D series is exhibits by the elements either in their oxides or in their fluorides. Clear? Right? Now, generally, we say that higher oxidation states are exhibited in fluorides and oxide. However, the oxides has a greater ability to stabilize higher oxidation states than fluorides, right? That means if you will see manganese, it can forms oxide in a higher oxidation state, which is Mn2O7, right? Where the oxidation state of manganese is +7. However, it is, if I have to consider its halide, or I should say its fluoride, so the maximum oxidation state of +4 only can be seen in fluoride. Are you getting my point? That means in oxide, generally manganese can show higher oxidation state, but not in fluorides. That means ability of oxygen to stabilize the oxidation state in oxides exceeds that of fluorine to stabilize fluoride. Right? Why it is so? The reason is beta, oxygen can form multiple bonds. Right? Right? Why? Because oxygen, because oxygen has a tendency to form multiple bond. Okay, oxygen has a tendency to form what? To form multiple bond. Am I clear? To form what? To form multiple bond. Clear, guys? It has a huge tendency to form what? It has a huge tendency to form multiple bond. Am I clear? Right? Now, what do you mean by this, beta? See, listen to me very carefully. If you will consider Mn2O7, okay, if you will consider what you will consider Mn2O7, its structure looks like this. MnO, Mn, double bond O, 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 double bond O. So oxygen can form lots and lots of multiple bonds, but fluorine can form only single bonds. So if oxygen can form more number of bonds, right, so definitely in its compound, the central element can exhibit higher oxidation states. Clear? So that is the reason stability of higher oxidation state in oxides is more than halides. Okay, fine, it's more than halides. Clear, everyone? Fine. Now here the question is given, why oxygen is superior to fluorine in stabilizing the higher oxidation state? You tell me what should be the answer. Yes, quickly tell me what should be the answer. Yes, guys, what should be the answer? What should be the answer? A, B, C, D. Just told you. What should be the answer? A, B, C or D? Quickly tell me. Absolutely correct. C. Right? Oxygen has ability to form multiple bonds with metal. Okay? It has a ability to form multiple bonds with the metal. That is the reason here oxygen is superior in stabilizing the higher oxidation states. Is it clear, guys? Yes. Is it clear, everyone? Perfectly clear? Perfectly clear? Okay, fine. Let's just move ahead. Let's just move ahead. Now, this question has also been asked in NCERT, that why Mn2O7 is possible, but MnF7 is not possible, right? Although fluorine is more electronegative than oxygen. The answer is pretty simple, yaar. MnO2 is possible because here oxygen can form multiple bond, right? And here around the manganese, the steric hindrance will also be less, right? Why? Because here you have around both the manganese only in total 4 oxygen atoms surrounding. How many in total? 4 oxygen atoms surrounding. That means here steric hindrance is less. Steric hindrance is less. Okay, steric hindrance is less. However, if you will think the same for MnF5, beta, here 7 fluorines will be surrounding a single manganese, so steric repulsion will be so much. So you can even take this logic also, that why MnF7 is not possible. Clear, everyone? Okay, one is fluorine cannot form multiple bond. Second is there will be steric hindrance when 7 fluorine will surround manganese. Am I clear, everyone? Am I clear, everyone? Okay, fine. Okay, chalo. Let's just move ahead. Let's just move ahead, everyone. So now, if this much is clear, please give a thumbs up in the chat box. I'm being a little quick because I just want to complete all the properties and give you a break as soon as possible. If this thing is clear, please give a thumbs up in the chat box. Yes, I want to complete all the properties by 12 and then give you a break of 10-15 minutes. So please tell me, if this thing clear, please give a thumbs up. Hearts, thumbs up, anything to express that this thing is clear to you guys. Okay, fine, clear? Yes, clear? Perfect, 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 perfect. Okay, 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 clear. Fine. So now, here in NCERT, they have given a table like this, in which they have shown all the possible halides. You don't have to cram it. You just have to listen what I am saying. You don't have to cram this. Okay, you do not have to cram this. You just have to listen to me. That's it. Okay, guys, fine. Now, here, in the case of titanium, okay, we are starting the formation of halides. Scandium is not given because scandium hardly forms any halides. So we are starting this table from titanium. Now titanium can show +2, +3, +4 oxidation states. So here all the halides of +4, +3 and +2 are given. Am I clear? Okay, guys. Now here, if it has been written only X, so that X could be, am I clear? That X could be from fluorine, chlorine, bromine to iodine, anyone. Clear, everyone? Okay. But here it has been written X triple dash. Triple dash means that X could only be chlorine and iodine. Okay, everyone. So are you getting my point? So if they are writing X, then it could be fluorine to chlorine to bromine to iodine, anyone. But if they are writing triple, then it could only be chlorine or iodine. Is this point clear to you guys? Okay, right? Fine. Now, similarly, vanadium can form halide in pentavalent state because it can form all the oxidation state from +5 to +2, right? Okay. So, in pentavalent state, guys, it can form only fluoride, right? That means only VF5 is possible. VCl5 is not possible. Why? Because sterically, 5-chlorine around the vanadium will actually results into lot of steric hindrance. Am I clear, everyone? If you will have 5-fluorine around vanadium, it will result into lot of steric hindrance. That is why VF5 is actually only possible. VCl5 is not possible. Clear, everyone? Right? In +4 oxidation state, V dash, X dash 4 is possible. Now, X dash means halogen could be fluorine, chlorine and bromine, but not iodine. Then VX3 and VX2 are possible. That means here X is written. So fluorine, chlorine, bromine, iodine, all of them can form VX3 and VX2. Clear? Similarly, chromium in +6 can only form fluoride, and +5 also can only form fluoride. Okay, right. In +4, it can form fluoride, chloride, bromide, iodide. Similarly, in +3 also and in +2 also. Manganese can form fluoride in which its oxidation state is maximum of +4 is MnF4. Okay, so in fluorides, manganese can have a maximum oxidation state of +4 only. However, if you want manganese to exhibit its possible maximum oxidation state, which is +7, then that is only possible in oxyfluoride, which is MnO3F. Okay, so in oxyfluoride only, right, in oxyfluoride only, manganese can show the +7, which is its highest oxidation state, not in fluorides. Okay, it can show only where? Only in oxyfluorides. Am I clear, everyone? Okay. Now, similarly, Fe can form halides either in +3 or in +2, because these are the only two stable oxidation states in the case of Fe. Right? Fine. And cobalt can also form in +3 and +2. Nickel can form in +2. Copper can form in +1 as well as in +2. And zinc can form in +2. Now, only those halides are written which are sterically stable. Clear? Right? Okay. Fine. Is it clear, everyone? Is it clear? Fine. Chalo, let's just move ahead. Let's just move ahead. So now, let's just quickly squint the NCERT written below to this table. Let's just quickly squint the NCERT. The highest oxidation state is achieved in TiX4. Absolutely correct. So in TiX4, we can say that titanium exhibits +4 oxidation state, which is its highest. Vanadium is exhibiting its highest oxidation state, which is +5 in VF5. And chromium is exhibiting its highest oxidation state of +6 in CrF6. Okay, right? So here these are those compounds in which, as halides, your 3D elements can have stable oxidation state. Am I clear, everyone? Fine. Further, Mn cannot form +7 oxidation state in its halide. However, in its oxyfluoride, which is MnO3F, manganese can show +7 oxidation state. Okay, fine. And after manganese, beta G, only Fe and cobalt can form trihalide and have an oxidation state of +3. Right, matlab after manganese, hardly, high oxidation state, which is +3 is possible, and that also only in the case of whom? That also only in the case of FeX3 and COF3. That's it. Clear? Right? Fine. Further, ability of fluorine to stabilize higher oxidation state is due to higher lattice energy. Already told you. Right? So, in the case of COF3, right? Since +3 is a higher oxidation state of cobalt, so it is getting stabilized in the form of fluorides only, right? Cobalt is said to exhibit +3 oxidation state only in fluorides. Beta, why? Because I've just told you fluorine and oxygen both have high tendency to stabilize higher oxidation state, and the highest possible oxidation state in the case of cobalt is +3 only. Am I clear, everyone? Okay, that is why here it is forming only fluoride. Fine. Okay. Further, similar things applies in the case of whom, beta G? In the case of VF5 and CrF5. Okay, they are also forming the higher oxidation states only in the case of their fluorides. Why? Because higher oxidation states can only be stabilized in the form of fluorides. Am I clear? Fine. Okay. Let's move ahead to the next important point. So next point written in the NCERT is that although vanadium +5 is forming VF5, but it is not forming the other halides, right? That means here in VX5, right, X could only be fluorine. It could not be chlorine, bromine or iodine. If VCl5, VBr5 and Vi5 has been formed, beta, they are not stable. Okay, what I am saying that VCl5, VBr5 and Vi5, okay, and Vi5 are unstable. So they are not formed. Why they are unstable? Because they undergo hydrolysis to form VOX3. Okay, so they have a chance to form oxyhalide, right, by undergoing hydrolysis. That is why VCl5, VBr5, Vi5 do not exist. Clear, everyone? Okay, fine. Now, here, in the case of VX2, guys, VCl2, VBr2, Vi2 exist. However, VF2 is unstable, so do not exist. Why it do not exist? Answer is pretty simple. Fluorine stabilize only higher oxidation states, not lower oxidation states. And here vanadium is said to have a lower oxidation state of +2. Is it clear, everyone? Is this point clear? Beta, you have to learn all these points. Once you will read it now, you will never forget them, for sure. But you need to learn and read them. Okay. So is it clear, guys? Yes. Is it clear? Clear, 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 clear? Pretty clear? Okay. So this is basically the table of oxides formed by transition elements. Again, you don't have to remember the oxides, their formulas. No. You just need to remember the oxides from scandium till manganese, which are present in their highest possible oxidation state. Okay. Like for example, scandium forms highest oxidation state oxide, which is Sc2O3, where its oxidation state is +3. Titanium forms TiO2, where its oxidation state is +4. Vanadium is forming V2O5, where its oxidation state is +5. Clear? Chromium is forming CrO3, where its oxidation state is +6. Okay, and manganese is forming Mn2O7, where its oxidation state of +7. So can we say that in the case from scandium to manganese, right? Okay, the oxidation state which they have in their oxides are coinciding their maximum oxidation state, or they are coinciding the group number, or we can say their maximum oxidation states are coinciding the group number. Like scandium belongs to third group, titanium belongs to fourth, vanadium belongs to fifth, chromium belongs to sixth, and manganese belongs to seventh. Right, everyone? So can we say that their highest oxidation states are coinciding with the group number? Yes. Can we say that their highest oxidation state is coinciding with group number? Can we say this? Yes, ma'am, we can say this. Right? This is the most important point. Once it has been asked in NEET exam. That is why I'm making you write. Clear, everyone? Is it clear? Clear? Absolutely clear? Okay. Fine. Now, let's just move ahead here. Few more questions of NCERT. Now we are discussing it. Right? We're discussing few more questions of NCERT. Question is that why all copper second halides are not iodine. So in CuX2 dash, right, X could be fluorine, chlorine, bromine, but not iodine. Why CuI2 is not possible? Beta, the reason is if CuI2 will be existing, then in CuI2, copper will be present in +2, iodine will be present in -1. And iodine in -1 is a very strong reducing agent, right? It is a very strong reducing agent. Okay, fine. So it will basically reduce copper 2 plus to copper +1 and itself undergoes oxidation to I2, right? And here copper 2 plus is an oxidizing agent. So that is the reason CuI2, that is the reason CuI2 does not exist. Am I clear? That is the reason CuI2 does not exist. Clear everyone? Fine. Okay, so we are doing in the form of questions because it becomes easier to remember. Fine. Okay, further everyone. Here we have seen that copper +1 is more stable than copper +2 in their gaseous state. Why? Why everyone? Why? Because in gaseous state, copper +1 is said to have 3D10 configuration and copper 2 plus has 3D9 configuration. Since 3D10 configuration is more stable, right? So that is why in gaseous state, +1 oxidation state of copper is more stable than +2. Clear everyone? However, in aqueous state, it is vice versa, right? In aqueous state, copper 2 plus is more stable than copper +1. Why? Because we know that hydration or the extent of hydration is directly proportional to charge. Right? It is directly proportional to charge. More is the charge, more is the extent of hydration. So copper 2 plus is said to undergo large extent of hydration. That means large amount of hydration energy is released. And whenever the energy is released, the stability is attained. Am I clear? Whenever the energy is released, stability is attained. Clear everyone? Fine. Okay. Right. So here, due to high hydration energy, copper 2 plus is more stable than copper +1. Right. So when copper changes to copper plus, first ionization energy is required. Copper +1 changes to copper 2 plus, second ionization energy is required. And when copper 2 plus changes into from gaseous to aqueous, hydration energy is released. Okay, so this is positive, right? However, this is highly negative. This is highly negative. And this is less positive. So overall, when this process happens, energy is released. Clear? And if energy is released, stability comes. That is why copper 2 plus is more stable than copper +1. Now on the same concept beta, the question has been asked in NEET 2023. What was the question? The question was why copper 2 plus is more stable than copper +1 in aqueous solution. The reason is due to high hydration energy. Right? What is the reason? The reason is due to high hydration energy. Am I clear everyone? Yes. Am I clear everyone? Okay. Beta, next break will be after 11:30. No more break before that. It's for your welfare only. I am also tired, but it's for your welfare only. Okay? Fine. Chalo, let's just move ahead. Now, you only tell me what should be the answer of this particular question. It has been asked in JEE Mains. The question is an assertion reason question. So the assertion here is copper 2 plus in water is more stable than copper plus. So they are saying that in aqueous solution, copper 2 plus is more stable than copper plus. Okay, right, fine, they are saying this. Cool, everyone. Reason they are saying enthalpy of hydration of copper 2 plus is much less than copper. This is false. Why? Because the hydration energy for copper 2 plus is higher than copper +1. Clear everyone? Clear everyone? That means here assertion is true, but reason is false. So A is correct and R is incorrect. So answer will be option number B. Am I clear, everyone? Answer will be option number B. Cool? Fine? Okay? Chalo, let's just move ahead, guys. Let's just move ahead. Let's just move ahead. Don't worry. We are soon about to complete the properties. So then we will start with the compounds of transition elements. Before that, I will give you a break. Before that, no break. Why? Because if you will take more number of break, beta, the duration of the marathon gets extended. I want to make you guys free till 2 or 2:30. Fine. So please support me. Okay, everyone? Fine. Chalo, let's just move ahead. Let's just move ahead. Now, let's come to some important points of NCERT. Fine. Fine. So I am just writing in short. Later on, I will read the full paragraphs also. But now I am writing in short. Okay. So it is about the oxides and oxoanions of metal. Right. So NCERT, this is basically your property number, I guess. This is property number, I guess. Just a second. So we have done your property number. Oh, wait. So we have done, just a second, guys. So we have done till property number, just a second, 9 na. So this is property number 10. Okay, this is property number 10. Oh. Property number 10, which is regarding the oxides and oxoanions of metal of 3D series. Am I clear, everyone? Fine. So here, if I talk about all the possible oxides which 3D elements can exhibit, I am considering specifically manganese, chromium, and vanadium. Clear? So here, manganese can form all these sets of oxides. Talking about the oxidation state in MnO, okay, in MnO, the oxidation state, in MnO, the oxidation state of manganese is +2. In Mn3O4, it is +8/3, you can calculate it, right? How? If you will consider the oxidation state of manganese as X, so it will be 3X plus 4 into -2 equals to 0. Okay, so 3X is equals to +8, right? So X comes out to be +8/3. Okay, guys, fine. So here the oxidation state is +8/3. Fine. Here the oxidation state is basically +3. Okay, right, fine. Here the oxidation state is +4 and here the oxidation state is +7. So what we are saying that left to right, the oxidation states are getting increased. Fine. Okay, so left to right, the oxidation states are getting increased. Now, my question to you guys, you have studied Fazan's rule. You have studied Fazan's rules, everyone. So what does the Fazan's rule says? It says that if the central cation, like there was manganese, has higher oxidation state or has higher positive charge, its polarizing power is more. Now, what is polarizing power? Polarizing power is an ability of a cation to distort the electron cloud of an ion. More is the polarizing power, right? More is the distortion caused in the ionic bond and results into the more covalent character in ionic bond. Am I clear, everyone? Fine. So if the central atom has higher positive charge or oxidation number, its polarizing power, guys, its polarizing power is more, and then more polarization occurs in the ionic bond, right? So there results into more covalent character in ionic bond. Am I clear, everyone? Fine. Okay. Cool. Perfectly clear. Right. So now here, left to right, oxidation state is getting increased. So the polarizing power of the central cation is getting increased. Right? Fine. So what is happening here? The covalent character in the ionic bond increases. right? That means left to right, covalent character increases. Yes, left to right, covalent character increases. However, ionic character decreases. Am I clear? Ionic character decreases. Is it clear, everyone? Yes. Is it clear? Perfectly clear or not? Perfectly clear. Right. Now further, beta, here I am again writing the oxidation states. Okay, I have already told you how to find. I am again writing the oxidation states right here. So now listen to me very quickly. More is the positive charge of the central atom. More is the Lewis acidic character, or more is the acidic strength. We have already studied it. Right, because more is a positive oxidation state. That means more is the electron deficiency. And the one which is said to have the more electron deficiency, it's said to be a good Lewis acid. That means left to right, what is happening, everyone? Left to right, Raji, what is happening? Acidic character is basically getting increased. Yes, left to right. Acidic character is basically getting increased. Acidic character increases right here. Agreed, everyone? Acidic character increases right here. Fine. Okay. So if acidic character is increases, that means the very first oxide is basic. And the last oxide is basically acidic. And the middle ones are said to be amphoteric. Now, amphoteric are the one which can react with both acid and base. Clear? Okay. So this is also amphoteric. Clear? This is also amphoteric. And this is also amphoteric. Clear? Fine. In a similar manner, you tell me what will happen in these cases, left to right. Will the acidic character increases or decreases? Yes. Is the acidic character increases or decreases? Quickly tell me, everyone. Pretty simple. Here, in CRO, the oxidation state of chromium is +2. In Cr2O3, it is +3, and CrO3 is +6. Right? So again, left to right, acidic character increases. Okay, left to right, acidic character increases. Am I clear? Fine. So that is why this is basically acidic. Fine. The left one is basic. And this is amphoteric. Am I clear? This is what? This is amphoteric. Now, in the case of vanadium beta, here, this has +3 oxidation state, this has +4, and this is +5. Actually, the thing is, in the case of vanadium, none of the oxide is acidic. Clear? None of the oxide is acidic. Either they are basic or amphoteric. Clear? So, V2O3 is basic. V2O4 is less basic according to NCERT. And V2O5 is amphoteric. Clear? It is amphoteric. Clear, everyone? It is what? It is amphoteric. Since it is amphoteric, it can react with both acid and base. Okay? Since amphoteric can react with both acid and base. Now, I will use this point in upcoming pages that it can react with both acid and base. Clear everyone? Fine. I will use this point further ahead that it can react with both acids as well as base. Okay. So this is important lines of NCERT who's squinting. We will do right now. Fine. Here. All these oxides which we have studied previously are basically formed by the reaction of metal and oxygen at high temperature. Clear? Fine. That means metal reacts with oxygen at high temperature to form metal oxides, which we have studied in the previous pages. Clear? Right. All can forms metal oxide of the type MO except scandium. Scandium cannot form SCO. Why? Because +2 oxidation state is not stable for scandium. So that is why they have written all metal except scandium can form oxides of the type MO. Clear? Right. Fine. The highest, all these oxide of the type MO are ionic in nature. The highest oxidation number in the oxide coincides with the group number. I have already told you, right? From scandium to manganese, the highest oxidation state in their oxides basically coincides what? Their group number. Okay. Beyond group 7, no higher oxidation state is observed, right? Except in the case of Fe, right? So the Fe can have +3 oxidation state. So beyond this, beyond +3, no other higher oxidation state has been seen. Fine. However, the higher oxidation states are seen in oxocations. Oxocations are the cations formed by the transition metal with oxygen where the overall charge is positive, right? Now, vanadium can show a +5 oxidation state in its oxocation VO2+, right? Vanadium can show +6 oxidation state in its oxocation VO2+, and titanium can show +4 oxidation state in its oxocation titanium O2+. You need to cram this. Data, purely data. Okay, right? As the oxidation number increases, already told you, covalent character increases, ionic character decreases, just shown you, right? In the case of MnO2, since it is said to have the highest oxidation state, right? So here the covalent character is maximum. So it is covalent and it has a appearance like of a green oil. Once in JEE mains, they have asked you, which oxide is said to have green oil like appearance? The answer is basically Mn2O7. Clear? Okay, fine. Further, CrO3 and V2O5 have low melting point. Why they have low melting point, beta ji? Because they are covalent, right? And covalent solids, although covalent bond is strong, but these molecules which are held by covalent bond, like you have CrO3 one molecule, CrO3 another molecule, CrO3 third molecule. So these molecules are held by weak van der Waals forces. So that is why the melting point is very less. Right? That is why since CrO3 and V2O5 are covalent in nature, they are said to have what? They are said to have low melting point. Why? Because they are covalent solid. Why? Because they are covalent solid. Right? Because whenever the oxidation state is higher, right, they are more covalent character is there. Okay? More covalent character is there. Fine. Okay. Further, whenever the oxidation state is high, these oxides are predominantly said to have what? Acidic character, which I have already explained you. But V2O5 has more amphoteric character. Clear everyone? Fine. Further, let's move ahead to other important points. These are very important here. From these questions have been repeatedly asked. MnO2, since it is Mn2O7, since it is acidic in nature. So acidic oxide have a tendency that whenever you make them react with water, right, they formed acid. So in the case of Mn2O7, you form manganic acid, which is HMnO4. Now oxides, those oxides are acidic, which forms acid with water. So since this is acidic, so whenever it reacts with water, it forms manganic acid. And similarly, your CrO3 is also acidic, Clear? It is also acidic. So when you make it react, okay, when you make it react with what? With water, it also forms an acid, and that acid is either H2CrO4 or it is H2Cr2O7. Am I clear, everyone? Fine. Okay. Now here, if I talk about V2O5, V2O5 is amphoteric. Okay. Right. Now, since it is amphoteric, beta G, it can give both the types of salt. Right. It can forms anionic as well as cationic salt. Why? Because it can react with both acid and water. Clear, everyone? When V2O5, since it is amphoteric, okay, it can react with both acids and base. Clear? It can react with both acid as well as base. Okay, when it reacts with base, it forms oxoanion. Okay, this is oxoanion. Okay, when it reacts with acid, it forms oxocation. Clear? It forms what? It forms oxocation. Is it clear, everyone? Fine. Okay, so it reacts since with both acids and base, it can form oxocation also, oxoanions also, right? Okay. Further, it has been written that V2O3 is basic, V2O4 is less basic, already explained you, right? Further, it is written that V2O4, since it is basic only, when it reacts with acid, it forms oxocation VO3+. Clear? Okay, so V2O4 is basic, although less basic. So since it is basic, it can react with acid. Once it reacts with acid, it forms oxocation, which is VO2+. Am I clear? Which is VO2+. Perfect, everyone? Okay, right, fine. Further, it has been written that CrO is basic, Cr2O3 is amphoteric. Already I have explained you guys. Clear, right? So we have done everything important in this paragraph in short form right here. Fine. Now, let's move to the questions. You have to tell me, if you have listened to me very carefully, these questions are peanuts for you. Okay, they're peanuts. Fine. Now you tell me, first question, which of the following oxide of chromium is amphoteric in nature? You have to tell me which of the oxide of chromium is basically amphoteric in nature. Yes, quickly tell me, which is amphoteric in nature? Quick, be quick. Just told you, Cr2O3. Yes, beta, CrO is basic. Cr2O3 is amphoteric. And CrO6 is acidic. So you have to tell the amphoteric one. So answer was Cr2O3. Option number B is absolutely correct. Clear, everyone? Fine. Okay. Chalo. Let's move ahead. Which of the following oxides are amphoteric, beta? See, in the case of chromium, Cr2O3. And in the case of vanadium, V2O5. These are only amphoteric. Okay. So the answer is option number A. Rest, this is acidic. Just told you, this is also acidic. Basic. Less basic, but basic. Only these two are what? Amphoteric. Am I clear, everyone? They can give you such questions. They can definitely give you such questions. Okay, right? So answer is option number A. Fine. Now this question was asked in NEET 2023. If someone have heard me, this question is piece of cake. Okay, it is piece of cake. Fine, it is piece of cake. All transition metals except scandium forms oxide which are iodic. You have to tell the statements which are incorrect. I've just told you. Now you only tell me whether it is true or false. Then only I'm going to proceed ahead. Yes, statement A. Is it true or false? Just taught you. Just taught you. It is true. Okay. Right. Fine. Highest oxidation number corresponding to group number in transition metal oxide is attained in scandium oxide to manganese oxide. True. Basic character increases from V2O3 to V2O5. No, basic character decreases. This is basic, this is less basic, this is amphoteric. That means this is false. V2O4 when dissolves in acids from VO4 3 minus. Beta, it is false. I've just told you it basically forms oxocation, not oxoanion, right? It basically forms what? It forms oxocation, which is VO3 plus. Clear, everyone? Okay, right. Just told you this is false. Chromium oxide is basic, NCr2O3 is amphoteric. It is true. Right. Now you tell me, is NCRT squinting important or not? It's pretty important. Arey, why option C is correct, yaar? What are you saying? How it is correct? V2O3 plus 3. V2O4 plus 4. V2O5 plus 5. So left to right oxidation state increases, yaar. So basic character, no, acidic character increases. In fact, none of them is acidic. This is basic. This is less basic. Yes, this is less basic. And this is basically amphoteric. Okay, this is basically amphoteric. Fine. So you have to tell the false. So answer is C and D. Right? Answer is C and D. Final answer is C. Right? Okay. Chalo. So let's move ahead again. V2O4 dissolves in acid to form VO2 plus salt. True or false? True. Okay, just told you right here. Just told you right here. Right? It is basic. So when reacts with acid forms oxocation. Clear? Next, V2O5 reacts with alkali as well as acid to form VO4 plus and VO3 minus. Beta, it is wrong. Because they have swapped it. Although when you read it, it seems that it is correct, but no. Beta, when V2O5 reacts with alkali, it does not form VO4 plus, it forms VO4 3 minus. Clear? When it reacts with alkali, it forms oxoanion. Clear? So oxoanion which is formed is VO4 3 minus. And when it reacts with acid, since it is amphoteric, now it reacts with both acids and base. Clear? Fine. Okay. So it will form what? It will form VO4 plus, which is oxocation. Clear? So this is false. Because they have written vice versa. Brass is alloy. Yeah, we will study this in some time. In upcoming 3 to 4 slides, we will study it. Brass is alloy of copper and zinc. It's true. Even a 10th student can say this. And bronze is an alloy of copper and tin. It is also true. So first is true, third is true, and fourth is true. So option number B is true. Clear? Okay. Option number B is true. Is it clear, guys? Yes. Is it clear? Okay. Fine. Chalo. Let's just move ahead, guys. Let's just move ahead. Next question. Next question. Vanadium has highest enthalpy of atomization among 3D series. True. You have to tell the correct statements. Okay. So you have to consider the following statements and you have to tell the correct statement. Okay. So vanadium has highest enthalpy of atomization. True. Chromium plus 6 forms dichromate in acidic medium is a strong oxidizing agent. Absolutely correct. Chromium in plus 6 is always a strong oxidizing agent. Scandium 3 plus in aqueous solution is colorless. In just some time, although this question have came priorly only, I will discuss it. Yeah, scandium 3 plus has D0 and all D0 and D10 configurations are colorless. We will study the next topic. So this is also true. Okay, right. So all the statements are correct right here, A, B and C. This I will explain you ahead in the next slide. Okay, fine. Chalo. So now let's come to the property number 11, which is that transition metal forms colored iron. Okay, transition metal forms colored iron. Do you need a break of 15-20 minutes? Yes, do you need a break or should I continue? Do you need a break? If you want, I can give you. Or if you can wait for half an hour, good enough. So in half an hour, you'll be able to complete all the properties. Quickly tell me. Quickly tell me. Quickly, quickly. You need a break. Okay, fine. Let's take a break of 15 minutes, 10-15 minutes, okay? Let me see how much I want. So here, break. 10 to 15 minutes. Hi everyone, am I audible and visible? Yes. Am I audible and visible, everyone? Am I audible and visible? Shall we start, guys? Chalo, let's start. So I guess before going on break, we have done the oxocation and oxoanion, which were property number 10, okay? So now, we will do the property number 11, which is formation of colored ions. Now here you can see these are the aqueous solution of transition elements. We can see that these are colored in nature, right? Okay. So the answer to the reason or the answer to the question that why they are said to be colored in nature, then bacha, all, not all, few of transition metal and their ions are colored in nature. Are colored in nature. What is the probable reason for that? Yes, what is the probable reason for that? Everyone, right? Reason is that they either do crystal field splitting or DD transition, or there occurs charge transfer. That means the two reasons which are responsible for the aqueous solution of transition metals and their compounds to be colored, right? Fine. In the solid state or in the aqueous solution, beta G, it is basically either due to DD transition or due to charge transfer. Now, what is DD transition and what is charge transfer? Let's understand. Right. In aqueous solution, the main reason responsible for color is DD transition, and in solid state, the main reason is charge transfer, basically. So here, what is the reason, beta? In aqueous solution, na, actually the transition metals and their cations forms the coordination compound with the water, right? Water can act as a ligand. Fine. Like for example, everyone, you have CrH2O whole 6 3 plus. So whenever a transition metal is forming the coordination complex, the d orbital, 5d orbitals, which the transition metal has, no longer remains degenerate. Okay, right. Now chromium has 5d orbitals or 5 3d orbitals. So these d orbitals are no longer degenerate now. Fine. Okay. Earlier we have dxy, dyz, dxz, dx square minus y square, and dz square. Further, first they were what? First they were degenerate. As soon as they form the coordination complex, right? First they were said to have equal in energy. Now they split up into two sets of orbital. I've already told you the two sets are basically one comprising of the three non-axial orbitals, which are dxy, dyz, dxz, and the other one is the axial sets, which basically comprising of the two orbitals. One is dx square minus y square and the other one is dz square. Clear, everyone? This set is basically T2G. This set is basically EG. Why they are called so, you will get to understand in coordination complex, which I will teach the next chapter most probably in this mega marathon. Am I clear, everyone? Okay, right. Now here, what happens is that in the aqueous solution, suppose you have the aqueous solution of chromium 3 plus, the d orbital of chromium gets split up, right? So when the white light falls, okay, right, some amount of white light, or we can say the sunlight, will be absorbed by the electrons which are present in the case of chromium to undergo transition from T to G to EG. This is known as DD transition because this is the orbital, this is the orbital, right? Fine. So some portion of white light, some portion of white light is absorbed, some portion of white light is absorbed, right? Okay. And suppose the white light given is 50 kilojoules. Energy required for DD transition is what? 30 kilojoules, right? So 20 kilojoule energy will be transmitted, right? Remaining energy is transmitted or re-emitted. And corresponding to this transmitted energy, everyone, corresponding to this transmitted energy, everyone, we basically observe color in the case of the aqueous solution of transition elements. Am I clear, everyone? Fine. Okay. Cool. So one of the reason for this color is DD transition due to crystal field splitting. Now, crystal field splitting is a splitting of degenerate d orbitals into two sets of orbitals, T2G and EG. Clear, everyone? Okay. So what happens is, if one electron is present right here, this one electron will get excited from T2G to EG by absorbing the energy from white light, and the remaining energy is transmitted, and corresponding to this transmitted energy, the color is observed for a given metal ion in aqueous solution. Clear? So one reason is DD transition. Clear? Now you tell me, only those ions or transition metal ions or transition metal atoms can do DD transition which have unpaired electrons, right? Which have what? Which have unpaired electrons, or that means which have partially filled or incompletely filled d orbitals. If d orbital is completely filled, beta, then there is no unpaired electron. Right, so there is no possibility of DT transition. At the same time, when there is no electron in d orbital, then also there is no DD transition, right? So here we got to understand that if we have scandium 3+, it has 3d0 electronic configuration, and zinc, it has 3d10. So both do not have unpaired electrons in 3D. So in both, DD transition is not possible. Clear? In both, DD transition is not possible. Am I clear? In both, DD transition is not possible. Okay, in both, DD transition is not possible. Clear? Fine. Therefore, they are colorless. Okay, therefore, they are colorless. Am I clear, everyone? Therefore, they are colorless. Now, they will ask you the same question. They will ask you which of the followings are colored. So, you just have to remember 3D0 and 3D10 are colorless. Rest colored. Okay. So, here if you have zinc 2+. Zinc 2+ is what? 3D10. Right? So, colorless. Okay. What it is? Colorless. Now, if I talk about titanium 4+, am I clear? If I talk about what? Titanium 4+. Again, this is 3D0. So, it is colorless. Copper plus, again 3D10, colorless. Vanadium 3+, 3D1. So, one electron is there. Okay, so it is colored. It is colored. Clear? So, the answer is option number D. The aqueous solution of vanadium 3+ is colored. Is it clear, everyone? Is it clear or not? Quickly tell me. Clear? Perfectly clear? Okay. If it is clear, please give me the answer of the next question. The question is, in which of the following pair both ion solutions are aqueous? See, both the ion solution should be colored, right? Colored. Fine. So, copper 2+, copper +1 is 3D10. So, definitely this cannot be the pair. Okay. Fine. Scandium 3+ is 3D0. So, this cannot be the pair. Scandium 3+, 3D0 again cannot be the pair. Nickel 2 plus is 3d8 and titanium 3 plus is 3d1. Okay, fine. Scandium, titanium, vanadium. Just a second. I think this is 3d2. By mistake, I've written 3d1. This is 3d2, guys. Make a correction. Huh? This is 3d2 and titanium 3 plus is 3d1. Okay, so this is 3d8, this is 3d1. Both have unpaired electrons. So their solution will be colored. Okay, their solution will be colored. Clear, everyone? Yes, clear? Absolutely clear, guys? Fine. So similar question is this one. Which of the following has colored? Just did it, that titanium 3 plus is basically said to have an electronic configuration of 3d1, right? So it is colored in nature. So it has been asked once. Now, the second probable reason for the color is charge transfer. Okay, right? It is charge transfer. Like for example, everyone, I have MnO4 minus and I have Cr2O7 2 minus. Clear? In MnO4 minus, manganese is said to have +7 oxidation state and Cr2O7 2 minus, chromium has +2 oxidation state. So here manganese is present in +7 oxidation state and here chromium is present in +6 oxidation states. Am I clear, everyone? Okay, fine. Now both are said to be what? Both are said to be 3d0. If both are said to be 3d0, then dd transition is not possible, right? Fine, dd transition is not possible. However, Cr2O7 2 minus crystals are orange in color. Clear? Right. Okay, and MnO4 minus is basically deep purple. So how they are said to be colored? Okay, how they are said to be colored? The answer to that is charge transfer. Okay, if I talk about MnO4 minus, it has tetrahedral structure. You have already studied in chemical bonding. Now here, this oxygen has lone pair of electrons and this manganese has vacant d orbitals. Okay, right? Manganese has what? Vacant d orbitals. So what can happen, guys? Oxygen can transfer its charge to manganese. So this is known as ligand to metal charge transfer. Am I clear, everyone? This is LMCT. What is LMCT? Ligand to metal charge transfer. Now, once the charge is transferred, the electrons will come to manganese and now it can do 2D transition, definitely. Fine. Okay. So this is LMCT, right? This is charge transfer, which is ligand to metal charge transfer. The charge transfers could be metal to ligand also, but here you have to study only LMCT. Similarly, here also, right, in Cr2O7, it is said to have this structure. Okay, so here also LMCT is possible. So due to LMCT, both of them although have D0 electronic configurations but are colored. Okay, but are colored. Is it clear, everyone? Fine. Any problem, anyone? If it is clear, please give a heart or a thumbs up in the chat box. If it is clear, please give a heart or a thumbs up in the chat box. Clear, everyone? Okay, fine. Shall we move ahead? Fine. So the reason for colored should be clear to you guys. Next is catalytic property. Right, this is your property number, I guess 12. Okay, this is your property number, I guess 12. Guys, okay, fine. So here, why transition metals are said to act as catalyst? Catalyst is a substance which basically increase the rate of reaction without getting itself used. It is always regenerated. Am I clear? It is always regenerated in a reaction. Here, transition metal act as catalyst. That means they increases the rate of reaction. Now, what is the reason that they can act as a catalyst? There are two reasons because of which they can act as catalyst. What are the two reasons, everyone? The two reasons are basically the number one is variable oxidation state and number two, complex forming property. Right? Let's understand one by one. What do you mean by this? Now, variable oxidation state means here, look at it. Look at it. Here, since Fe can have variable oxidation state of +2 and +3, right? Okay, so Fe3 plus can catalyzes the reaction of, my dear students, CS2O8 2 minus to SO4 2 minus. Okay, now this is what this is. S2O8 2 minus, this is peroxo ion. Okay, peroxo ion means beta, here sulfur is said to have peroxy linkage. You must have studied in your redox reaction. Am I clear, everyone? So oxygen is said to have your peroxide linkage, and whenever oxygen has peroxide linkage, its oxidation number is -1. Okay, so what happens right here is beta G. This Fe3 plus first reacts with I minus. Clear? Once it reacts, Fe3 plus is a catalyst. Okay, first it reacts with whom? It reacts with I minus. Now I've already told you I minus is reducing agent and Fe3 plus is oxidizing agent. Right, now since I minus is a reducing agent, right, it undergoes oxidation to I2, and since Fe3 plus is oxidizing agent, it itself undergo reduction to what? Fe2 plus. Clear, everyone? Now this Fe2 plus, which is regenerated right here, reacts with S2O8 2 minus. Clear? Fine. Now what happens is right here, beta G, this Fe itself oxidizes it to Fe3 plus. That means it acts as a reducing agent. Clear? And this basically acts as an oxidizing agent. That means here Fe2 plus cause the reduction in the case of S2O8 2 minus. Here the oxidation state of oxygen is -1 and here it forms SO4 2 minus where the oxidation state is -2. Am I clear, everyone? Okay, so when you will write the overall reaction, you will see here that the catalyst is regenerated, Fe3 plus is regenerated. Fine. And when you will write the overall reaction, right? Fine. Okay, you will see that catalyst is not coming in the overall reaction. Okay, so the thing is, if I minus and S2O4 2 minus have reacted directly, the reaction would have been that fast. But when Fe3 plus, which can show variable oxidation state, is involved, the reaction becomes fast. Okay, so one of the major reason that why transition metals can act as catalyst is basically due to presence of a variable oxidation state. They can form intermediate oxidation states also. Am I clear, everyone? Yes. Am I clear, everyone? If it is clear, please give a thumbs up. Are you even listening or dead? Huh, guys? Listening? Are you even listening? But I am way ahead of this body shaming now. Hannah, I am way ahead of it. Okay, Mobina is listening. Who else? Yes. Gopa, Kumar S. Yes. Very good, very good. Mobina, very good. Fine. So Ashiba is listening. Adarsh is listening. Rajiv is listening. Okay, cool. Okay, fine. Chalo. So I think your energy is low. Understandable. The time is too late. So that is why the energy is low. Okay, fine. Chalo. Let's just move ahead. Let's just move ahead. Okay. Very good, Haritha. Very good, Edward. Okay, fine. Cool. So now, one more thing, that why they basically act as catalyst. One more reason is that their complex forming tendency. Okay. The second reason was what? Complex forming tendency. So what happens is that your reactant forms a complex or a transition state with the catalyst. Suppose this is the surface of the catalyst and you have two reactants. First is AB and the second reactant is CD. Okay. So what happens is both the reactants when interact with the catalyst, their bonds start breaking, right? And their bond with the other reactant starts forming. And they basically forms transition state or complex with the catalyst, which is highly unstable. And it immediately undergoes bond breaking to form AC plus BD. So due to this transition state or complex forming ability, your transition metal catalyst can act as what, everyone? They can act as, guys, catalyst. Okay, they have a high tendency to act as catalyst. Cool, fine, chalo. Let's move ahead, guys. So let's see some catalytic properties. Or some examples in which the transition metals are acting as a catalyst. First, Fe can act as a catalyst in Haber's process. Fe can act as a catalyst in Haber's process. Okay, fine. Then V2O5 can act as a catalyst in Oswald process, which is one of the most important point in formation of H2SO4. Okay, in the contact process. Am I clear? Right, by mistake I have said Oswald. It is contact process. Okay, it is contact process. Okay, so contact process is used for the preparation of H2SO4, and this is one of the very important reaction which is taking place there. Fine. Then in formation of ghee from oil, we use nickel, platinum, palladium as catalyst. Okay, then in Walker's process, in which your ethine changes to acetaldehyde, you study this in organic, right, in hydrocarbon. Okay, so in Walker's process we use palladium chloride as a catalyst, right? Similarly, Ziegler-Natta catalyst, which is TiCl4 plus Al-C2H5 whole 3, is basically used in polymerization. Earlier, you used to study polymers. So there we used to study this particular reaction. Okay, and Wilkinson catalyst is basically, is used in the hydrogenation of alkenes. So these are some important catalysts which are mentioned in NCERT. Okay, fine. Cool, everyone. Now, next in NCERT, there have been written that yes, due to complex forming tendency and variable oxidation state, D block elements are used as a catalyst, but they are used as a catalyst in wide variety of reaction. There is one more reason for that, beta. The reason is that it is very easy to powder them, and when you powder them, the surface area increases. So the concentration of reactant which could have been absorbed, that also increases, and when the concentration of reactant is increases, the concentration of product also increases. That means the rate of reaction increases. Clear? So this is also one of the reason to use D block elements as catalyst. Fine, it is written in NCERT. Next topic which we have to start right now is beta G, magnetic properties. Okay, magnetic properties. Next topic, which is number 13. Yes, number 13 property is your magnetic properties. Am I clear? This is basically your magnetic properties, right? Now, what is magnetic properties, guys? See, whenever magnetic field is applied to transition metals, they show two types of behavior. Either they attract the magnetic field or they repel the magnetic field. If they attract the magnetic field, beta G, they are basically known as paramagnetic. Am I clear? They are basically known as paramagnetic. And if they repel the magnetic field, they are basically known as diamagnetic. Okay, now how to characterize that these are paramagnetic substances? But paramagnetic substances usually have unpaired electrons. Okay, right? What ma'am is saying? Ma'am is saying paramagnetic substances usually contains one or more unpaired electrons. Okay, they contains one or more unpaired electrons. Am I clear? They contains one or more unpaired electrons. And if I talk about diamagnetic substance, they do not contain unpaired electrons. They contains all paired electrons. Clear? They basically contains all paired electrons. Am I clear? All paired electrons. Clear, everyone? Fine. Now we characterize your magnetic substances on the basis of their dipole moment. Okay, right? On the basis of dipole moment only, we characterize whether the substance is paramagnetic or diamagnetic. If the dipole moments comes out to be 0, the substance is said to be diamagnetic, and if non-zero, paramagnetic. Now, ma'am, how to identify the magnetic moment? Is there any way to calculate the magnetic moment, beta G? Right? Yes, there is a way, which is the formula. The formula is, which is used to calculate the magnetic moment, is basically, my dear students, root of n into n plus 2 Bohr magnetron. This n right here is basically equals to what? This n right here is basically equals to number of unpaired electrons. Clear? This n in the formula is basically equals to what? Number of unpaired electrons, and the magnetic moment is basically represented by mu. Am I clear, everyone? Fine. Now we will solve few questions of magnetic moment. Okay, so you basically have to tell that which of the following is said to have higher magnetic moment. Guys, see, magnetic moment mu is n into n plus 2 Bohr magnetron, where n is what? Number of unpaired electrons. Okay, what is n? N is basically number of unpaired electrons. Okay, number of unpaired electrons. So as the number of unpaired electrons increases, magnetic moments increases. Okay, so as n increases, mu increases. So that means you do not need to find the complete magnetic moment, just find the number of unpaired electrons and you are sorted. Clear? You're sorted. Okay, like for example, here in the case of vanadium 4 plus, right? Scandium, titanium, vanadium. Okay, so vanadium has 4s2, 3d3. So elimination of 4 electron, it has 3d1. Okay, manganese plus 4 will have 3d3. Okay, Fe3 plus has 3d5 and nickel 2 plus has 3d8. Right, so here the number of unpaired electron is 1. Here it is basically 3. Here it is basically 5. And in 3d8, beta G, see, in 3d8, your 3 electrons are paired, guys. Okay, so you have only 2 unpaired electrons. Am I clear? Right. So where the number of unpaired electrons are maximum? In option number C. Right. In option number C. Okay, that is why beta G here, since the number of unpaired electrons are the maximum, so magnetic moment also right here is maximum. Cool, everyone? Yes, is it cool? Clear? Understandable? Okay, fine. Now, further, next question for you guys is, why most of transition elements are paramagnetic? This question can be asked because it is given in NCERT. So the reason is, beta, most of transition elements have unpaired electrons. So they will have certain moment or value of magnetic moment. And since they have certain value of magnetic moment, beta G, they will said to be paramagnetic in nature. Am I clear? They are said to be paramagnetic in nature. Clear? Fine. Okay. Chalo. Let's just move ahead. Let's just move ahead. Next question, it has been asked in your AIPMT, which of the following is incorrectly representing? First, melting point. This is incorrect, beta. Melting point of chromium is greater than manganese. Okay, so if this is incorrect, so answer will be option number A only, right? And when you will find the magnetic moment order, although these two are correct only, this I've already done. And this also is true that from titanium to manganese, the number of oxidation state increases. Fine. And here in titanium 3 plus, I have one unpaired electron. So it has 3d1. Okay. Vanadium 3 plus has two unpaired electrons. Chromium 3 plus has 3 unpaired electrons, and manganese 3 plus has 4 unpaired electrons. So since the number of unpaired electrons increases, the magnetic moment also increases. So this is true, this is true, this is true, and this is false. So option number A is correct. Clear, everyone? Fine. Okay. Chalo. Next question. They can give question in this particular form also. Magnetic moment of 2.84 is obtained by which of the following ions, beta? See, root 8 is 2.84 approximately, and root 8 can be obtained when the number of unpaired electrons are 2. Okay, because see, magnetic moment is n into n plus 2 Bohr magnetron, right, everyone? This is your mu. So when n is equals to 2, the magnetic moment comes out to be root 8. And root 8 is basically equal to what? It is basically equals to 2.84 or nearly 2.83 Bohr magnetron. So see which has two unpaired electron. Okay, the very first is titanium 3 plus. It has one unpaired electron. Okay, now next is your chromium 2 plus. So chromium 2 plus is basically your 3d4. It has 4 unpaired electron. Cobalt 2 plus is 3d7. Okay, so if it is d7 beta G, you have 3 unpaired electrons, right? You have 3 unpaired electrons. And in 3d8, you have how many beta G? You have 2 unpaired electrons, right? Okay, so answer is option number D. Am I clear? Answer is option number D right here. Fine. There is one more question of NCERT exampler. You can try it in homework. Fine, you can try it in homework. It is a similar sort of question. Clear? Right? Fine. So now we are done with the magnetic properties, which were your 13th property. Now let's come to 14th property, right? Now what is the 14th property, beta? 14th property is basically alloy formation. Transition metal can forms alloy. Now what are alloy, guys? Okay, what are alloy? Like for example, brass is an alloy. How it is formed? You basically take copper and zinc, okay, melt them and mix their melt. So what will happen? Copper atom will insert themselves into zinc lattice, and zinc atoms will insert themselves into copper lattice. Is it clear, everyone? Okay, so by the mixing of metals, mostly metals, although alloy can be formed by the mixing of non-metals also, but majority of metals forms alloy. Okay, so you can say the mixture of metals is basically known as alloy. What we basically do, we melt zinc, we melt copper, we mix them, okay, and then we solidify it. So it results into the formation of brass. Brass is an alloy. Clear, everyone? Okay, Now, can any two metal will be mixed to form the alloy? No. Only those two metals can be mixed to form the alloy in which the size difference is almost 15%. Clear? The size difference should not be more than 15%. It should be almost 15%. Okay, fine. Now, since D block elements are said to have similar size due to so many reasons, right? Fine. So that is the reason, beta G, D block elements are actually forming alloys. Fine. Because they have very less difference in size, so they can replace each other, okay, in their metal lattice. Fine. So for example, orange was a zinc lattice. So what will happen? The copper atoms in a alloy insert themselves in the zinc lattice. So results into the formation of alloy. Clear, everyone? Fine. Now here there are the few examples of important alloys which they can definitely ask. For example, bronze is an alloy of copper plus tin, right? Brass is an alloy of copper plus zinc. Then you have German silver, guys. Okay, it seems like it is an alloy of silver, but no, it has an appearance like that of silver, although it is an alloy of nickel plus copper plus zinc. Clear? Lico, as the name suggests, is an alloy of aluminium plus nickel plus cobalt. Invar is an alloy of nickel plus iron. Okay, right? Then steel, it is basically an alloy of iron, but purely iron is not present. There are some impurities of nickel, manganese and chromium are present. Okay, so these three are present as impurity. So for all those who thinks steel is pure iron, no, it has certain impurities of nickel, manganese and chromium, as well as some other elements are also present. Okay, right? So we can say some other impurities also. Fine. Okay, in mains they have asked few questions regarding what alloy is made up of what atoms, so that is why. Okay, fine. Now number 14th, I guess, and the last property, not last, second last, is that coordination compound, or I should say the D block elements, not the coordination compounds, D block elements or transition elements, my dear students, basically act as interstitial compounds. Okay, D block elements or transition elements can act as what? They can act as transition. They can act as what? They can act as interstitial compounds. Okay, they can act as what, guys? They can act as interstitial compounds. Whom, guys? Whom? Transition elements, right? What can happen is, beta G, small elements, right, which have small in size, specifically non-metals. Okay, non-metals have smaller size. Why? Because left to right atomic size decreases, right? So generally non-metals which lie on the extreme right are said to be having smaller size. Okay, so you have non-metals like hydrogen, carbon, nitrogen, boron. They have small size. So what they can do, beta G, they can trap themselves into the metallic structures of various transition elements, right? Okay, fine. Like for example, this was a lattice of a transition elements, and there were certain voids or gap, right, where the impurities such as non-metals, okay, hydrogen, carbon, nitrogen, boron are trapped. Then the resultant compound is basically known as interstitial compound. Okay, the resulting compound is basically known as what? Interstitial compound. Am I clear, guys? Okay, now interstitial compounds are basically non-stoichiometric, right? Majority, although they could be stoichiometric, but majority of them are non-stoichiometric. What is non-stoichiometric? Example, you have TiH 1.7. So here the molar ratio of titanium is to hydrogen is 1.7, right? So it is not a integer ratio, right? There's a decimal value right here. So that is why when you have, integral ratios. So they are stoichiometric compounds. Like for example, you have TIC, so 1:1 molar ratio. Mn4n, that is 4:1 molar ratio, right? 3:1 molar ratio. So these are stoichiometric compounds, right? But they forms non-stoichiometric compounds also, like TiH 1.7. Okay, fine. Now the question come is what happen when they form interstitial compounds? What is the advantages of forming interstitial compound? Everyone, am I clear? Fine. What is the advantage of forming interstitial compounds, beta? See, obviously, first there were few elements which are present, right? Now some more elements are coming. So definitely the melting point will be higher than pure metals. Okay. So if you want to increase the melting point and use it at a place where the high melting point is required, you can take the transition metal in the form of their interstitial compounds. Okay. Right. Then they are hard. Okay. Even few interstitial compounds are that hard that their hardness approaches to diamond. Okay, then their metallic conductivity is retained. Why? Because there is no change in the number of delocalized electrons. The delocalized electrons are same. Clear? Okay, fine. Okay. ठीक है. Further, they are chemically inert. Why they are chemically inert, beta? Because they are not changing the chemical composition, right? Fine, there is no ion which is forming. Okay, there is no increase in electrons, so there is no reactivity which is increasing right here, so they are chemically inert. Clear? Fine. Now let's come to 15th property of transition element is that they can form coordination compounds. Now they form coordination compounds. Why? Because their size is small. Okay, right. Now when size is small, then size to charge to size ratio. Okay, charge to size ratio. When size is small, charge to size ratio, which is charge density, basically gets increases. Okay, am I clear, everyone? What is charge density? Charge density is basically charge to size ratio. Okay, it is charge to size ratio. So when charge decreases, guys, charge to size ratio or charge density increases. Now since transition metal have lesser size, so their charge density is more, so their tendency to attract the ligand towards themselves in order to form the coordination compounds increases, right? Their tendency increases. At the same time, when the ligand come, they themselves has vacant d orbital, so they can accept electrons, okay, right, from the ligands. So due to presence of vacant d orbitals, at the same time due to high charge density, transition metal can form your coordination compounds. For example, here are few examples of your coordination compounds. Clear, guys? Okay, perfect, fine. So finally the part second, which was the most extended and the longest part, which is properties of transition elements, are done and dusted. Okay, right. Now we have to come to the third part, which is basically the compounds of transition elements. I am having a sip of water. Let's start it in a minute. Okay, fine. Now we have to study two important compounds of transition elements, my dear students. How many? Two. Okay, two. One is basically KMNO4 and the other one is K2CR2O7. Now KMNO4 is basically potassium permanganate. Clear? It is basically what? It is basically potassium permanganate. and K2Cr2O7 is basically potassium dichromate. Am I clear? It is basically what? It is basically potassium dichromate. Fine. So these two have to be studied. Okay. Right. Now, first, let's start with KMNO4. Okay. Let's start with the KMNO4. Now, beta, in KMNO4, it has two ions. One is K plus and the other one is MnO4 minus. Now this MnO4 minus is the active ions. That means all the reactions which KMnO4 or potassium permanganate does, it does. Why? Basically due to presence of this active ion which is MnO4 minus. Okay, fine. Now this MnO4 minus is basically your permanganate ion. Okay, permanganate ion. Fine. In a similar manner, if you have K2Cr2O7, it has K plus and it has Cr2O7 2 minus. Clear? So Cr2O7 is the active ion. That means this reaction mainly participates in the reactions of K2Cr2O7. Okay, so this is basically your dichromate ion. Okay, it is basically your dichromate ion. Fine, cool. Any problem, anyone? I don't think there should be any problem. Now, when there comes the name of potassium manganate, people usually get confused between the two. Dear students, try to understand this thing. One is KMNO4. This is potassium manganate. Am I clear? This is what? This is what? Sorry, beta. This is potassium permanganate. Which has active ion MnO4 minus, right? Okay. And one is K2MnO4. This is potassium manganate. Okay. This is what? This is potassium manganate, right? This is potassium manganate. Right? It has active ion MnO4 2 minus. Is it clear? Are you super duper clear regarding the manganate and permanganate ion, guys? Yes, clear? Okay, fine. Now, if I talk about your permanganate ion, it is dark purple in color, right? Right. And if I talk about MnO4 2 minus ion, it is dark green in color, right? It is dark green in color. Now, why this is dark purple in color? Because here Mn is present in +7 oxidation state. Okay, right. And there occurs, I've already told you, LMCT, that is ligand to metal charge transfer, right? And here the color is due to the fact that here Mn is present in +6. There was in +7. Here Mn is basically present in +6. So it has one unpaired electron. Okay. Since this one unpaired electron is there, it can undergo DD transition. Am I clear? It can undergo DD transition. So that is the reason responsible for color. Clear, everyone? That is the reason responsible for color. Is it clear, guys? Now, MnO4 minus has 4 oxygens which are tetrahedrically surrounding the manganese. You must have studied in chemical bonding. Okay, you must have studied in chemical bonding, right? So whenever the arrangement is tetrahedral, we say the hybridization is sp3. But my dear students, mark my words here, the hybridization is not sp3, it is sd3. We sd3, yes, sd3. Okay, in JEE teachers teach this, but in NEET it is irrelevant, and in NCERT also they haven't mentioned anything about the hybridization. They have just written, okay, they have just written that they're tetrahedral. Okay, so you need to remember just only one thing, right, that it is tetrahedral. It is tetrahedral. Right, now here there are 3 pi bonds which are formed by the sideways overlap of the p orbital of oxygen and d orbital of manganese. That means they are basically your d pi p pi, d pi p pi and d pi p pi bonds. So there are total of 3 d pi p pi bonds are present. Okay, how many? 3. Now here, since manganese can undergo resonance, and whenever it undergoes resonance, the bond order is neither of pure double and neither of pure single, right? So all the bonds are said to have equal bond order, right? And how do you calculate that? Bond order of MNO bond, pretty simple. What are the total number of bonds you can see? 1, 2, 3, 4, 5, 6, 7. And how many pairs of elements which can hold those bonds? MNO, one pair, MNO, second pair, MNO, third pair, MNO, fourth pair. Okay, right, fine. So this is the bond order basically. Okay, ji, fine. And here all the MNO bond lengths are equal, or the bond order are equal, right? Bond order and bond lengths are equal. Here all bond lengths and bond orders are equal. Why? Due to resonance. Clear? Now, if I talk about MnO4 2 minus, guys, right, it is said to have a structure, again, tetrahedral. But here, instead of 3, you have 2 d pi p pi bond. Okay, you have how many? You have 2 d pi p pi bonds, right? And here the bond order of MnO bond is total bond 6 and total pair 4s. So definitely the bond order of MnO bond in the case of MnO4 minus is higher, right? The bond order of MnO bond in the case of MnO4 minus is higher than bond order in MnO4 2 minus. Clear? And we already have studied in chemical bonding that bond order is inversely proportional to bond length, right? So bond length of MnO bond in MnO4 2 minus will be higher than the bond length of MnO bond in MnO4 minus. Is it clear, everyone? Is it clear? Okay, fine. If it is clear, please give a thumbs up or a heart emoji in the chat section. If it is clear, please give a thumbs up in the chat section. Yes, clear, everyone? Clear? Okay. Chalo. Beta, if I talk about MnO4 minus, it is said to have 3d0 electronic configuration. Why? Because here Mn is present in +7. Okay, in MnO4 minus, Mn is present in +7. +7 means 3d0. So it should be diamagnetic. But NCERT does not like simple things, okay? So NCERT says that it is a temperature dependent phenomenon. Fine. It is a temperature dependent phenomenon, everyone. Okay, it is a temperature dependent phenomenon. At times, due to temperature, fine, they might behave weakly paramagnetic. Am I clear? They might behave weakly paramagnetic. Am I clear? They might behave weakly paramagnetic. Fine. Okay. I think we should give insecticides to parasites so that they can disappear. Hope someone give them insecticides soon. Okay, guys, let's just move ahead. Okay, let's just move ahead. Fine. Now, if I talk about MnO4 minus, here manganese is present in +6. So can have an electronic configurations of 3d1. So it is said to be what? It is said to be paramagnetic. Am I clear, everyone? Fine. Is it clear? Yes. Clear, everyone? Okay. So we have done the major things. Now let's come to commercial preparations of potassium permanganate. Okay. Now let's come to commercial preparation. Now let's come to the commercial preparations of potassium permanganate. Okay. Fine. Now, commercially, beta, your potassium permanganate is basically prepared from where? It is basically prepared from pyrolusite ore. Now, what is pyrolusite ore? Pyrolusite ore is MnO2, where manganese is said to have an oxidation state of what? It is said to have an oxidation state of what, my dear students? +4. Okay. So, what they do basically the oxidation of MnO2, right? Fine. By using an oxidizing agent in basic medium. Now the oxidizing agent which is being used could be O2, right? That means air. In air O2 is present. Fine, that means it can undergo aerial oxidation. At the same time, it can undergo oxidation in presence of oxidizing agent, which is potassium nitrate. Am I clear? Which is potassium nitrate. It is also an oxidizing agent. So what happens is, in both the ways, the pyrolusite ore in which manganese is present in +2 oxidation state, they oxidize to K2MnO4, that is potassium manganate, where the oxidation state is +6, right? That means oxidation from +4 to +6 has occurred, guys. But the major challenge is we want to prepare potassium permanganate, not manganate. So how we can do that? How we can do that? There are 3 ways, beta. There are 3 ways. Am I clear, everyone? How many ways? There are 3 ways which are practically possible, right? You put few drops of acid and leave it at room temperature. In some time, it itself undergo disproportionation, right, to form KMNO4 plus MnO2. Right, so there undergoes what? Disproportionation. But the drawback of this is, beta ji, here MnO2 is regenerated. Right, now since MnO2 is regenerated, then it can again forms K2MnO4. So the yield is not good. The yield is not good. Clear, everyone? Fine. And whenever nothing works, when oxidation doesn't work, keeping still for some time doesn't work, one thing works, which is passing electricity. That means doing what? That means doing, beta ji, the electrolysis. So if we will do the electrolysis, on electrolysis, it can form KMNO4. And another trick is you can even use a powerful oxidizing agent such as O3. What happens? You can use a powerful oxidizing agent. You can use a powerful oxidizing agent such as O3, right? That also oxidizes manganese from +6 to +7. Clear? So I have done the complete preparation. Okay, I have tell you the short trick. Now you just have to do what? You have to do the preparation according to the lines of NCERT, okay? According to the lines of NCERT. Fine. Okay, so let's do it according to the lines of NCERT. Now, NCERT says that how we do the commercial preparation of KMNO4 by using pyrolusite ore, which is MnO2. Right? What is MnO2, beta ji? It is your pyrolusite ore. What we do, we take pyrolusite ore into finely divided pieces. That means we crush them into small particles. Clear? Okay, fine. Then we do the oxidation of pyrolusite ore in basic medium, either in presence of air. From air we use O2, right? To form what, Rajay? To form, I have just told you, K2MnO4. And if nothing, you know how to make the product. Hydrogen is there, oxygen is there, form water. Clear? Form what? Form water. And if you want to balance, here 2 potassium, let's do it 2. Oxygen, here you have 2 plus 2, 4 plus 2, 6. Here you have 5, so you can do 1 by 2. Equation is balanced. Clear? You can do the above process by using KNO3 as well. You can use KNO3 as well, my dear students. Okay. So here what will be formed? Bachaji. Here you will get K2MnO4. This is an oxidizing agent. So itself it undergoes reduction to KNO2. Clear? That means it undergoes reduction from +5 to +2. NH2O is formed right here. Now, if you want to do the balancing, you can just take it to KOH. Fine, it is completely balanced. Clear, everyone? Quickly tell me, is it clear? Is it clear? Fine. Now, once K2MnO4 is formed, right? That means your permanganate is formed. You can leave it in acidic medium for some time. It can undergoes what I've just told you. It basically undergoes disproportionation to form what? MnO4 minus, right? Fine. Plus MnO2. Bacha log, fine. Plus it forms H2. Fine. So whatever I have told you in the short trick, the same thing is written in NCERT as it is. Now I have told you that once you prepare K2MnO4, you can even do the electrolysis, that is electrolytic oxidation. So in electrolysis, what happens is you have aqueous solution of K2MnO4, right? So in electrolysis, first you form ions. Right? And since it is aqueous solution, so water, although it is a weak electrolyte, but water can form H plus OH minus. Now we know that the discharge potential of the ion, right? The ion whose discharge potential is lower, that basically goes towards the electrode and undergo oxidation and reduction. Like for example, at anode, an ion goes. Now the discharge potential of MnO4 2 minus is lower. Okay, fine. So MnO4 2 minus basically loses one electron to form MnO4 minus, where the oxidation state is +7. And among potassium and H plus, discharge potential of H plus is lower. So this cation goes towards the cathode. And on cathode, it undergoes reduction. And so H2 gas is released. Am I clear, everyone? Fine. Next is basically the laboratory preparation. Okay, laboratory preparation. In laboratory, you can use peroxodisulfide. I've already told you what is peroxodisulfide. It is S2O8 2 minus. Okay, peroxodisulfide is basically said to have peroxide linkage. right? And in peroxide linkage, the oxidation state of oxygen is basically -1. Am I clear, everyone? Class duration, beta, till 2:30. Till 2:30. Fine. Okay. So this is basically what, beta G, this is basically an oxidizing agent. Fine. So if you have manganese in +2 oxidation state, it will oxidize it to MnO4 minus, okay, and itself undergoes reduction to SO4 2 minus, right? So manganese here get oxidized from +2 to +7. That means here occurs the oxidation of manganese. Clear? There occurs what? There occurs the oxidation of manganese. Clear? Right? And here, since oxygen has -1, here it has -2. So decrease in oxidation number has occurred. That means your peroxodisulfide ion undergoes what? It undergoes reduction. Clear? It undergoes what? It undergoes reduction. Clear, everyone? So laboratory preparation is done in this particular manner. Now, let's just move to the properties of potassium permanganate. Okay. Now, let's just move to the properties of potassium permanganate, guys. Now, what are the properties of potassium permanganate? Yes, let's quickly see them. First is beta G. Potassium permanganate is said to have a dark purple crystals which almost look like black crystals. Further, they do not are your KMNO4 crystals are not soluble in water at room temperature. Okay, if you will heat it a bit, it will get solubilized. Right? If you will heat it a bit, it will get solubilized. Fine, everyone. Now, what is the action of heat? That means what happens if you heat your KMNO4, guys? It basically undergoes decomposition. Fine, it basically undergoes decomposition to form K2MnO4, okay, plus MnO2. This is important. It has been asked so many times. Plus MnO2 plus O2. So you can remember in the way that it will give those compounds from which it is formed. Fine. Okay. So that is basically the action of heat. It is important. It is really, really important. Am I clear, everyone? It is really, really important. Fine. Cool. Shall we move ahead, guys? Yes. Chalo, let's move ahead. Let's just move ahead. Next property is basically oxidizing properties. So your KMNO4 is a very powerful oxidizing agent, right? And we know that the active ion is basically MnO4 minus. Fine, it is a very, very, very powerful oxidizing agent. It can act as oxidizing agent in acidic medium, in basic medium, at the same time in neutral or faintly alkaline medium. Okay, at the same time in neutral or faintly alkaline medium. In acidic medium, since it is an oxidizing agent, so it will itself undergo reduction now. So it basically forms Mn plus 2. Okay, right, fine, by the gain of 5 electrons. How 5 electrons? Here the oxidation state is +7, here is +2, so 7 minus 2. That means here 5 electrons gain is there. In basic medium, it basically undergoes reduction to form MnO4 2 minus. Okay, right? So here the oxidation state is +7, here it is +6. So it basically gains how many electron? 1 electron. Fine. Okay. Next, in neutral or faintly alkaline medium beta G, it undergoes reduction to form what? MnO2. +7 plus 4. So gain of how many electrons? 7 minus 4, 3. Fine. Now we know that the equivalent mass of reducing agent hash oxidizing agent is basically equal to molar mass divided by n factor, right? And what is the n factor? N factor is basically number of electrons gained or lost, right? So if I have to find the equivalent mass of KMnO4 in acidic, basic and faintly alkaline medium, it will be different. In the case of acidic medium, since the n factor is 5, it is m by 5. In basic medium, it is m by 1. Okay, fine. And in faintly alkaline medium, the equivalent mass is basically equals to m by 3. Clear, everyone? Yes. Is it clear or not? Quickly tell me in the chat box. Clear? Yes. Clear? Fine. Now, it acts as an oxidizing agent in acidic medium. How? By itself getting reduced to Mn2 plus. Fine. Okay, everyone? Right? Fine. And in acidic medium, it can oxidizes so many elements and compounds. For example, it oxidizes H2S to sulfur. Right? In acidic medium, okay, it oxidizes H2S to sulfur. So how can we write the balanced equation corresponding to this, right? How can we, is voice not clear, everyone? Is voice not clear? Is voice not clear? Clear? Is the voice clear, everyone? Yes, clear. Okay, fine. So here, it oxidizes H2S to sulfur. Fine, it basically oxidizes. I have told my Telegram channel in the starting part of the video, in the starting first 5 minutes, you will find the link of my Telegram channel, okay? Fine. So here, what happens in acidic medium, your KMnO4 or the permanganate ion itself undergoes reduction. So what will be the reduction half reaction? Here, MnO4 minus get converted to what? Get converted to Mn2 plus. Fine. So here the oxidation number is +7, here is +2. So that means there occurs the gain of how many electrons, guys? There occurs a gain of a total of 5 electrons. Fine. What is oxidation half reaction? Here, H2S is getting converted to sulfur. Fine. Here the oxidation state is -2. And here the oxidation state is 0. That means there occurs a loss of how many electrons? 2 electrons. Now, if you have to write the net reaction, fine. Okay. In net reaction, guys, the number of electrons are always 0. Net reaction never has, electrons. Never. So for that, if you have to cancel the electrons, what you have to do, you have to multiply this equation by 2 and this equation by 5, guys. Fine. So you will have 2MnO4 minus plus 5H2S, okay, forming what? 2Mn2 plus 5 sulfur. Fine. Now, then you have to see that other atoms except hydrogen and oxygens are balanced. So I guess which are already balanced, 2Mn, 2Mn, 5 sulfur, 5 sulfur. Now you balance your oxygen. Okay, on right hand side you have 8 oxygens, right? In the left hand side you have 8 oxygens, right? So that means on the right hand side you also need 8 oxygens. So that means you need to add how many water molecules, beta ji? 8 water molecules, because you balance oxygen in acidic medium by adding equivalent amount of water to the oxygen deficient site. Fine. Okay, so now here you have 8 into 2, 16 hydrogens, and here you have 10 hydrogens. Everyone, 5 into 2, 10, right? 5 into 2, how many? 5 into 2, 10. Okay, 5 into 2, how many? 5 into 2, 10. So that means what, beta ji? That means here you have 16 and here you have 10. So that means here you need to add 6H plus, right? So 6 plus 10, 16, and here also 16. So hydrogen is also balanced. Okay, so you add equal amount of H plus to the side which is deficient in hydrogen, right? Okay, so in this manner we can do the complete balancing. Now you can do this balancing for all the possible cases which are given in NCERT, right? We do not need to go in detail, guys. Fine, we do not need to go in detail. Okay, fine. I have just told you how to do it, and you must have studied in redox also. So you just need to know the product after oxidation. Like for example, KMNO4 or MNO4 minus act as an oxidizing agent, right? Okay, fine. So it basically oxidizes H2S to sulfur, fine. Oxalate ion to carbon dioxide, nitrite to nitrate, sulfite, which is SO3 2 minus, to sulfate, Fe2 plus to Fe3 plus, I minus to I2, ethyl alcohol to acetaldehyde or ethanol. This you will study in organic, acetaldehyde. Okay, so these are all the possible oxidation reaction which it can do in acidic medium. Clear everyone? Any problem? Yes, any problem? All clear? Fine, all clear? Okay, fine. Next, Beta ji, next. Now, in neutral or faintly alkaline medium, MnO4 minus is actually getting reduced to what, Bachaji? It is getting reduced to MnO2, right? By the gain of how many? 3 electrons. Fine, itself is basically undergoing reduction. However, it can oxidize H2S to sulfur, right? Fine. MnSO4, where the oxidation state of manganese is +2, to MnO2, where the oxidation state is +4. Fine. It can convert your thiosulfate, where the oxidation state of sulfur is very less, to NaSO4. Am I clear? You can find the oxidation state of sulfur. It will comes out to be what? 2 plus 2x minus 6 is equals to 0. So 2x minus 4 equal to 0. So 2x is basically equals to 4, x is +2. That means here the oxidation state of sulfur is +2 and in sulfate it is +6. Okay, so here the oxidation is done by MnO4 minus. Clear everyone? Clear. This is sodium thiosulfate. Okay, this is sodium thiosulfate. sodium thiosulfate. Fine. So now we are done with the properties, reaction, preparation of KMNO4. Already done. Alkaline, friendly alkaline medium is done. So now let's move to K2Cr2O7. Now my board is getting hang. Huh? My board is getting hang. So now we have to study K2Cr2O7. So here again, do not get confused. One is K2Cr2O7. Fine. One is K2Cr2O7 and the other one is K2CrO4. Okay. So if I talk about K2Cr2O7, K2Cr2O7 is basically potassium dichromate. People get confused among the two. That is why I am doing a complete distinction right here. Okay. So this is potassium dichromate. This is potassium dichromate, everyone. Okay, fine. And this is basically potassium chromate. Okay, this is basically potassium chromate. Clear? Right? The active ion of potassium dichromate is Cr2O7 minus. And here the active ion is CrO4 minus. Clear, everyone? Okay. So here oxidation state is +6. Here also is +6. So definitely they are not colored due to DD transition, guys. Fine. They are not due to DD transition, guys. Fine. Okay. They are colored due to LMCT. Right? They are colored due to LMCT. This is having orange color due to LMCT. Orange color. Fine. And this is said to have yellow color. This is said to have yellow color. Fine. Now, this is your dichromate ion. This is your dichromate ion. Fine. And this is basically your chromate ion. This is your chromate ion. Is it clear, everyone? Okay, this is your chromate ion. Now here, in dichromate and chromate, guys, chromate is basically stable in basic medium. Fine, it is basically stable in basic medium. So this is all in experimental observed facts, guys. So you need to remember. Fine. Okay, fine. This is basically stable in basic medium. Fine. Okay. And this is being stable in acidic medium. This is basically stable in what? This is basically stable in acidic medium, guys. Fine. Now, if I have to look at the structure, then in K2Cr2O7, you have two chromiums which are tetrahedrically surrounded by oxygens. Right? Here, so you have only one chromium. Again, tetrahedrally surrounded by oxygens. Clear, everyone? Okay. So here you have 2 plus 2, 2 plus 2, 4 d pi p pi bonds. And here you have only 2 d pi p pi bonds. Am I clear? You have only 2 d pi p pi bonds. Perfect, everyone. Perfect, perfect, perfect. Okay. Now, if I talk about all the bond lengths in this particular structure, due to resonance, all bond lengths are equal. Fine. And if I have to find the bond order, what should be the bond order, guys? Total of 1, 2, 3, 4, 6 bonds, and number of chromium oxygen pairs, 4. Right? So bond order is 6 by 4, and all chromium oxygen bond lengths are equal. Now we thought the same for Cr2O7 2 minus. Okay, we basically thought the same, guys, for Cr2O7 2 minus, that it also will be having, guys, equal bond lengths. But what happens is, listen to me very carefully. So what happens here is, here bonds in this part are same and this part are same. Okay, right? That means if this bond is basically your B, right, and this is A, then A and B are different. Rest, this is also B, this is also B. That means resonance occur only in this part. This oxygen is not in the plane of this particular ion. That is why this oxygen is not involved in the resonance. Am I clear? This oxygen is not involved in the resonance. Am I clear? Fine. Is it clear? Okay. It is not involved in the resonance. Perfectly clear, guys. This is not involved in the resonance. Okay. Fine. If this particular part is not involved in resonance, this is a pure single bond, and all these bonds, since are involved in resonance, they have partial double bond character, guys. So definitely single bond length is greater than the bonds which have partial double bond character. That means here bond length of A is greater than B. Clear, everyone? Fine. Okay, so if you have to find the bond order of these chromium oxygen bonds, so definitely you can't take this bond into consideration, not the part of resonance. So total 1, 2, 3, 4, 5 bonds, and total pairs. Yes, how many total pairs are there, guys? Yes, how many total pairs are there? 1, 2, 3. So the bond order is 5 by 3. Am I clear? The bond order is basically 5 by 3. Clear, everyone? Okay, shall we move ahead? Shall we move ahead? So let's see who all stays till the end. Huh? Let's see who stays till the end. Guys, let's see who stays till the end. Who is that much serious? Let's see. Okay. Fine. Chalo. Now, next important point which we need to know before proceeding ahead, everyone, is that in a similar way as you have potassium dichromate, you have sodium dichromate as well. Okay, you have sodium dichromate as well. Potassium dichromate is less soluble in water, so precipitate out easily. The one which is less soluble always precipitate out easily. Clear, everyone? Fine. And this is basically more soluble in water. Okay, more soluble in water, so it is difficult to precipitate out. Clear? Further, K2Cr2O7 is not hygroscopic. Hygroscopic means, beta ji, it do not catches moisture easily. The one which do not, catches moisture easily can be used to prepare primary standard. We know that in titration we prepared one primary standard. Now primary standard is the one whose concentration is known to us. So if you are doing the titration of K2Cr2O7 and oxalic acid, you already know the concentration of K2Cr2O7 and you can find the concentration of oxalic acid. Why? Because K2Cr2O7 can be used to make the primary standard. Why? Because it is non-hygroscopic. Clear? It is what? It is not hygroscopic. Not hygroscopic. Is it clear, everyone? Fine. However, your Na2Cr2O7 is hygroscopic in nature. It is hygroscopic in nature. Since it is hygroscopic in nature, guys, okay, that is why it cannot be used to prepare the primary standard. Therefore, it cannot be used to prepare primary standard. Am I clear, guys? It cannot be used to prepare the primary standard. Fine, cool. Any doubt, anyone? You can ask in the chat section. I can answer it. Any doubt, anyone? Fine. So now let's see first the shortcut for the preparation. Okay, let's see first the shortcut for the preparation of your K2Cr2O7. So now your KMNO4 is prepared with the help of pyrolusite ore. However, your K2Cr2O7 is basically prepared with the help of chromite ore. Now what is chromite ore? Chromite ore is FeCr2O4. Clear? It is actually a mixture of two oxides or two ores. One is FeO and the other one is Cr2O3. Clear? Fine. So here it consists of Fe plus 2 oxide and chromium plus 3 oxide. This is your chromite ore. Am I clear? This is what? This is your chromite ore, and from chromite ore only, okay, from chromite ore only, we basically prepared K2Cr2O7. Okay, what we basically do is we take chromite ore, guys, right? And this chromite ore, in presence of air or in presence of oxidizing agent, right? Air has O2, it undergoes oxidation. Clear? It undergoes oxidation, right? Fe oxidizes from +2 to +3. And chromium again oxidizes from +3 to +6. That means here you get CrO3. Now, if I talk about Fe2O3, beta G, this oxide is basically basic in nature. And I have just told you a hour or so ahead that CrO3 is acidic in nature. So when you make them react with sodium carbonate. Now sodium carbonate is basic. So it is basic. So it can react with the acidic oxide beta G. So on reacting it forms sodium chromate. Clear? Fe oxide remains as it is. And whenever you take carbonate, it decomposes to release what, everyone? It decomposes to release what, everyone? Beta G. It decomposes to release CO2. Is it clear, everyone? Fine. Okay. Now once this Na2CrO4 is prepared, okay, right, we introduce it to the acidic medium. I have just told you in acidic medium, Cr2O7 is more stable than CrO4 2-. It is stable in basic medium. So if you will do the medium acidic, it will get converted to Na2 Cr2O7. Is it clear, everyone? Fine. Okay. Cool. And once you will treat your Na2Cr2O7 with 2 KCl, right, it forms K2Cr2O7. And since it is less soluble, right, it is less soluble, fine, in water, so it gets precipitated out. Fine. or you can say that its ionic product exceeds its solubility product. That is why this precipitate out. Clear? This precipitate out, right? So this is the method by which K2Cr2O7 is prepared. This is K2Cr2O7 preparation. Clear, everyone? This is K2Cr2O7 preparation. Fine. So now let's do the preparation according to NCERT line by line, okay? Fine. Let's do the preparation of NCERT line by line. Fine. So first is chromite ore is fused with sodium carbonate in presence of air to give sodium chromate, right? I've just told you, you take chromite ore, which is Fe2Cr2O4. You fuse this with whom? With air and sodium carbonate, guys. Okay, so what it will form? Yes, what it will form, my dear bacha log? It will form Fe2O3, just told you ahead. Plus it will forms what? It will forms Na2CrO4 plus it will form the CO2. Clear? If you have to do the balancing, then two. Okay, this is basically Fe, right? Not Fe2, this is Fe. So this is Fe. So since there are two Fe, here you have to do two Fe. When you will do two Fe here, the number of chromate ions increases to 4, right? So you have to multiply here it with 4. And when you will multiply this with 4, the number of sodium becomes 8. So here you have to multiply it again by 4. Right? Now the carbon becomes 4 into 1. 4, right? So that means CO2 is also 4. And now in order to balance the oxygen, okay, I think there are total of 8 plus 16 plus 3. 8 plus 16 plus 3, that means 27, right? And here you have how many? 8 plus 12. That means you have 20. So you need 7 more, right? So you can do 7 by 2. Clear? Now this equation is balanced. Okay, it took some time, but the equation is balanced. Now, since your chromate ion is unstable in acidic medium, it is stable in basic medium. So in acidic medium, it forms dichromate. Am I clear, everyone? It will form what? It will form dichromate, right? Now, this Na2Cr2O7, once treated with KCl, 2KCl, it will form K2Cr2O7 plus 2 NaCl. So this is the preparation, the balanced one according to NCERT. Right, I have told you the trick and I have told you the complete one also. It's your choice what you need to do. Fine. Okay, now let's basically comes to the properties. Now let's just basically comes to the properties of K2Cr2O7. The very first properties is that it is an orange crystalline solid with a very high melting point of 670 Kelvin. Okay, again the same thing, it is soluble in hot water but moderately soluble in cold water, same as KMnO4. Okay, right. Now we know that K2Cr2O7 2 minus is stable in acidic medium. So once you introduced basic medium, it will get converted to what, beta G? It will get converted to chromate ion. Fine. And similarly, since this is stable in basic medium, so if we will introduce the acidic medium, it will get converted to Cr2O7 2 minus, right, plus H2O. This is very important. Very, very, very important. Clear? This is very, 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 very important. Am I clear, everyone? Okay, fine. Now, if I talk about the heating, on heating, K2Cr2O7 decomposes, right? K2Cr2O7 decomposes on heating, right? To what? Yes, to what, guys? It basically decomposes to K2CrO4, right? Plus, it forms Cr2O3 plus O2. I guess the decomposition is similar to KMNO4. So you can quickly do it. Quickly do it. Okay? Fine. Further, like potassium permanganate, potassium dichromate is also a very powerful and a very strong oxidizing agent, right? It acts as oxidizing agent only in acidic medium. Now, since it is an oxidizing agent, it itself undergoes reduction. Okay, itself undergoes reduction and oxidizes the other, right? In acidic medium, where it acts as an oxidizing agent, it basically undergoes reduction from +6 to chromium +3, okay, by the gain of 3 electrons, okay, right? But the 3 electrons are for 1 chromium, okay, +6 to +3. This change represents for 1 chromium, because here you have 2 chromium, both chromium have +6 oxidation state. So for 1 chromium, the change is 3. For 2 chromium, the change is 3 into 2. How many electrons, guys? The change will be of 6 electrons. Clear? The change will be of how many electrons? The change will be of 6 electrons. Okay, fine, clear. Any problem, anyone right here? Any problem? All clear? Fine. Since it is a powerful oxidizing agent in acidic medium, guys, so what it can do? It can oxidizes fine. It can oxidizes Fe2 plus to Fe3 plus. Fine. The similar oxidations which KMNO4 does. Okay. Fine. It oxidizes I minus to I2. Fine. It oxidizes sulfite to sulfate, nitrite to nitrate. Fine. So from here -1 to 0, here +4 to +6, here +3 to +5. Clear, everyone? Am I clear? Yes. Am I clear? So now I have given few questions, right, which you have to try it by yourself. These are based on potassium dichromate and potassium permanganate. Okay, so you have to try it by yourself. I've already completed this topic. Now let's have to start with inner transition elements. So I am basically taking a break of 10-15 minutes. This is the last topic. It will take 45 minutes only approximately to 1 hour. So I am taking a 10-15 minutes break. Okay. So we'll start in 10-15 minutes. Okay. This is the last topic. It will get over by 2:30 or so. Fine. Am I audible, everyone? Let me check the bike battery, okay, if it is fine or not. Fine, it will work for an hour now. Yes, am I audible and visible, everyone? Quickly tell me, quickly tell me. Audible, visible? Fine. So now we are at the last portion, after which the chapter will get over. It will take 45 minutes to 50 minutes to complete it. So let's rock and roll and complete it, okay? Right? Fine. So now we are starting with the last topic, which is F block elements or inner transition elements. Right? So here, what are F block elements, guys? F block elements are those elements in which last electron enters F subshell of the anti-penultimate shell. Am I clear? Fine. Now, anti-penultimate shell is basically n-2 shell. Right? I've already told you, if this is the nucleus of the atom, the last shell has principal quantum number n. The penultimate shell has n-1 and the anti-penultimate shell has principal quantum number n-2. Right? Okay. So in n-2 shells, which is anti-penultimate shells, F subshell, the electron is entering, that element is basically known as F block element. Clear, everyone? Fine. Now, F block elements are also known as inner transition elements. Why? What could be the probable reason for that? Yes, what could be the probable reason for that? Beta, see, since your F block elements comprises of lanthanides and actinides. Lanthanides lie after lanthanum and actinides lies after actinum, right? So that means they lie within the transition series, right? Although they occupy position at the bottom of the periodic table due to space issues, but they lie within the transition series, right? Okay, that is why they are known as what? They are known as inner transition series. Am I clear, everyone? That is why F block elements are also known as inner transition series, because they form transition series within the transition series. Okay, they form transition series within the transition series. Fine. Now, if I talk about F subshell, guys, if I talk about F subshell, consists of 7 orbitals, right? And these 7 orbitals can accommodate maximum of, one orbital can accommodate 2 electrons. So 7 orbitals can maximum accommodate how many? 14 electrons, right? They can maximum accommodate 14 electrons, right? That is the reason F block basically consists of 2 series of 14 elements, right? Fine. First series is basically lanthanides, which lies after lanthanum. Starting from cerium, whose atomic number is 58, to lutetium, whose atomic number is 71. Clear? Right? And the second series of 14 elements are actinides. Fine. So they basically starts from thorium, whose atomic number is 90, and goes till lawrencium, whose atomic number is basically 103. Clear, everyone? Right? Why lanthanides are known as lanthanides? Because they lies after lanthanum. Why actinides are known as actinides? Because they lies after actinium. Cool, everyone? Fine. Okay, let's move ahead. Let's just move ahead. Clear? Now, if I talk about lanthanide, lanthanides are known as 4F series. Why they are known as 4F series, beta? Because 4F is being progressively filled in lanthanides. In lanthanides, 4F is being progressively filled. actinides are basically known as 5F series, guys. Why? Because 5F is progressively being filled in actinides. Okay, here 5F is being progressively filled. Progressively filled. Am I clear, everyone? Fine. They starts from cerium, whose atomic number 58, goes to lutetium, right? There are 14 elements, guys. There are 14 elements, which starts from cerium, whose atomic number is 58, and goes till lutetium, whose atomic number is 71. And actinoids are also 14 elements, right? They are also what? They are also 14 elements. Fine. They basically starts from thorium, whose atomic number is 90, and goes till lawrencinium, whose atomic number is 103. Now see, lanthanides comes after lanthanum. So that means the group and the period of lanthanum is group and period of lanthanides. Right. Now lanthanum lies in period 6 and group 3. Right. Period 6 and group 3. Right. So lanthanides also lies in period 6 and group 3. Similarly, the group and period of actinides are the group and period of the group and period of actinium are the group and periods of actinides, right? So that is why we say that actinides basically lies in period 7 and group 3. Am I clear? Guys, is this thing clear? Any problem, anyone? You can ask me in the chat box for all those who are studying it till now. Fine. Now, majorly what we have to do the electronic configuration, which is time consuming. After that, rest portion will take hardly 15-20 minutes. Okay, right? So now let's come to the electronic configuration. Okay, lanthanoids. First, lanthanoids. So lanthanoids have a general electronic configuration of xenon 4f 1 to 14, 5d 0 to 1, 6s 2. Now how this electronic configuration is coming? See, lanthanides, if I talk about lanthanides lies in period number 6. Okay. So in period number 6, 6s can be filled. Then your, because you know that subshells are filled in the order like NS first. After that you have what? After that you have what, beta G? After that you have N minus 2F. Then N minus 1D. And then NP, right? Okay. Here in lanthanides, NP is not filled, so let's just forget it. Fine. So in lanthanides, after 6s, what could have filled? N minus 2F, 4F. And after 4F, 5D will be filled. And if you will compare the energy as per the Aufbau's principle, 5D is said to have higher energy than 4F, and 4F is said to have higher energy than 6S. You can compare on the basis of Aufbau's principle or on the basis of Bohr-Bury rule or N plus L rule, right? The N for 6S is 6 and for S, L is 0. So N plus L is 6 plus 0, 6. Okay. For 4F, N is 4 and for F, L is 3. So N plus L is 3. For 5D, N is 5 and for D, L is 2. So N plus L is again 7. Okay. Fine. Whenever the N plus L is same, the one which is said to have the higher value of N is said to have the higher energy. Right. Fine. That means 5D has higher energy than 4F and 4F has higher energy than 6S. So if I have to consider the case of lanthanum, okay, whose atomic number is 57, right? It basically lies in period number 6. So first we have to write the noble gas of the prior period, guys, right? And that is basically xenon, which is said to have an atomic number of 54. Fine. So first the electron should goes to 6s because it is the subshell of lower energy, right? And after 6s, as per the Bohr-Bury rule and Aufbau's principle, next electron should have entered 4f, right? But again, lanthanum has an exceptional electronic configuration. I've already told you. Here, the next electron basically enters where? 5d. Clear? Now, due to this 5d, the electronic configuration of lanthanum becomes exceptional. Okay, it becomes exceptional. Fine. And in fact, all those lanthanides where this 5d is filled, because idealistically in lanthanides, last electron should have entered 4f, right? But if electron is entering 5d, they have exceptional electronic configuration. Clear? 5. Clear, everyone? Only those are exceptions, right? Only those are exceptions which have 5d1. Now they are basically cerium. One is cerium, right, which has exception. Other one is gadonium, GD, which is an exception. Clear? And the last one is lutetium, which is an exception. They have electrons in 5d. Rest, there is no exception. How to remember these lanthanides? Okay, so you can remember in a manner that last century presented new democratic prime minister on social media. The first mnemonic to remember is last century presented new democratic prime minister on social media. Now from last, I am writing lanthanum right here, although lanthanum is not an F block element, but I am writing it. Okay, so this is lanthanum. Fine, atomic number 57. Clear? After that, from century, you have cerium, whose atomic number is 58. From presented, you have praseodymium. Okay, praseodymium, whose symbol is basically Pr. Then you have from new democratic beta G Nd, neodymium. Then from prime minister, we have PM, which is basically promethium. Clear, everyone? We have promethium. From social media, we have SM, which is samarium. Okay, which is samarium. First mnemonic done. Last century presented new democratic prime minister on social media. Clear, everyone? Right? Next mnemonic is European governments to ban dirty hotels entirely to make yellow building luxurious. So European government is actually about to ban the dirty hotels so that they can open new luxurious beautiful yellow buildings. Clear? So from European, guys, we have EU. Okay? Right? European. From government decided, you have GD, gadonium. Okay, you have GD, gadonium. From to ban, okay, from to ban, my dear students, you have TB, which is terbium. From dirty, okay, from dirty, you have DR, which is basically dysprosium. From hotels, you have holium, whose symbol is basically HO. From entirely, you have basically bachaji ER, which is a symbol of erbium. From to make, you basically have TM, which is thulium. Fine, TM. From yellow buildings, you basically have your YT. Am I clear? You basically have YT, which is ytterbium. And from luxurious, you have LU, which is lutetium. Clear? Now, I have told you the exceptionals are the one which are said to have how many? 1 electrons in 5D. Now, if I talk about lanthanum, guys, right? Lanthanum has an electronic configuration of xenon 54, 6s2, right? In 4f, it has 0 electron. However, in 5D, it has 1 electron. Am I clear, everyone? Right? Now, if I talk about cerium, what happens in cerium? That it also has 1 electron here, right? And 1 electron in 4f1. That means the electronic configuration of cerium is exceptional. Clear? It is exceptional. Absolutely clear. It is basically exceptional. Right? Now, here, praseodymium do not have any exceptional electronic configuration. That means here, the electron will enter in 4f only. 5D will have 0. Similarly, ND also no exception. In PM also no exception. In SM also no exception. In EU also no exception. Clear? However, in GD what happens? 1 electron goes to 5D so that you can have half filled 4f orbital. Clear? So GD has an exception. It has 6s2, 4f7, 5d1. Clear? And I've told you only those are the exception in which 5D has 1. So GD is one of them. Right? And the last one is lutetium, which is one of them. Clear, everyone? Right. In the case of TB, there is no exception. That means here you have xenon 6s2, 4f9, 5d0. Clear? Right. In DR, again, no exception. 4f10, 5d0. In HO, again, no exception. Xenon 6s2, 11, 0. In ER, again, no exception. Xenon 6s2, 4f12, 5d0. In TM, again, no exception. Xenon 6s2, 13, 5d0. In YT, yttrium, no exception. Xenon 6s2, 4d14, 5d0. In EU, since 4f is completely filled, so last electron goes to 5d, right? That is why I have told you only those are the exceptions where 1 electron enters 5d. The very first is cerium. Clear? The second one is gadolinium. And the third one is lutetium. Only these are the 3 exceptions, right? Rest, no exceptions. Am I clear? Rest, no exception. Is this thing clear? If it is clear, please tell me in the chat box. Perfectly clear, guys? Clear? Please tell me in the chat box. Is it clear? That means you have how many exceptions, guys? You have how many exceptions, guys? You have only and only 3 exceptions. Only 3 exceptions. Which have 5d1. One is cerium, which has electronic configuration of cerium 6s2, 4f1, 5d1. Next one is gadolinium, GD, which has an electronic configuration of xenon 6s2, 4f7, 5d1. And the last one, which is exceptional, is your lutetium, which has configuration of xenon 6s2, 4f14, 5d1. Is it clear, guys? Is it clear? Very good, Jasleen. Yes. Very good, Haritha. Okay, this should be clear to you guys. This should be clear to you guys. Fine. Okay. Now, let's now come to actinides. Okay, now let's come to actinides. Now see, before moving to actinides, we all know that actinides lies in period number 4. Sorry, period number 7. Actinides lies in period number 7. So here 7s will fill first, then 5f is filled, and then 6d is filled. Clear? First 7s is filled, then 5f is filled, then 6d is filled. And if I have to write the order of energy, 5f have higher energy than 4s, and 6d has higher energy than 5f. Right? So when we write the electronic configuration of actinium, from where the actinides begin, actinium is said to have the configuration of radon 86, right? So the 2 electrons goes to 7s. So the next electron should have gone to 5f as per Aufbau's principle. But here, the electron goes to 60, right? Fine. Okay. So that means in the case of actinides, right? In the case of actinides, only those will be the exceptions, guys, which although have 1 electron in 60, but there are some elements which will have 2 electrons in 60, they will also be the exceptions. Okay, there are 2 exceptions, the one in which D has 1 electron, 60, and the one in which 60 has how many electrons? 2. Clear? They are the only exception, because yeah, in lanthanides the electron should have went to 5f at last, but since it is going to 60, so it is an exception, right? Fine. Only those are the exceptions. Clear? So here, my dear students, the mnemonic is Thor protected Uranus, Neptune, Pluto. Okay, so from Thor you have thorium TH protected, you have proactinium Ta. From Uranus you have uranium U. From Neptune you have neptunium NP. From Pluto you have Pu, plutonium. This is the first mnemonic. Second is America, come back to California. So America you have Americanium. From come you have curium, from back to you have berkelium, from California you have californium. The next mnemonic is Einstein, Fermi made Nobel laws, right? So you have Einstein, fermium, Einsteinium, fermium, mendelevium, nobelium and lawrencenium. So we can remember in this format or with the help of this mnemonic. Am I clear, everyone? We can remember in the form of this mnemonic. Fine. Now thorium is said to have atomic number 90. This has 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102 and 103. Right, so now let's see the electronic configuration. Guys, in the case of thorium, right, so the noble gas is of the 6th period one. Why? Because it lies in the 7th period. So we will write your radon, right? So radon 86. So idealistically, first the electron should have gone to 7s, then to 5f. Okay, how many electrons remaining? 1, right? Sorry, how many electrons remaining? Guys, here thorium is 90, right? So how many electrons remaining right here? 2 electrons are remaining, right? Okay, so you have 88, so 2 electrons are remaining. So it should have 2 electrons in 5f, right? It should have 2 electrons in 5f, right? But life is always not simple. In the case of thorium, 5f have 0 electron. Instead, the 2 electrons are present in 60. Right? That is why thorium is basically an exception. After that, there comes Pa. Clear? Pa, or I should say proactinium, is also an exception, guys. It is also an exception. Why it is an exception? Because here one electron comes in 6d and 2 in 5f. Clear? So it is also having an exceptional electronic configuration. Mark it. Mark it. Clear? Then there comes U, again exceptional. Again exception. Why? 61, 5f3, 7s2. NP, again an exception. 5f4, 7s2. Am I clear? It is 5f4, 7s2. Okay. Then PU and AM are not exceptional. They are not exceptions. Why? Because they have 60, 0, 5f6. Okay. So here also in americium also no exception. However, in CM, exception occurs, similar to gadolinium. It has 1 electron in 60. Am I clear? Yes, am I clear? It has 1 electron in 60. Clear? Right? And then from berkelium to nobelium, fine, from berkelium to nobelium, no exception. So that is why I am not writing it. You just have to fill 1 extra electron in 5f. There is no exception. However, in lawrencenium, the configuration is 7s2, 5f14, 61. So this has an exceptional electronic configuration. Clear? Fine. So you just have to remember the one which are exceptional. So this is the exceptional. This is the exceptional. This is the exceptional. And this is the exceptional. So exceptional are only those one which are said to have either 1 or either 2 electrons in 60. Clear? They either have 1 electron or 2 electrons. Right? 62 is basically atomic number 90. And 61 is atomic number 91, 92, 93. Then atomic number of curium 96. And then of lawrencenium 103. So you can generally write it that 61 is of cerium, na, whose atomic number is 90. It is an exception. Clear? Right? And 62, this is 62. Only thorium is the exception. Right? Not cerium, thorium is the exception. Clear? Right? Fine. Only 90 is the exception. 91, 92, 93, 96 and 103. These are the exceptions which have 1 electrons in 60. These are the only exceptions. Okay. These are the only exceptions right here. Fine. And if I have to write the true general electronic configuration of F block elements, so you only tell me, what is it? Inert gas of prior period? Right? Inert gas of prior period. In NS, you will always have 2 electrons. In N minus 2F, you can have 1 to 14. And in N minus 1D, you can have 0, you can have 1, even you can have 2 electrons. We have seen. This is the true. However, the NCERT is writing somewhat different. Do not get confused. This is a true electronic configuration. True electronic configuration. Is it clear, guys? Is it clear? Fine. I think it should be clear to you guys. Absolutely clear. If clear, please give a thumbs up in the chat box. If clear, please give thumbs up in the chat box. Now, now, this is a question you can try. I've already explained you the electronic configurations. These are few questions you can try. The answer I will give in the PPT only. When I'll give you the PPT, I will give the answers. You can try at home. Fine. Now let's come to lanthanoids and discuss their properties. First is atomic and ionic sizes. Okay. Atomic and ionic sizes. So with lanthanoids, what happens is that as atomic number increases, right, the atomic and ionic radii decreases. Why? Because when you move left to right in lanthanides, here 4f is progressively being filled. 4f is progressively being filled. Clear? 4f is progressively being filled, which has poor shielding. Due to which Z effective increases and atomic hash ionic size decreases. And atomic hash ionic size decreases. This is basically known as lanthanoid contraction. Okay, so that means as we move left to right in 4f series, what happens is guys, from left to right, the atomic and ionic sizes basically gets decreases. Is it clear, guys? Reason is basically lanthanoid contraction, right? For example, if you have say all these elements of your lanthanides, so left to right, what is happening? Left to right, atomic size is getting decreased. Why? Due to lanthanoid contraction. However, there's an exception in the case of EU, right? EU, you have already seen, has 4f7 stable electronic configuration. And when the electronic configuration is stable, now metallic bonding is weak, right? Fine. So weak bonding, and due to which metallic radius increases a little bit. Fine. Okay. So that is why what is happening, EU is said to have more size than SM, right? Fine. Although it should have lesser, and it is even have more size than GD. Rest, there is no exception. And in the case of ionic size, so there is actually no exception, right? Left to right, your ionic radius decreases, right? Left to right, your ionic radius decreases. Okay, now we know that the most common oxidation state is +3. So left to right, what is happening? The ionic radius decreases. Clear, everyone? Fine. Okay. Now, here, let's come to the consequences of lanthanoid contraction. But although the size is decreasing from left to right, however, still the sizes are nearly same. And since the sizes are nearly same, beta ji, the physical and chemical properties of lanthanoids are nearly similar. Okay, fine. And due to similar in size, their separation becomes very difficult. Right? Okay, fine. Clear, everyone? Further, due to lanthanoid contraction, the size of 4D series element becomes nearly equal to 5D series. Like for example, titanium, zirconium, hafnium, right? I've already told you zirconium has larger size than titanium. However, zirconium and hafnium have nearly same size. Why? Due to lanthanoid contraction, Z effective increases and your size basically gets decreases, right? Okay, so therefore what happens is that RF, radius of zirconium, becomes nearly equal to radius of RF, which is hafnium. Why? Because beta G, here when the hafnium comes, before hafnium, what is happening? 14 Lanthanides are lying in which 4F is being progressively filled. Right? Fine. And due to the reason, since 4F is filled, which has poor shielding, Z effective increases, everyone. And since Z effective increases, size decreases, and the size of hafnium becomes nearly to that of zirconium. Clear? Nearly to that of zirconium. Clear, everyone? Fine. Okay. Now, since lanthanoids have similar size, I've already told you their separation becomes difficult. That is the another consequence. And the last consequence is basically the effect on basic strength. Okay, the last consequence is basically the effect on basic strength. So what happens is that we know that the most common oxidation state in the case of lanthanides is +3. Now here we are considering the lanthanum hydroxide also. Why? Because lanthanum also has properties similar to that of what, everyone? Similar to that of your lanthanides only. Okay, so first one we have taken the oxides of lanthanum, and as we move ahead, right, to the last elements oxide, which is lutetium, right? So here the oxidation state is +3, and here also it's +3. Now what is happening, guys? Here, left to right, we know that size of cation decreases due to lanthanoid contraction. Already explained you, right? Size of cation decreases, and whenever the size of cation decreases, the polarizing power of the cation increases, and when the polarizing power of the cation increases as per the Fazan's rule, guys, what happens is that the covalent character increases. Right, left to right, what happens is the covalent character increases, and if the covalent character increases, beta G, what will happen? What will happen? The ionic character decreases. Now, as we move from left to right, beta G, since what is happening, the size of cation is basically getting decreased, right? And whenever size decreases, guys, what happens is that guys, that when it will form its corresponding hydroxide right here, okay, right, hydroxide right here. Fine. So the removal of OH becomes very easier. What happens is the removal of OH becomes very, very easier. Why? Why? Because when size decreases, na beta ji, electronegativity increases. Right? We know that when size decreases, what happens is electronegativity increases. Right? We know that na, the one which is said to have the lower size is said to have the higher electronegativity. Clear? The electronegativity increases. Fine. And if the electronegativity increases, what will happen right here, guys? What will happen right here, guys? If the electronegativity increases, that means here, in this particular case, the acidic nature of oxide and hydroxide, okay, the acidic nature of oxide and hydroxide increases. Why? Because the one which is said to be more electronegatives, right, this is said to be more electronegative, right, so it can attract, you know, it can just easily, it's very easily, since it is more electronegative, so it's much easier for it, okay, it's much easier for it, right, okay, it's much easier for it to easily beta G, be acidic in nature, right? It's very easy for it to be acidic in nature. Clear? Fine. It's very easily for to be in acidic in nature. Why? Because see, it's pretty simple, guys. Whenever the electronegativity is getting increased, na Rajay, and the covalent character is getting increased, it's very easy for it to lose OH minus. Okay. I think I have said the vice versa thing. Just give me a second. I have said the vice versa thing. Sorry. Hi, it's about to get over. Just I'm having a sip of water. I think I have said a vice versa thing. Okay. Yeah. So now let's get back into track. I have sent 2 to 3 extra. Let me just explain it again. So what happens is when the size of cation is getting increased, electronegativity, size of cation is getting decreased, electronegativity is getting increased, beta ji. So what is happening? The bond right here becomes stronger. The lutetium oxygen or OH bond is basically a stronger bond, right? So it's very difficult for it to lose OH minus, right? If it is difficult to lose OH minus, then basic strength basically gets decreases and acidic strength basically gets increases. That means left to right, basic strength, yes, left to right, basic strength decreases and acidic strength increases. Duration 15-20 minutes. Give me 15-20 minutes. I'm overing it. Okay. Fine. So what I was trying to say that as the size of the cation decreases, electronegativity increases. So the bond between LOH becomes shorter and stronger. So the removal of OH minus is difficult, right? So basic strength decreases, or we can say the acidic strength increases. Clear, everyone? Yes, is this thing clear? Any doubt, anyone? You can ask me, I can repeat it again. Clear, everyone? Okay, so that means this is said to be what? This is said to be less basic. Fine, and this is said to be what? This is said to be more basic. Clear? This is said to be what, guys? This is said to be more basic. Fine. Fine. Okay, fine. So now let's just come to properties. Let's just come to properties of your lanthanides. The very first properties is that the typical oxidation state which has been exhibited by lanthanides is +3. However, they might exhibit an oxidation state of +2 and +4 also in some elements. Why? Because it results into the formation of stable electronic configuration, right? Okay, like for example, if I talk about cerium, right? What is the electronic configuration of cerium, beta? It is xenon 6s2 4f1 5d1. So when it forms bacha cerium +4, it is said to have an electronic configuration of xenon which is stable now. So cerium can have +4 oxidation state. Similarly, if you have ytterbium, clear, it is said to have an electronic configuration of 6s2, okay, 4f14 5d0. So when it loses 2 electron from 6s, it forms xenon 4f14, which is again in stable electronic configuration. That is why ytterbium, that is YB, can also have what, beta G? Can have +2 oxidation state. Similarly, EU, okay, EU. Fine. Now, if I talk about EU, what is the electronic configuration of EU, guys? Yes. What is the electronic configuration of EU? I've just told you. Yes, EU. You can quickly see it. EU is said to have an electronic configuration of 6s2 5f7, right? Right, 6s2 4f7. Xenon 6s2 4f7, right? Fine. So it can also lose its 2 electrons to form EU2 plus, in which it can have an electronic configuration of xenon 4f7. Clear, guys? Fine. So although +3 is the most common oxidation state, but +2 and +4 can also be seen Why? Due to stable electronic configurations. Why? Due to stable electronic configurations. Clear, guys? Is it clear? Haritha, is it clear? Fine. Further, all of them are metals, right? And they tarnishes rapidly. Okay, fine. Now, as the atomic number increases, hardness increases in lanthanides, and samarium, SM, guys, it is one of the most hardest element. It is being hardest as steel. Clear? It is as hard as steel. Clear? It is as hard as steel, guys. Okay. Further, since they are metals, so they have all the properties which metal has: malleable, ductile, high melting point, good conductor of electricity, high density, so on. Right? Further, beta G, these lanthanides forms alloy with metal easily. Now there is an alloy known as mesh metal. It consists of cerium about 55%, and there are other lanthanides also which are present about 42-43%, and nearly 5% it has iron, and it has traces of sulfur, carbon, calcium, and aluminium, and it is pyrophoric material. Now pyrophoric material is a material which basically produces fire when comes in contact with air, right? For example, bullets, as soon as they come in the contact with air, they produces fire. So that is pyrophoric material. So mesh metal is basically used to make tracer bullets and lighter fins. You know, the lighter used for the cigarette, you use it there. Am I clear, everyone? You use it there. Clear? Okay, fine. Now, next is basically the color. Color. Most of trivalent metal are colored in solid as well as in aqueous state. Why? Because they have partially filled f orbital. Now, in a similar manner, you have DD transition, guys, right? Then similarly, in the manner you have FF transition. So due to FF transition, beta G, your inner transition metal, or I should say your lanthanides, are said to be what? Colored in nature, right? Further, if I talk about magnetic behavior, fine, then there are few which are diamagnetic, and other than then are paramagnetic basically. Clear? Right? Fine. So those are lanthanum plus 3. Okay. Cerium plus 4. Right? It has 0 electrons in F. It also has 0 electrons in F. Clear? Then you have YB2 plus. Okay, you have YB2 plus. It has 14 electrons in 4F, and lutetium 3 plus. It also has 4F14. Okay, so these, except them, majority are paramagnetic. These, since have all paired electron, so they are diamagnetic. Am I clear? They are diamagnetic, right? Further, why they are colored? Due to FF transition. Why? Due to FF transition, like DD transition. They have unpaired electrons in F subshell, so they undergo FF transition. Clear, everyone? Any problem, anyone? Yes, any problem, anyone? Okay, right, fine. Now, let's move ahead. Let's move ahead. Further, bacha, for YB, plus 2 oxidation state is stable. Why? Because it has 4F14 electronic configuration. However, the more stable oxidation states for lanthanide is plus 3. So it is a huge tendency to get oxidized to YB3 plus. Right? Since it get oxidizes to YB3 plus, it basically act as what? It act as reducing agent. Am I clear? Okay. Similarly, you have EU2 plus. It has an electronic configuration of 4F7, which is stable, right? Okay. But this also get oxidizes to EU plus 3, right? Why? Because plus 3 is more stable oxidation state, so also act as a reducing agent, guys. Clear? Similarly, cerium plus 4 has a stable electronic configuration of xenon. Clear, right? But again, plus 3 is more stable, so it undergoes your reduction and hence act as oxidizing agent. Clear? Similarly, your TB, okay, TB plus 4 has a stable electronic configuration, but it also has a tendency to get converted to TB plus 3. Why? Because plus 3 is a stable oxidation state, so act as an oxidizing agent. Clear? It act as what? It act as an oxidizing agent. Clear, everyone? It act as what? It act as oxidizing agent. Clear? Right? Fine. Now, number 9. All lanthanides are metals, so they are said to be electropositive. Am I clear? They are said to be what? They are said to be electropositive. Fine. Okay. And they have similar reactivity. They react in a similar manner. That means all of them basically exist in plus 3 now. So they form compounds accordingly. Right? Okay. So if you have, say, lanthanides right here. So when they react with carbon, they can form few different carbides like Ln3C, Lnc2, Ln2C3. However, with rest of the elements, the product is predictable. Like we know that with oxygen, it forms oxide, right? So the formula is Ln2O3. Okay. With sulfur, it forms sulfide. With nitrogen, it forms nitride. With water, it forms hydroxide in plus 3 oxidation state. With halogen, it forms halide in plus 3 oxidation state. And since it is a metal, when react with acid, produces H2 gas. Clear, guys? Now, if I talk about your actinides, okay, although you don't have to study actinides in detail, but if I talk about your actinides, right? So what are the physical properties of actinide, guys? What are the physical properties of actinide? They are highly dense metal, right? And they can form alloys with metal. Again, they have white appearance, silvery white appearance. They are also electropositive. They also have high melting point, right? There also atomic and ionic radius decreases. Why? From left to right due to actinoid contraction. In a similar manner as lanthanoid contraction, you have actinoid contraction. That means decrease in the atomic radius of 5F series as we move left to right from thorium to lawrencium. Clear? Right? And in fact, since 5F has more poor shielding than 4F, so actinoid contraction is more pronounced than lanthanoid contraction. Clear? Okay, fine. Further, the color is, many actinoids are colored, few are colorless, which are said to have 0 or 14 electrons in F. Magnetic properties, many are paramagnetic, but some are dia, which have paired electrons. And their most common oxidation state, again, in plus 3. However, they can also have higher oxidation state of plus 4, plus 5, plus 6 and plus 7, right? And you have NP and PU. They have oxidation state basically of plus 7, okay? So they can exhibit the oxidation state of plus 7 as well. Clear, guys? Okay, so here I have written few differences which I've already explained. You can go home and read them. Fine. So now few questions. You can try them in homework. And now the chapter is ended from my side. Clear? Fine. So as I've told you, till 2:30 I leave you. So till 2:30 I'm leaving you. Fine. At last, I know my energy got little lower because obviously we get tired, right? But ma'am is trying to become fitter. So most probably till your NEET exam, ma'am will become more active and more fitter, right? Although I have given my 100%, I hope you guys like it. Fine. If you liked it, then please like the session and give a comment at end of it. Clear? Okay. Fine. Now, if anyone wants to study from me on plus, guys, if anyone wants to study from me on plus, right? So a flash sale is going on where you can get 10% extra discount if you use my code Sonali05 to buy the Plus subscription. The link will be below. You can buy it from there. And if you buy it using this code, you will come under my mentorship, my doubt group, my DPP access group. Clear, everyone? Okay, fine. Further, there is one crash course which has already been started, which is Phoenix All-Star Fast Track Reloaded batches, in which I am teaching few chapters in organic, right? All of them, all of the pioneer educators are teaching. So it is available only at 2799. You can again purchase this by using the code Sonali05, which will be available in the description box, right? So if you like this session, then don't forget to comment, right, once the session stream is ended. And again, we'll meet it to do coordination compounds, right? Till then, take care. Good day. Bye-bye.